Preface. This book discusses the discovery of a most remarkable electrical repomp. Eshep, though we are just at the beginning of a new body of information on an electronic entity whose energetics lie somewhere between chemical and nuclear binding energies. I believe this gateway will all rep into one of the greatest industries yet known. The research results described in this book were financed a method reminiscent of the scientific patronage of the Renaissance. This method has greatly lessened the need to publish results as soon as they were discovered. As a resuit, it has been 7 years from the basic discovery here described to the time of publication. The leaven of these data have been a closely held secret during this time. This electrical phenomenon once seen cannot be easily ignored. It is not an increment to well-known field where one can find comforting familiarity. Under such conditions, information about the repomp easily provokes skeptical responses. It is fruitless to try to prevent either these or the occasional harsh compliments and denials. Nevertheless, this work answers some long-standing and deeply troubling questions. The long time lag between the initial discovery and its publication has produced a larger-than-normal volume of new information. For this reason, the description of what happened in the distant past tends to be somewhat superficial. The total quantity of the data is large. Thege is simply not space to describe Safulu the old work, and still I al to get on with the new. Of course, the pastoral tendency is to get on with the pew and let fade devil-like the hindmost. For this resop, the descriptions of past work are somewhat truncated. This is therefore first a story, not a scientific treatise. At this point in the work, there is neither enough detailed data, poor AP inclination on the part of the author to create formal scientific publications out of the observations. We are able to say at present that the law of mutual charge repulsion has been overcome, the use of some Speep container, to the extent that a new freedom has EEP found in compressing uncompensated electronic charge to the acreage density of a solid, without the use of ectopole magnetic fields, ions, or relativistic velocities. The exact physical mechanism responsible for doing this is still a mystery, but there are theories available to help us along that are based Europe radiation containment from zero-point energy fluctuations. In spite of our ignorance of the details Gosha PPG, the observed processes, two conclusions are quite that we have tapped into a higher order of energy and charge density, where even the effective chalches of certain basic physical constants might be modified, and two, that a myriad of pew uses will emerge. In the absence of a guiding theory as to the co-attainment mechanism, empirical methods have been devised for manipulation of these fiercely charged entities, and engineering applications have yielded some electronic devices with much better properties than APU other technology allows. This book discusses primarily the most basic entity of compressed charge. The grid size for this structure is about 1 micrometer in diameter, and the shape appears to be spherical, although it could have fine structure that is not yet disegpil, our primitive methods of analysis. There is a distinct quantum-like preference for this size, although entities in the 1-2 micrometer diameter reshke have also been seen. This tiny bundle of charge, 1 micrometer in diameter, contains 100 billion electronic charges and has a very high electric field associated with it. It seems that everything must be paimed, and so the little A11 of Shkar we see has EP tagged MEU. The notion for this PAIM originally came up when they were thought of as an electromagnetic vortex. As time went up, and proof was still lacking for the vortex aspect of their constitution, I backed into a safe Latin sorpa and named them Elestrum validum. Electrum validum. Canny translated loosely TPTO strop G L strop. They are echoey bit of that, and there are times when I wish they were not quite so strong. This beginning phase of the Ocarol riot has been named PACER as apiosropum for rotile compression via electromagnetic radiation. This nilm alludes to the use of electromagnetic energy a containment mechanism, including possibly the use of the electromagnetic epergu of the chasuchum, AP aggregate of virtual particles, photons, as polarizable medium and as the source of energy for compression. Some of my favorite books contain glimpses of the thought processes that went on behind the actual work performed and reported, because I believe that these thought processes are even more valuable than what is reported. I am including some of my own thoughts and working methods in this writing. Also, you will certainly notice the absence of any mathematical expressions, beyond the most basic numerical ones. I don't think mathematically, so I don't write mathematically. This should pose no difficulty for those who intend to use the results shown here. I am very device-oriented, and I do not generate theories of the usual type, a viewpoint that is reflected in this writing. However, from time to time, an attempt will be made to generate a theory in order to cover gaps in the observations. The measurements will always be senior to the theories generated. The theories should be thought of as a railing to guide us from one isolated observation to another, in the full knowledge that there are any number of railings available for guidance, and not all of them can be real. The apparatus used to do this work was very simple, and this leads to the expectation that future EV technology can also be simple. Looking back on these events, I can see with certainty that I was intentionally playing the double game of finding new effects and, at the same time, doing so without complication. I am an explorer and will not burden myself with unnecessary and cumbersome methods and apparatus. I got where I wanted to go with an economy of effort, and it was fun to do so by following nature's most fundamental law, the principle of least action. She. Chapter 1. People, Places and Things. This chapter describes the people, the places, and some of the apparatus that came together to begin the quest for the elusive EV. The importance of workspace. I am strongly affected by the surroundings where I work, both the inside and the outside. For me, the details of the working space are intimately involved in getting things right. For this reason, I spend at least half my time doing tasks that may look useless, but are directed towards creating the right conditions in the working space, conditions conducive to efficient work. This problem of working efficiency matters because I have to produce the devices I use myself or give in to the incredible inefficiency of having someone else do what I want done. Making my gadgets and lesser doodads is, at best, dog work. For this reason, I try to begin with a working environment that helps me circumvent all of the myriad built-in reasons to stop that seem to plague us all. Without such an environment, it is all too easy to let the problems bring us to a halt and to cease work. Actually, it is not hard to work in a physical mode, where no creative thoughts intrude on the thoughts necessary for the physical work, but, given half a chance, the creative thoughts arise and throw me off the track, spelling disaster for efficiency. A lot of tricks are needed to mix the two modes, the physical and the creative. As I build the working space, I try to perform some of these mental tricks that potentially allow the will-o'-the-wisp creative mind to coexist in harmony with the more mundane part of the mind capable of routine production. I've developed some tricks that allow me to think good thoughts and work on them at the same time. I'll let you in on some of these as we go along. Where we began. In 1975, having had mouthful of living and working pair 2 Mapu people, I began building Mew House and Laboratory in an out-of-the-way raise that would hive you, put the best features that could think of to remote good worn conditions. I had located a spot about 40 miles south of San Francisco that was far enough from the Pacific Ocean to avoid the corrosion problems of the salt air, but close enough to take advantage of the soon, foggy, marine air layer that invigorates me. This spot was hidden in the Santa Cruz Mountains, surrounded fir and redwood trees, with great-tasting spring water coming out of Pelu every crack in the ground. This is Ekas what I wanted at the time. You can get an idea of what the rays looked like on the outside from the photograph in Figure 1.1. Figure 1.1. Figure 1.2 shows the conference room we often used. In attendance for that particular day, from left to right Arupdi the circle, were the dog, Ed Mao, Nawan Putoff, the author and the founder of Jupiter Technologies, Bill Church. Figure 1.3 is an inside view of one part of the laboratory, real places, and things 1 to 2. Figure 1.2. Figure 1.3. People, places, and things 1 to 3. This wasn't the greatest raise in the world to raise a family that needed any social life at A11, but the social life would have to wait for a while. Somehow we got used to the fact that when the creek came up in the fall, we could not get out in the car until late Mao. We had to walk over a rickety suspension bridge that could get wiped out any time a storm brought big tree down the creek. We survived all of this and more, and the living and warm was good. The people. Ope Day in 1976, when I was bored with the overly predictable things I was doing and felt the urge to do something about my situation, I went to visit a friend of mine at SRI International and to seek an audition with a researcher there, Hal Puthoff, who at the time was director of a one-arg ESP program, in the hope that I sockhold find something realu nuts to work op. Mew friend introduced me to Hal, who was trying to separate the wheat from the chaff and bring some scientific order to a mazy field. We hit it off very well from the beginning because, unknown to me, he had shared an office with an ex-contract monitor with whom I had worked for many years. Thus I was not entirely unknown to Puthoff, and conversely, I had read Otst some of the things he was doing. What I did not know at the time is that he was Ope Crackerjack theoretical physicist with a major quantum electronics textbook to his credit, and that, as time went on, he would come up with some earth-shaking revelations, Sopsipi PG, the foundations of physics. Although Nay1 was a PhD physicist, he had set that HND of work on the back, ERPA, for while to do his daily work in ESP phenomena at SRI. At this point in Hal's life, physics was his hobby, but we would soon begin to relow the physics game fiercely. After we met, practically on the spot, Hal called a friend of his from Texas who was known Rimarilu for his fast food business, Church's Fried Chicken. Within 2 days, Bill Church had some to Menlo Park, where Puthoff lived, and we struck a deal to do work in far-out physics. Bill was to provide the financing, Hal would do the theory work, and I would do the ecroremeptal things. Actually, we also had a lot of crossover talents that we did not know about at the time. One of the biggest surprises to me was to find out that Bill and NA1 had been collaborating for some time op topics in theoretical physics and had done pretty well with some of the realu basic considerations in physics. Real, places and things 1 to 4. Bill Church is a very interesting character, not easily or simply described. If there was ever anyone who fell to earth from somewhere else, this is the guy. His methods of operation are totally abnormal, but they are very effective in certain places. I am not sure how others perceive Bill in his business world, but in our scientific world, I see him as a mystical inventor. I claim that, aside from supplying all of the money to do our work, Bill is best at getting us unstuck from problems that would have stopped nearly any other bunch. He has an intuitive feel for the physical universe that comes through at a critical time when a turn in project direction is needed. When this talent of Bill's is added to the powerful way Hal manipulates physical theories, and to my experimental abilities, it all adds up to more than the simple sum of our 3 talents. We 3 have whipped some really nasty problems with a higher efficiency than I have ever seen before. Preliminary efforts. We tackled some earlier projects before taking on the project that is the main subject of this book. Those projects were even less complete than this one that I am reporting on here, and our methods would undoubtedly be criticized by the stodgier members of the scientific community. Yes, I am fully aware that the way I handle a subject, both the actual work and the description of it, is not in full alignment with the more conservative standards of the scientific community. I like the way I do things, and this deviation from the norm does not bother me too much, because I am very effective as I am. Suffice it to say that all of the Kalia work done served as a good background, and in some way set the stage for the present work. I usually work with so many choices of what to do that there must be a very selective process at work to narrow things down. In my world, there are far more good things one could do than there is time or resources to do them. The key to efficient progress is finding the best way or path out of a selection of at least hundreds of alternatives. People, places, and things 1 to 5. Looking for the project. Our principal goal throughout most of the exploratory work was to find an interesting energy source. Our basic inclination was to search for this at the elementary particle level. We also had a strong bias not to invoke nuclear processes. We were not left with many well-known theories to go on, and so our search took us into many strange places. We were well equipped for such travel. We were a physicist who was also working on ESP phenomena, a mystical inventor, and a maverick thing-maker. We could see no terror in any of the dark alleyways of science we went into. This journey would make Oz look like Main Street, USA. In the work preceding this project, and toward the end of one of my forays into a dark scientific alley, having to do with destabilizing electrons, and thereby obtaining their annihilation energy without the use of positrons or anti-matter. I was totally surrounded with theories of elementary particle structure formed from vortical flows of primeval substance. These theories were expostulated by Shekawat, Jaley, Larson, Kraft, Golko, and a host of others. All of these notions showed the possibility of stable, quantizable, force-free structures that could be taken apart by some process that would yield energy gain. Thus, I was plenty tuned up for vortex notions and was thoroughly into all of the tricks that fluid vortices play in either regular fluids or superfluids. I was ready for an experimental attack on the elementary particles and had actually started some exploratory experiments. I remember that about this time I was feeling pretty much alone, and I felt that this exploratory journey was going to be a long one. I must have thought how nice it would be if something really easy would come along. I suppose I was doing a review of the easy things, such as the plasma vortex work of Wells and Bostick, when the notion struck me forcibly to call Winston Bostick, of the Stevens Institute of Technology. I did call Bostick, and he told me that in just a few days there would be a conference in San Diego on November 10th, 1980, and that we could meet there and talk. We met, and we talked, but we did not talk about the regular old-type plasmoids on which he had published earlier. Instead, we talked about the electron concentrations he had been seeing in an electron beam he had made by using a plasma focus machine. Bostick called these effects vortex filaments, Nardi et al., 1980, and the word vortex sucked me into them. I had been well prepared to deal with that subject, and this looked like a great way to apply what I knew. People, places, and things 1 to 6. It was clear that the Repa-Mepa Bostick alluded to had something of interest in it, since most of my écrieps in the physical sciences had dealt with devices plagued with space charge problems. I had a sore spot there from being rubbed so much, and was ready to reach for any ointment that promised relief. There was yomthing in these vortex filaments that promised relief. If one could believe the PHMers, they were already in gross violation of the space charge law. Possibly there were mitigating circumstances, such as enormous 1-OSA-1 magnetic fields, that permitted their existence. Whatever the reasons were, I was in no mood for reason. I simply grabbed onto tie effect and began Lear PGA11. I could out it. 11 other thoughts and approaches went down the TUI, and I was to be locked into this area for the next several UShes. Changing source. This description of how I got started, Mao seemed to suggest that it was easy to th up from op thing to another, or to abandon a year or more of work op something that ops looked so good. It was the only thing in Mu Life. It was not easy at A11. It is very hard, actually, to steer to a new sub when heavy commitments Hache EP made to an earlier route, op of the finest things about OCAR organizational structure, was the nice balance we sawed manian between doing enough concrete work to serke as a guide in the physical world and still manianing the mobility of alert minds. Supporting structure. I cannot assuratelu describe OCA process of decision-making, but do know that it contains elements not usually found in contract resemch work. For one thing, we have never written a proposal. We even had a motto, it is all right to be wrong, to be right. Actually, R was always reluctant to take this hypothesis too much, so I modified it for mu own ruroses. You saying it is A11 right, to be wrong, to be right, once. There were no reports or ECHEP letters required as descriptions of the work. We all knew what we were doing and what had to be done. Any formal stricture would oplu serve to destroy the mobility much needed at this point in the work. The time would some when the standard structure would be needed, but for now I could use a technique I call snepping. People, places, and things 1 to 7. Would SEOP erupt HMD to do things, Petcher hitting them head op. We did not hash the right HND of Roa for head-on confronitions, would snap over worksheets that seemed unessential at that particular time. Although I knew full Cree-11 fat, someday one would have to fill in that quagmire to allow the armu of workers that might follow to cross Oka ill at the time. I thought, why should I bother filling it in now? The armu might not be coming this way anyhow. Some real might wonder how it happened that AP individual like Bill could support such AP effort without crying daily for some HND of spin-off product or whiz-bang that could make a buck. I wondered, that too. Of the ingredients Bill had in HS makeup, which allowed us to proceed into the far reaches of physical science, was his ability to do just that. I was constantly aware of the need for conservation of resources, and being Patrol Pinch PNNY helped. Still, I never felt APU pressure to hold back what we judged was right to do. For Bill, what was right came before all else. I was the one that had Trockley going out to the thin leading edge of right. Although I greatly prefer skating thin ice, or exploring as far into the Arvoods as possible, looking for the Nolu Grail of Science EP, it is absolutely necessary for me to have Yomiopi hand to hold. Bill APD, nay one, and I formed a chain of safety for each other, and we should all go a long way into the woods without feeling too threatened, it. I doubt if I would have gone elope. I might well have terped back to something safe. These formative years leading up to the actual work on the EV were realu good years. Looking back this time sometimes gives me fey illusion that nothing but joy stemmed from the magical methods we used. The facilities. In the beginning of this experimental work, the laboratory consisted of a building of about 1,200 square feet, designed to either a house or shop. Additional building of about 500 square feet was used to house apparatus too shrewd for the laboratory space, and also used to store the junk that is always a part of such a 1A. A few years after the beginning of the project, another 1,500 square foot ARP-like structure was built to house the heavy aerators and dig-2 process work that had overflowed from the laboratory. At this level of development, these facilities were useful and productive, and for several years I worked elope here doing all of the things that had to be done. Reoral, places, and things 1 to 8. The apparatus. The apparatus available in the beginning was pretty pitiful and sockled easily, described as auroriate to a garage operation. The only saving grace was that this apparatus was mostly hand-hewn with tender-loving Sarah, an old instrument maker, me, and it could do wondrous things. As time went on and the rays of the peak quickened, Mapu purely commercial items were added, and they were mostly general-purpose tools. Special-purpose devices were not purchased because of Mon-U deep convictions that forefront work required forefront tools. The tools we needed always had to be made because there was potpath market to surge in despery to produce them. The most obvious exception to this way, a scanning electron microscope that was purchased to save time in building a low-energy electron interferometer used a previous peaked. Homemade interferometer would been better, but time was of the essence. DS, it charped out this SEM, was the key instrument in discovering the EV, and we had made a fortuitous decision in buying the SEM. The staff. There was no subcontract work and no administrative personnel in Mula Orayuri. I was the whole show and I loved it, most of the time. Of course it got lonesome, but then I was living where I worked and could always go into the house for a chat with Claire, my wife. That helped a lot. In mid-1981, Mew son Stephen began Sopsdusti PG laboratory apparatus for me, and it was Slesh that he had a talent for such work. This was a good time for him to begin Warn PG with me, because some relatively routine work was becoming available as I settled down to serious EV work. Except for AP Apprentice and other part-time help used for production of 2 Ellestrop Samaras, Stephen and I were the entire Ecrarametal staff until we moved to Dustin, Texas, in 1984. The Mosh to Austin. In Austin, we put together a SIP-DASD laboratory with real employees and a mappager. We intended in this laboratory to do what Mighty called development work. It was also our intent to begin building a Aurora research laboratory that I could feel realu good about. It furped out to be quite a chore to find an acceptable raise to build the laboratory, and so this effort was delayed for Perlu 2 years before construction could even begin. Reoral, places, and things 1 to 9. Beginning the Rogist. Let's jump back in time to Nokshim, 1980, when Bostic first told me about Vofiex filaments. The day after that meeting, I wrote in Mew Notes, "Is this the Ellestrop laser?" I was thinking that the Sohereps implied would produce the particle equivalent of a photon only, sir. I also made entries in Mew Notes of plans to condense electrons to the density of a solid U using the techniques had just leapt about, and the guidelines published, U Malmberg, Malm-Erg, and O'Neill, L977 Tara, 1333 to 133b, stating that densities of 1020 electrons, rare Suis centimeter, could possibly E condensed with modest electron temperatures and magnetic field strength. NMDI, an associate of Bostic, had also stated that there were a degree of electromagnetic guidance available for these Chortek filaments, APD to me, that was an essential parameter. Almost immediately I had vast plans for further cooling the electrons, adiabatic demagnetization and spontaneous cyclotron radiation to get the necessary degree of coherence that was implied in the order shown the vortex filaments. Older plans for using freestanding vortex rings of intense solid charge to promote electron annihilation were dusted off. In almost Poe time at A11, everything converged to say that this is where I would stand for the fight to some. A driving thought. Although OP January 30th, 1981, had made a formal statement, does Lara PG an official switchover from theory work, which to me meeps not building anything but thinking a lot about it, to experimental work. I had let a few theory thoughts rear in. One of the most significant rarers I found during PG this period was one U. Bergstrom, 1973, RMA 4394 to 44,021. Bergstrom declared that their ALU was something like AP ether, and that it was dielestious in nature and therefore polarizable. Ney said fat Mapu effects would arise from this, not the least of which would be a single method of containment for charge of a single kind ranging from elementary particles to bar lightning. Bergstrom literally set me afire with his rarer, but try as I would, with and without his help, and the help of other great physicists, I could not get a grip on the physical really of what he was saying. I knew there was a lot of truth here, but I could not chess it, just toward the data for later use. As it turped out, put off work to slesher the matter much later and gauge us another grip op our new world. It is a pleasure to me how we all, including me, think they know where they stand when there is nothing but thin AIG under them. It is seriously clear from where I stand now that I did not know anything really important about what was to happen following that meeting in November 1980. Yet, have EP able to follow unerringly a tenuous path laid down at that time. I love this process of pection into the future, and I hate the ultra roadblocks thrown up minute as we proceed down the pected path. Real, places, and things 1 to 10, a method of attack. Everybody has their own methods for getting ready to solve a problem. Mine is to tool up with every gadget that I can think of that will apply to the problem. I never think about what I can buy. I could never afford to do that. I start designing specialty instruments and tools to help solve the problem. I back way up into the basic technologies that these instruments stem from and come out of the comer with something specific to hit the problem with. Of course, I take a lot of big swings that miss the mark, but all is not lost because I can always put the gadget away and use it another day. For this fight, the tools I chose were a very short-pulse vacuum Marx generator for driving a miniature version of the plasma focus machine. I would also need an especially fast oscilloscope to see what I was doing. Both of these would be built and customized to the work using flame spraying of metals, insulators and resistors as the basic construction technology for the instruments. Boy, was I nuts. I always do this kind of nutty thing when I am working best. I think it is some kind of threat waved at the problem or a mystical scheme to scare away the devils. I rarely ever do anything as cuckoo as I threaten, but the pattern persists. You can see why I don't get along too well writing proposals a year in advance and then sticking to them. That kind of working structure would drive me over the edge. The physical attack. A lot of time went by as I tooled up for the onslaught. I flame-sprayed oxides, metals and carbides on all kinds of substrates. I designed special fixtures, shields, gas mixers, miniature nozzles, and high-velocity guns. The detailed design of a miniature high-vacuum Marx generator, capable of producing 1 nanosecond pulses of 500 kilovolts, had taken shape and the construction technologies were in good order. I was testing one of the Marx storage capacitors for breakdown limits when I noticed an unusually straight, narrow, and uniform breakdown path on the surface of the dielectric. This was one of the most normal things you can see in vacuum breakdown over a dielectric surface, and I had seen it hundreds of times before in my life, but the bell rang when I saw this one. Somehow all of the previous data I had been gathering came to the fore and said this streak is not just a streak. Look at it carefully. I put together some thoughts on how to test the thing I was looking at, and the notion came to me to use the witness plate technique that plasma researchers use. I got a piece of brass foil 0.001 inches thick and put it under the dielectric electrode I was testing so that the discharge would strike it instead of the main test electrode. The voltage was raised to about 20 kilovolts. The discharge occurred. The path of the discharge went straight to the center of the foil, and a miniature explosion occurred that coated the ceramic with brass and left a tiny mark on the brass. People, places, and things 111. Revelation. In the optical microscope, the mark was interesting but not entirely distinct. I fired up the scanning electron microscope and took a look. The mark I saw was identical in size and shape to those obtained by Bostic in the plasma focus machine and the TX-25 relativistic electron beam machine running at several megavolts. This telltale mark signaled the presence of the vortex filament I had been seeking. I had arrived, and all of my fancy marks generator and fast oscilloscope work went out the window and into the BAM. It was May 15th, 1981, and I had wasted all of that time working on the wrong thing, or so it seemed at the time. I was literally crushed in the face of success. People, places, and things 112. Chapter 2, Demise of the Filament. There it was. The unmistakable fang mark of an EV, and it had been made by the simplest process in the world instead of by using an atom smasher. I was ashamed to have been sucked into going the long way to get to this point, but at least I now had presence of mind enough to recognize the need for simplicity and smallness to unravel the remaining knots. I could easily see that large machines and high-energy discharges were good for justifying large budgets, but not for finding the answers I needed. Low voltage and low power were the solutions to many of the detection problems facing the evologist. These little EV devils had been hiding in the plasma trash of almost every spark discharge since the time a few billion electrons could get together. I was determined to find out how they had hidden from so many people for so long. To do this, I hit the literature. They were everywhere I looked. Lafferty, 1980, had edited a book about them under the heading of vacuum arcs. Mesiarts, 1983, had a beautifully elaborate description of the birth of a cathode spot in an arc that was probably the creation place for an EV. I was inundated with data, but I was most humiliated when I went back to the work of Boyle, and others 1955, and Kisliuk, 1956, and found strike mark photographs on electrodes of relay contacts operating at 25 volts or so. I had used these references in conjunction with earlier field emission work I had done, and was thoroughly familiar with the work, but had somehow overlooked this point. Why hadn't I checked the literature before? Because I wouldn't have seen what I was looking for anyway. Bill has made me very aware of this effect with his name for it. He would say, "You don't have confront," meaning that I was unable to see the truth at this time, even if I were looking straight at it. There is a certain time when we can, or will, accept the truth and not before. Comparisons. Let's compare witness marks on some photographs to see some of the similarities, despite the different conditions under which they were made. Figures 2L22 and 2.3 were made in a TKH-25 relativistic EM machine operating at about 5 megavolts. Figure 2.1. The pictures in Figure 2.1 through 2.3 were given to me, Winston Bostic, when he was warming up the TKH-25. Fig 2.1 is a scanning Eelstrop micrograph of the Wi-Fi iris plate, while Figures 2 to APD-23 are optical photographs. In both cases, the witness plates were 0.01-inch thick titanium metal foil placed at the anode of the discharge. Demise of the filament 2-2. Figure 2.2. Figure 2.3. Demise of the filament 2-3. Figure 2.4 was made in a chasume discharge at 10 holovolts using apparatus somewhat similar to that shown in Figure 2.5. Figure 2.4. If you direct your attention to the isolated splash marks in the photos, Figures 2.1 through 2.4, you can see that they are remarkably alike, in spite of the EPIRGU differences between the two experiments. In Lafferty's book, these shapes she referred to as Morpie-PG glory structures and are usually found on the cathode electrode. Some identical structures she found op anodes, but the operating conditions for producing these are much narrower in stand-MD Chasham arc for the generation of anode strikes. Demise of the filament 2-4. There is absolutely nothing fancy about the structure shown in Figure 2-5 on the following page. The cathode can be any conductor I know of. The dielectric can be any insulator such as ceramic, glass, plastic, or vacuum. The EV is formed and propagates to the anode whenever the direct current, or pulse voltage, rises to the point at which field emission begins a runaway switching process aided by metallic vapor from the cathode emission site. This process happens 100% of the time. The worst thing about this simple apparatus is that the voltage gradually rises from shot to shot, due to cleanup of the emission sites, until an equilibrium value is reached at some high voltage. I looked at these witless mark structures a long time, as others have, wondering why there is no really prominent line structure depicting the flow of the end of a filament of energy over the surface. If these are filaments depositing their EPIRGU, why are they so locked in position and upali to draw lines, you either moving or string in a skewed fashion? Why always straight on into the surface without error? I was told, you those in the know, that this is the way, and that there were reasons, and that even the length of the filament can be known, you certain magical manipulations. There are image forces, you know. Okay. Somehow I was not satisfied. Low energy level exploration. I started putting the EVs through their paces. I found what materials they could be formed from, what they ran on best, and what made the best witness anodes. This was a time for wild, rup-amok, Edisonian experimentation. Nothing was sacred. I would have used shoe leather for a dielectric if Mipe had not already been wogged too thin. It is for sure that nails worked for cathodes any day, and did not do too badly as anodes either. I found the demon Ev loved to run in grooves and hide in cracks. The smaller the better. It even prefers running in totally enclosed structures, such as in tubes and between plates, to running in the open. At this point, I was convinced EVs were female because of the way they are always looking at their mirror image in dielectrics. Up to this point, I was still trying HHD to break away from the convention of plasma physics and fusion work, where bigger is better. I was using a 40 picofarad capacitor for the energy storage source, and a mechanical Chasium switch to discharge the capacitor. At 10 kilovolts this recepts, a lot of EPIRGU and Fey EVs made were covered up. A big and nasty discharge that obscured a lot of the details I was looking for. One day went to the smallest cathode capacity I could make for the discharge, isolating a tiny piece of metallic material op the tip of a resistor-coated ceramic rod. With this configuration, the capacity of the discharge was below MU ability to measure easily, about 1 picofarad. The EVs came out as interesting as Eka from this source of below 10 to 6 joules of energy. Demise of the filament 2-7, Figure 2-6. Figure 2-7, demise of the filament 2-8. The photos in Figure 2-6 and 2-7 show APCM image of the witness plate of titanium. The energy used here stands in great contrast to the 1000 joule shots of the plasma focus machine. The small, round, bright spots on the photos she deposits of molten metal blown off during the discharge. There is a large distribution of Stike mark diameters shown in the photos. The magnified view in Figure 2-7 shows some clear skikes of 1 micrometer in diameter. The largest size is limited to about 10 micrometers in diameter. During this low EPIRGU push, I flame-sprayed aluminium oxide onto schiestous metal anode backing plates to thickness of about 0.05 inches and generated beautiful EVs at 2 kilovolts applied voltage. The cathodes for these tests were usually brass or sorrow wire, and, as the char points were knocked off the discharge, the voltage would rise from shot to shot. Following tracks with the SEM, I SMA interested in seeing the rack the EV made use some method other than optical examination of the plume it left. The SEM was set up to accommodate making EVs inside the vacuum chamber, and the beam was set up first to adjust the surface charge to whatever was needed to make the EV happy. And then the EV was fired, and the surface was analysed for Schke redistribution, you running the SEM at very low Serept, so as not to disturb the charge pattern. Figure 2.8 and 2.9 show examples of this HND of Ororatio. Demise of the filament 2 to 9. Figure 2.8. Figure 2.9. Demise of the filament 2 to 10. Figure 2.8 is a calibration RUP, using the eam of the misread first to deposit charge in simple line retegb. After the charge is deposited, the picture is scanned, and the charge shows as a dark line going from left to right. There is also a squome pattern of Schke, showing up this particle RUP. The rough line below the centre ein is a scratch up the ceramic surface. These charge retegbs can be wiped off you adjusting the eelstrop, pegu, and charging the surface to equilibrium. Figure 2.9 shows a ceramic surface that had pumerous runs made on it. The bright spots arranged in a semicircle represent the initiation spots pair a large cathode wire on top orihi ceramic using a configuration simum to figure 2.5. The streaks running taum D, the edge of the ceramis, are dishmish trails. Often these discharge trails be seen to follow small scratches up the ceramis surface. Nothing much was lerped, you using this method except that there was charge scattered all ochre the surface. This is ope of those places in the work where, if I had persisted with the measurements, I would have lerped something of value because, as it turped out, charging surfaces were going to be a pain. I slid right on you this good thing, synchronization search. It was time to hit this vortex filament shape rolum again. I was going to find out how long they were and how variable the length was, and what caused it. The RR-Fest scheme for this would be a coincidence method whereby ope filament would be used as a probe to measure another. This is just a chariot on particle scattering and collision cross-section work. What I needed were two sources that solidfied synchronously with a shear timing op ope to concol coincidence. Good luck. The times of interest here were somewhat less than a picosecond of jitter in FSIPG to achieve even half reasonable results. Nobody in the world had some close to that. So I stumbled on in my inimitable way to make two sources of EVs that were synchronized to better than a picosecond. As you sap well imagine, there were a lot of trials, and there were a lot of test techniques, and knowing when I had a good result was at least half the ROLEM. Demise of the filament 211. The main attack in this encounter way to use one EY source to trigger another and still have something EF ochre from the feed Eve to sum the target for the collision experiment using the clone, delayed in time as the bullet. After all, these were just fierce bundles of charge, and could be handled like more ordinary electronics, if ope cranked in enough constants to offset their brashness. Easier said than done. I tried a lot of dopey things that seemed reasopally at the time, but the combination of poor generation technique and raw measuring technique kept me out of the picosecond domain. Mosaic guides. While Mapucheripji to do this, APD to conquer time jitter, I had evolved a technique for guiding EVs a Roop D in the Somrelix circuits that had developed. The finished parts looked like Mipiacha tile floors that had been laid you a 2-year-old child, and so I called this the mosaic technique. It consisted of cutting out little PMT of sockets, guides, and whatnots, and gluing them down to the base ceramic plate that had a sum the starting point for Perlu all experiments. An ecomral of this HND of YT Ukcha is shown in figure 2.10. AP anode was flame shroud sheptopeth, and AP array of cracks or 90-degree edges were formed op the top, U-bonding down other ceramic book. The eye greatly referred to follow the boundary of a 90-degree sorper made to the substrate, U these bonded ceramis or glass parts, instead of following a flat surface. Two other mosaic features shown in figure 2, she the movable guide, and the Laksha. The Mokali guide is used as a time delay unit in Fei Ekamle, shown MRSD, is accomplished, you putting a bevel on the section of the guide that is made Mokale. This Ratishla placement of the Echa 1 Koyi, the EV, to leave the straight wall for the beveled wall, thus allowing the EV to proceed to the Lopsha, instead of continuing around the same piece of material onto which it was originally locked. The launching function is accomplished, you using AP acute angle at the end of a guide. The EV would rather go forward onto the flat substrate than around the sharp sauper. Considerable SARE is required in making the launcher edges, otherwise raptum launching angles result. Demise of the filament 2 to 12, figure 210. Demise of the filament 2 to 13. Epta the splitter. One of those happy accidents occurred during the bonding of a Ceramis mosaic tile to the substrate with water glass. Water glass dries, evaporation, and it requires a path out to the air to do that. If you don't give it a path, it makes one. Between the two resios of ceramic AP intricate web of canals had been formed with dimensions of a fraction of 1/1000th of an inch. These tunnels were ORIP throughout their length to accommodate the IOS of water for drying. The space between the plates looked like a miniature two-dimensional termite nest. I did not notice the drying error until after I had tested the part and found it weird. I put AP EV into the input of Fethi guide. I got it late a dozen ochti. I had made a splitter for EVs. It was /immediately fat. This would do what it wanted to do with the double source device. A11, I had to do, was delay the path of one of the ochfuti with respect to a pother and collide them. In AP effort to make a neater structure to control the EVs and to improve on the mosaic technique, I tried grit-blasting guide grooves in alchmicium oxide, substrates through photo-developed elastic masks. I etched rutty patterns in fused QMC and did metashrin with vacuum evaporation. In the end, I returped to the mosaic because it had AP edge occur the others, virtue of being AL to do A11% of the functions I needed for laboratory work on one-off basis. I could even change a substrate that did not work oct because this time I was bonding down the chips of mosaic. Quick-setting a Roku glue, and they could E1 ifted off, heating to the softening point of the glue. No collision, no SIGA. Through all of these machinations I succeeded in constructing a test unit, similar to the one shown in figure 210, Sarala of launching two EVs at each other and performing a HND of scattering ecromept with the aim of determining the length of the vortex filament. DP additional mosaic guide component was added to accomplish the splitting function. The splitter is simply two pieces of dielectric material bonded to the substrate in such a way as to provide a Y-trait path and AP angle path. It is necessary to limit the width of the crack at the split, or A11 of the EV energy will follow this path. The trick in this experiment was to have the EVs from the split VR go through their respective mazes. Mass RD hit a target of either a phosphor or a simple witness plate, giving off light from the plasma plume. Demise of the filament 2 to 14. Everything seemed to work, but there was no answer. The two darned EVs seemed to pass in the night and rarely do anything else. No interaction. Several times as I dutifully tuned the time delay unit for coincidence, a very blind operation, I would see something like a deflection of one path, and it would usually be in the same place on the target as if a quantum effect were taking place. This experiment would win no cigar. I was constantly plagued by charging of the dielectric surfaces, and this may be what did me in. As much as I wanted this one to work, I gave up. It was time to skip a little, instead of hitting my head on the substrate. I'll let you in on a little secret. It never really occurred to me that the problem may have been that the EV length was so short that the probability for coincidence was just too low with the apparatus I was using. One thing that I did get out of this series of mistakes: a repeated observation that under certain conditions the visual trail of the EV would vanish, but the EV would still be there. There were many instances when the EV would go around part of the complicated circuits in a totally invisible fashion, and thus it eamed the title of Black Ev. I'll have a lot more to say about this later. Exploding and self-repairing emitters. Cathodes or EV sources that would not operate at constant voltage were a pain in the neck, and so I attacked this problem. I knew of liquid metal field ionization sources and had played with them a little on earlier projects. I remember having once had the power supply turned around backwards, making the liquid metal tip the negative electrode or cathode. This caused a monstrous blow-up at the cathode, not just once but many times. I must have halfway reasoned that there is a self-repairing process at work here. I set about trying the process in a way that, from where I am now, seems like the hard way. I put a titanium coating on a graphite tip I had made by mechanical process. The coating was reacted with the graphite by heating in vacuum and titanium carbide was formed. I knew this would allow aluminum to wet to it. A little aluminum was applied, and the composite reheated until, at about 600 degrees centigrade, the aluminum flowed on the surface. A negative voltage was applied to this cathode assembly while the aluminum was molten, and, lo and behold, EVs started showering off. I ran the thing for quite a while just to amuse myself. I needed something like this so much, and it felt so good that I was totally blown out for the rest of the day, and just took off for the Tall and Uncut, where I could be with Mother Nature, and thank her for this little gift. This modest success was followed by another and another. I made EV sources out of everything in sight. Demise of the filament 215. I used mercury opsora and silver. That worked great. I used alloys of gallium indium and alloys of tin lead, and they both worked well. I wrapped some conductive glasses such as Aurop oxide at 900 degrees centigrade to see how this glass worked. Just middling, but it worked. I tried organic material in the form of sodium iodide-doped glycerin, and that was okay. In all of this wild melee, I each-ep wrap nitroglycerin that was nitric acid doped for conductivity to Yi. If I could get AP entirely gaseous sultrus that did not onique a metallic deposit, it was fine. Vu, this time, I had a good grip on what the basic processes at work were, and I ventured fond to a fefferent class of yokocies that were not totally self-repairing as the liquid ones were, but they had some redeeming chalk. These were the metal hydride sources. Vu, spraying typitchum in the flame irawa with AP excess of hydrogen gas for combustion, I got a fair grade of titanium hydride that would adhere to a substrate, and that was conductive enough to use as a cathode. The Rosies also produced a very rough surface with Mapu field emission tips on it. These cathodes were not the greatest, but they had other interesting properties in that they released a lot of hydrogen gas at each Fiji PG that gave the EV a Realu nice cert. Doghouses. The battle to obtain stable evsocacies was drawing to a cloy, but Ope Thing had EEP noted op several of the Sorosy that were painted or sprayed op a ceramic substrate. These Yorsi seemed to work better when they were confined or closed op their top, a ceramis plate with a small cavity in it. This shap was AP outgrowth of the mosaic technology and had EEP used when I needed to isolate the plasma plume of the source from the Baru electrodes that required seal potentials. A11 that was needed to get the EV out of the doghouse, as it SMA KPOWP, weigh a very small groosh, perhaps 0.001 inch in diameter, cut into the lower surface of the ceramis sosha. Following this lead, I attempted putting emitters of whatever metal combinations were to used into ceramis NOS or E structures having an outlet hole of about 0.23 inches IP diameter. These nozzle Yolsi were really great after all of the variability I had EP living with. They would just sharp away A11 day long at 2 kilovolts and give out beautiful EVs without much plasma junk. Demise of the filament 2-1b. Mother EVs. Although I was still heavily into the question of how long the EV filaments were, I had a short interlude where I tried to answer some questions about why some of these EV shots broke my apparatus. There was a class of shot, usually running at 20 kilovolts or so, that had been responsible for ruining a digital voltmeter that was located 3 feet away from the vacuum system, and, at another time, had blown out a power supply and pulse generator that wasn't even hooked up to the experiment. I knew I was getting strong electromagnetic impulses, but this was a bit more than I was used to. Instead of starting down in the radio frequency spectrum to look for the trouble, for some reason, I went to the X-ray spectrum. I made up a little X-ray film pack holder, about 1/4 by 3/8 inches, that could be put in the path of an EV so as to catch the EV on the front, and, in the back, expose the film that had been separated by various filters. The film was Kodak NMB1, a single-sided X-ray film. The witness plate, or first plate in the pack, was 0.001 titanium, so that I could verify the presence of an EV in a standard way. The second plate was an optical radiation filter of aluminum, to stop any thermal spectrum coming from the back of the titanium. The X-ray film was the next layer. The film pack was exposed with an EV and then developed and checked for radiation indications. There was one black spot right where the EV had hit the titanium. So there are X-rays. I ran the same scheme again, except that this time I upped the ante on the filtering to a 0.803 molybdenum EV target and a 0.33 lead filter placed before the film. Same result. One black spot where the EV had struck. So there really are X-rays around here. One more try, this time for serious stuff. I set up the scintillation detector and energy dispersive analyzer and calibrated it with americium-241 at 59 kilovolts and cesium-137 at 662 kilovolts. A 3/4 inch thick piece of brass cut the cesium-137 count from 804 to 459. The scintillator was then placed outside the 1/4 inch bell jar at a spacing of 4 inches from the EV source. When the EV source was fired up at about 20 kilovolts and was running in the sharp mode where one could almost feel something happening, and indeed there was a different acoustical ring to the shots, the scope showed huge peaks from the scintillator output, even with the 3/4 inch brass plate interposed between the source and the detector. There was some electromagnetic pickup leaking into the detector, but when this was shielded out, the signal from the EV gamma output was still there. Demise of the filament 217. A rough calibration, based upon absorption, yielded 200 kilovolts energies for this mode of operation. Changing only slightly the properties of the EV target made the high-energy photons go away. Later, we would find out a lot more about the inductance effects of this process, but for the immediate future, I backed away from the hard stuff and rarely operated above 2 kilovolts. We sure enough had X-rays. Still no collision. After this brief reprieve at doing some X-ray work, I went back to the question of the length of a vortex filament. Having had my thinking shaken up by the mere passage of time, I was now disposed to using another collisional approach to the problem. I would try to work out a method of cross-streaming or counter-streaming the EVs to see at least something happen when EVs encounter each other. It is a long and sad tale of how I struggled trying to make these little buggers run into each other, but to no avail. Mostly I required high aiming accuracy in all of the experiments I planned, and surface charge effects defeated this. I was just too far out in the woods. On this last trip through the woods, I was able to pick up a couple of interesting tidbits that I could carry on with me. I had worked the mercury-wetted copper cathode down to 1.2 kilovolts when operated in conjunction with 0.006-inch thick dielectric substrates. This greatly helped instrumentation that had been plagued with stray electromagnetic pickup. Fission fusion. A most stunning observation was made while working on a splitter that was part of the counter-streaming EV apparatus. An EV source had been set up on a glass surface and fired at a distant anode that had another glass plate covering a part of the region between the source and the target. This glass plate was a standard microscope slide, as was the base plate, and was spaced only a few microns above the base glass, as indicated by the interference fringe pattern between the plates. When the EV was fired and encountered the first edge of the cover glass, it spread out in a pattern over 1/4 inch wide and penetrated under the top glass as a group of relatively straight and independent EV paths. This is amazing enough, but when these multiple paths reached the far side of the cover glass plate, they united into one EV again and went their way to the anode as if nothing had impeded them. Demise of the filament 2 to 18. Think a octet. Near is a bunch of little critters of not more than a few misrops in size, tunneling through a vast expanse of space, more than 5,000 times their characteristic size, and still to communicate to their most distant parts that it is time to emerge and then unite on the far side of the tuple. Pretty good, for a thing that is not supposed to be smart. What I had seen here was more than a simple message. At least one phrase of the message was that these things would watching each other, and the walls, and a lot more things than I had initially thought. They WSRE watching with electromagnetic eyes, and seeing more than I had seen up to this point. You can bet would watching them more safulu from here, op. The ring cycle, and watch I did. I set up a series of witness plate experiments to get better statistics op what I was 1 UNPG at. I would fire various sources into VMIS witness plates up to various spacings and voltages. This is one of those dumb modes where it does not row to think, just do. I was finally rewarded with a freak shot that showed 2 small rings instead of the usual splash, although there were plenty of splashes erupted too. Figure 2.4 shows these rings. Magnified views of the rings are shown in Figure 2.11 and 2L2. T background material, within the centre of the rings, has not been disturbed much. AP interesting clue as to the shape of what stretched the surface. Why there were only 2 of these things is beyond me, but thank goodness for them. I think this was mu break. I should see a long quest coming to a close. Demise of the filament 2 to 19. Figure 2.11. Figure 2.12. Demise of the filament 2 to 20. It was time to get very serious POW about this length problem. I was sure that if Sockled set up a Y-tream of vortex filaments from the source and electrically sweep them across the target, I could surely cause them to show some streak effect that would indicate theat length. To accomplish this, I used AP-EV source that shot a Crocea Tejan of glass, coated with high-resistance material to control the charging. A deflector scheme was worked out to couple part of the rapidly falling voltage of the SU.CE, which oscilled when the EV was initiated, to the resistive regiop the EV had to traverse. The witness plate at the end of the RUP was spaced a small distance from the plate the EV wrap on, and in this case it was made from film of alumipum on glass. After the EV Sori was fired one time, the witness plate was taken to the optical microscope and examined. The rate was interesting but not sherry slierlu resolved. I do not hache a sherry good optical microscope. The sample was sarried to the SEM, and it was clear why the optical image was not easy to figure out. Most of the shea struck, the EV was blown away, and the aluminum that left with the micro-explosion carried some glass with it. Demise of the filament 2 to 21. Figure 13. Demise of the filament 2 to 22. Figure 2.13 and 2.14 show what I saw. A little bit of a may, but basically I was on the right track. The top centre portion of Figure 2.13 has several /mmks that are in the 1 micrometer range that were not energetic enough to destroy the surface. Figure 2.14 has some beautiful decoration op the substrate, possibly stemming from the Rescher wave pattern of the explosion. On target. Next, rearshed yom targets, witness plates, from a fairly heavy evaporation of chromium sarop op glass. The notion here was to provide a material fat would rather sublime than melt. This should improve the resolution of the witness mark, because most of the resolution had been lost through melting effects. A 5 kV shot was fired, the target examined in the SEM, and the vortex filament theory was dead forever. Long one-eye of the bead. There was po length to the charge structure at all, save that of its own diameter. The basic sarig of the chargeway a bead, OP misrometer in diameter, and the beads formed chains. These chains would hit a surface square on without rotation, translation, or skewing. Figures 3.1 through 3b, in the next chapter, show what these beasties Raelu look like. They are not more PPG glories. They she not cortec filaments, they mao knotty vortical at A11. At this point I imagined they were microscopic packages of raw charge having the density of solid, possibly being held together, UAP unseen container of radiation stemming from the chasukum, that exalted reptum of energy we might hop somehow to tap. Demise of the filament 2 to 23. Chapter 3 tooling up again. It was December 27, or 981, when the bead data came in. Although it was 2 days late, it was ope of the best Christmas recipe I could hache asked for. Such little gains in data grief intensify mu urge to go on, but I have learnt. They also provide me with a great deal of guidance about how to all rep up other routes. I am sure I spent some time reflecting on the routes we had abandoned, as well as some that had not quite EEP started, but none of this was in mu notes. Everything was out the beads. A look at beads and chains. In addition to showing that the EVs were beads in a chain instead of a filament structure, the photographs clarified some of their other properties. The chains always hit flat on the witness plate. APD ellipticity in circum chains was largely d-chi to the 45-degree viewing angle in the SMM. These chains are to be spaced through time, and they would most likely be found as a stream of chains in Chasham flight, one behind the other. There was also a similitude of chain diameters in any one particular shot. The beads were somewhat quantized in size, although a few detached beads could have found that were apparently smaller in size. Stray beads were HSHD to find. They were mostly grouped within the available rings. Chains up Ra. The most string characteristic of the bead chain was its impossibly complicated tangle that somehow knew how to straighten itself oct. The photographs in Figure 3, 1 through 3.6, show a shot that had been given a vacuum jump of about 1 millimeter between the launching glass surface and the witness plate. This Chasham jump allowed the chain to begin to up Ra from its previously tangled state. Figure 3, 1, Figure 3, 2. Tooling up again 3 to 2. This appears to be an analogue of the familiar pull chain for a light, or the old bead chain on the plug for the bathroom tub. Such a bead chain would tangle when thrown across the floor, but would unerringly straighten out when picked up. I do not mean to imply that there is an actual untwisting occurring, but rather that the nodes of a complex pattern are somehow moving. Many amulets, the pendants that hang off the chain, as seen clearly in Figures 3, 2 and 3.6, worn by the EV chain are still unwrapped in Figures 3, 1 through 3.6. But the chain is many orders of magnitude more pristine than the one shown in Figure 3.7, although the latter is also an EV chain. Sweep indications. The heavy concentration of EV strikes in the center of Figure 3. One produced so much strain in the witness plate film that it was cracked and detached from the substrate. It was the intent of this experiment to sweep the group of chains along the substrate by applying a deflection voltage to the region between the EV source and the witness plate. In the photo in Figure 3, the sweep was supposed to be from right to left. It appears that something like that happened. Figure 3. 2 is a continuation of the sweep and was found immediately to the left of Figure 3. 1, presumably the nose or front end of the EV train, arrived in Figure 3.1, and the tail end of the shot came along in Figure 3.2. As is usual for the kind of strike shown, there is a quantity of molten material scattered around the surface. There is a fair correspondence between the amount of molten material found and the destruction on the surface. In some configurations, it is possible for cathode material to be carried over to the anode witness plate. Few wandering beads. Figure 3, 2 shows several interesting things. The strike immediately at the end of the crack in the film shows many radial marks that are, more than likely, unopened portions of a chain. The center is well developed into a circle. Allowance must be made here for the 45-degree viewing angle of the SEM that tends to produce an elliptical appearance for perfect circles. The circle immediately to the left of the crack end shows a very nice circle. But 4. Tooling up again 3 to 3. Figure 3, 3. Figure 3, 4. Tooling up again 3 to 4. Some reason a disordered group of beads extends downward from the circle. Higher magnification shows that this group is attached to the circle. This same circle shows a few disconnected beads in the center of the circle, but none are to be found outside of the circle. This is very common for a highly ordered EV shot such as this. Randomly placed beads are rarely found. High surface energy gradient. Near the center of Figure 3, 2, there is a small circle of beads that is shown magnified in Figure 3, 3. One of the interesting details of this photo is the clear region that exists between the beads. There is not enough energy available to even lightly disturb the surface. Again, there are 2 beads in the center of the circle that are seemingly detached from the rest. In this photo, there is an opportunity to assess the size of the beads that were presumably made under similar conditions. I have been telling myself that there is some force tending to make beads having a diameter of 1 micrometer. This is not strictly so, as can be seen in Figure 3.3. There is a tendency to average around 1 micrometer in diameter, but a lot of vagaries exist. Figure 3.4 is a magnified view of the top center bead shown in Figure 3.3. The thermal process that produced the crater has seemingly destroyed any detail the EV may have had. All that results is some pressure wave pattern or flow pattern for the film material. Handbook data on chromium states that a pressure of at least 10 atmospheres would be required to produce the effects of melting shown in the photo. All that can be said for sure is that there is a very high energy gradient at the surface. Tooling up again 3 to 5. Figure 3 5. Figure 3 6. Tooling up again 3 to 6. Figure 3. 5 is an ecameral of another intermediate stage of opening where the amulets hanging onto the main structure are fairly complex. Perhaps, Yulun at this intermediate state, someone can figure out what the aschol roses is that is forming this shape. A few beads are shown within FE circle, and some very heavy metal splashes are shown, coming from somewhere near the top right of the photo. Figure 3. B shows a more fully developed chain opening. Notice in this photo how the background is clear of damage and how the free beads are located entirely within the circle. Figure 3. 7. Figure 3. 7. Also APF chain is a 1500 Kate DM-keeled optical microscope image of APF shot that was caught pair the launching glass plate APD had a very short chasucum flight. Possibly this is how messed up APF chain gets when it is being dragged along a surface. There are literally hundreds of beads in this chain, and they she hanging onto their order for life while being beat up the surface, ionizing gas, and screaming along at 1/10 the velocity of light. The binding epigu of the beads apparently exceeds that of the material they are beating up at the surface. In the lower left sauper of Figure 3, there is also an effant tangle of beads that failed to straighten out as much as the others in the same photo. This tangle was put up in a previous shot as a marker of where the next shot having the vacuum flight was supposed to begin. Tooling up again 3 to 7. Figure 3 8. Figure 3 9. Tooling up again 3 to 8. Yazuum Rs on surface. Figure 3 8 and Figure 3 9 are video Samera photographs of a typical vacuum arc running across a surface. The surface is prepared coating 2 ceramic plates with a 1000 ohms square resistor material in the region shown in black. This coated region on each plate is about 1 inch long. On the top and bottom of the coated region, a silver 1 hour is also fired onto the ceramic adjacent to the resistor material, and these terminals serve as cathode and anode for the test. The 2 plates are separated a vacuum gap of 0.01 inches, thus causing the discharge to jump across the gap to the other plate. The entire apparatus is operated in chasuum, and a direct surrept voltage is applied to the electrodes with a suitable series resistor and raised until, at Abel art 10 kilovolts, a spark is initiated. A VMI of things can be seen in the Mapu video frames beyond. Almost always, the discharge comes from the silver electrodes and Reshlu from the resistor material, although occasionally field emission can be seen at the edge of the resistor at the gap. This is shown as a small light spot in Figure 3 8, just to the left of center, at the chasuum gap. The width of the optical image is much larger than the damage mark left on the surface. A discussion of this damage effect follows. Varying the resistance of the coating, it has been found that the relatively small EVs used here are to rub op surfaces as low as 200 ohms rea scumtra, but no lower. Below this value, the EV is destroyed much as it would on a metal surface. Even when resistor-coated surfaces are used, the EV will not rub in a straight or predictable path, and so it is assumed that something other than the charge op, the surface, is controlling the path. Often an imperfection can be seen blowing up just as the EV takes a turn. It is hard to make surface free enough of imperfections to entirely eliminate this effect. It is Mu contention that an EV group starts at the cathode, runs across the surface of the dielectric or resistor material, jumps the chasuum gap, and proceeds op to the anode across more resistor material. This is a trulu virtuoso reformaps for such a little fellow. Tooling up again 3 to 9. Figure 3 10. Figure 3 11. Tooling up again 3 to 10. Hopping EVs. Figure 3 10 and Figure 3 11 show a SEM shot of the trail that was left behind when an EV ran across a surface. A surface of glass was very lightly coated with aluminum by thermal evaporation, and a negative voltage was applied so as to repel the EV. I had learned that this negative voltage gradient was bad news for EVs and would destroy their order if propelled against the field in a particular way. What you are seeing is a group of EV chains bouncing along the surface, biting out small hunks, breaking themselves up, and then, at times, fusing back into larger entities. One interesting characteristic of this action is the almost equidistant nature of the jumps. Big boulders jump a long way, small rocks don't jump so far. This skipping and hopping gives a clue as to what the damping forces are. It is not entirely obvious from the photograph that the EV is really hopping off the surface. What shows is just regions of non-destruction, and this could be caused by something else. I am getting ahead of myself slightly, but I will tell you now that an EV can be gently lifted from a surface and will fly along at any desired height without touching a thing. That is why I say they are jumping in the photograph. There is more discussion of this later. No field, free regions. Now might be a good time to pause from our technical flight and consider some of what was going on with my thinking at this time. I had a fair background in reasonably standard gaseous discharge and particle optics work, and all of that now seemed wrong. This bothered me a lot because such massive bodies of information are not wrong very often, give or take a few witch hunts and inquisitions. At this point, I had tried mightily and would try some more to put EVI-like things through standard electron lenses, quadrupole containers, and spiropole filters. They just would not go. I felt like I was a little boy again, trying to stuff our big old yellow tomcat through the small hole in our underground cistern. It just could not be done. I could not get the EV past a single aperture in a particle optics system. Had I lost my mind or something? Were these things massless? What happened to the inertia that is supposed to carry them along in a field-free region? Aha! There are no field-free regions around an EV. This intense, moving charge entity works electrodes over so thoroughly, coupling to everything, that the voltages I put on them, tooling up again 3 to 11, are almost inconsequential. It looks like all the old rules mow okay, but I would have to mosh the goalpost a little to accommodate this new KD on the block. This new HD is the proverbial 800-pound gorilla, and he is going to do pretty much what he wants to do. The scientific reader is Roalu, wondering how new what the total charge and charge density was. I certainly hash not given any measurements thus far that would tip that fact. Please, be patient a little longer. I will get to that. Mainstream considerations. There was another matter that kept me awake a 1-0, and that was how to fit this newfound EV data into all of the standard Rs, Yurshk, and glow discharge work. The new data, or at least Mo interpretation of it, seemed very much at variance with most mainstream considerations. Worst yet, suppose they were right with all of those leader, streamer, returp, surrep sheath arguments, and that there were Ryulu no EVs at all, but just some form of continuous flow process that miraculously necked down at the Y-virus plate to deposit its energy. Okay, if that is so, I would ike this Rosus and work with it too. Seriously, at one point in this pict, I could take any 50 VO of the data I had, and with it, I could not roche or disprove the streamer notions. We hired consultants, and we argued mightily among ourselves as to where the true coals of requisite 1 AU, but in the end, the Gidmer say, same from the gentle hands of Bill and Hal, who said something like, "Come up down the path, it's better ochre here." I might have terped back had it not been for this help. If someone had just seriously suggested Arve make a whiz-bang she, sell it as a mopo rumour, that would have eeped the end of the UPO to Eve LAPD. We were very delicately balanced. What can I make them do? Enough of the psychological worries that went up during this time. Let's go back to the technical considerations. This second Paciot tooling up was going to emphasise seeing the electrical properties of the EVs, instead of just creating them. Of course, fair would some sideways motion that wackled sopsegbed with generating and divecting them in different ways. This sideways exploration is inevitable with me, but is a good thing to do apuao at shu, a primitive state in a piect. Tooling up again 3 to 12. I could take the view that Thomson must have taken when he discovered the electron. To heck with what it's made of. Let's see what we can do to it. The instruments in this phase of work would have the characteristic of analysing the actions of the EV under different conditions, with the aim of eventually controlling all of its actions. There were some large hurdles to overcome at this point, because I had not been able to put an EV through an aperture into a field-free analysis region, one of the most fundamental requirements for conventional particle analysis. I could handle them somewhat on surfaces and guides, but the confinement was so tight, there was no way for weak external measuring forces to sample their properties in the presence of this containment noise. I was destined to try a lot of silly-looking things in an attempt to inject EVs into a measuring region. Lossy mirrors. The first of these schemes for injection was based upon using highly dissipative materials for the particle optical elements. I'm not really sure where the idea came from, but I already had the notion of how an EV travelled on a resistively coated dielectric surface. I imagined the surface to appear positive to the EV and that it would be attracted to such a region just ahead of it. As soon as the EV reached this positive point, it would effectively neutralize the point with its negative charge, and the positive-looking point would move ahead to further induce the EV to go that way. I am sure this scheme does not really hold water, but I built a lens structure out of graphite and shot an EV through it. It wasn't much of a success because the hole had to be much larger than I wanted, and the EV struck the graphite lens element on the back side, but it was better than I had been doing. I tried to plot the trajectory of the EV behind the lens in a kind of left-handed fashion by using witness plates at various spacings and voltages behind the lens element. I could collect the EV on the witness plate under certain conditions, but for the most part, the system was acting like a very divergent mirror. It looked like the EV was inducing large negative fields on the electrodes and then responding to this field, just like the book says. Dissipative structures helped some, but did not leave me with a good feeling. I dumped the effort, tooling up again 3 to 13, figure 3, 12, tooling up again 3 to 14. Gas guns. In AP entirely different arrowish to injecting EVs into a Yaskum region for measurement, I built a gas triode similar IU the one shown in figure 312. The entire apparatus Y operated in a Chasium chamber pumped, UAP oil diffusion, reach mate. The EV Yorsway operated at a sufficiently low hydrogen gas ratio, Rarehas 1, 0 to 2 torr, that their way Po gas discharge WEP several hlovol B were applied to the cathode. At slightly higher voltage, the cathode would fire off an EV, and with a positive voltage applied to a POD second, operating in pair Chasham due to the Acher plate and differential pumping, the EV would strike phase center of that anode. Tooling up again 3 to 15. Figure 3, 13. Figure 3, 14. Tooling up again 3 to 16. Figure 3, 13 shows an SEM photo of the removable witness plate that served as an anode, and figure 3, 14 is a magnified view of the center region. These look like standard strike marks that can be obtained by almost any method. Considering that the anode was over 1 inch away from the source, and that the entire shot group, usually fired one at a time, was only about 200 micrometers in diameter, I was surprised by the consistency of such a random-looking process. The pressure adjustment was very critical, and this was not the kind of beast I wanted to incorporate into a complex system of measurements. Why did I do it? I don't know. Maybe I just wanted to get one of these things through a hole under any conditions. As they say, onward, through the fog. Storage. There was one very interesting effect that showed up with a slight modification of the apparatus, figure 3, 12, when a noda 2 was changed from a plate to a wire about 1/64 inch in diameter, and the signal voltage on this wire was fed to an oscilloscope. There was an alternating current signal hanging around for nearly 100 microseconds after the EV pulse was terminated. It could have been just the usual gas vagaries, or it could have been an EV orbiting the wire in wildly different orbits. This is a known stable mode for a short time for both electrons and ions. I really didn't think of this while I was doing the work, and I couldn't afford the time to go back and check. Coaxial diodes. It seemed to be time for another one of my digressions into EV formation, with the intent of getting more specific about the energy needed to form them. I set up a coaxial structure similar to the one shown in figure 3, 15, with the center electrode movable between a charging electrode and the discharging electrode. Both surfaces in the discharge region are removable hemispheres that could be highly polished before discharge and put into the SEM for examination after discharge. The line impedance was about 50 ohms, and both a 5-inch and a 1-inch line length were used at various voltages to form the EVs. The discharge is obtained by first moving the line center conductor to the charge position and then carefully moving the two hemispheres together until the spacing is small enough for breakdown to occur. Figure 3, 16, and Figure 3, 17 are photographs of some of the shots taken on titanium electrodes. Tooling up again 317. Coaxial line EV generator. Figure 315. Tooling up again 3 to 18. Figure 316. Figure 317. Tooling up again 3 to 19. EV gas diode. Figure 318. Tooling up again 3 to 20. The most obvious patterns in the photos are the concentric rings with a really wiped out center. The energy in the center is so high that all EV data is wiped out by melting. In the circles just outside of the melted region, there are many of the morning glory patterns showing. In fact, there are far too many patterns showing for me to assess anything about the energy for EV formation, even at the lowest voltage used, 1 kilovolt. It was found that the concentric patterns are due to the curvature of the surfaces and are undoubtedly related to the pressure waves of vapor coming from the electrodes. This is just another ill-fated experiment when it comes to gathering significant EV data. All of these little bits and pieces of the puzzle, although not strictly related to the problem I was working on at the time, were adding up to become significant tools. An example of this follows. Enter the black EV. While working on the gas triode shown in figure 312, many unanswered questions had come up, but the EV source itself was an interesting one. In order to investigate some of the properties of gas sources, an EV gas diode source was fabricated similar to the one shown in figure 318. The nozzle had a 0.004-inch diameter hole in the tip end and a copper wire in the large 1/32-inch diameter end. Hydrogen gas was fed into the nozzle by using porous ceramic between the feed line and the nozzle. The feed line was grounded and acted like an anode, but the porous ceramic prevented direct bombardment of the anode. The entire structure was operated in an oil, diffusion-pumped vacuum system. At this point in the project, I introduced a real pulse generator instead of my old faithful mechanical vacuum switch. I didn't get too fancy, mind you. I used an old capacitor discharge ignition system out of a car. The pulse was pretty awful, 80 microseconds or so in duration, but it stopped direct current glow discharge when working with low-pressure gas, and that was the main reason for going to a pulsed voltage. In use, the tip of this gas EV source was made to touch a substrate at a very acute angle aimed in the desired direction for propagation of the EV. One thing noted immediately was that this source launched black EVs. Tooling up again 3 to 21. Whatever came out of the nozzle was not optically visible, unlike the usual case, and the EVS would travel a long way compared to the vacuum case. Apparently running in a low gas pressure was much less lossy or interactive than even the vacuum case. In the triode device, figure 312, this was also the case, as an EV was never seen in the region having a low hydrogen gas pressure. Witness plates were used to verify the existence of EVs, and every shot was the real MC coil. In designing this type of source, I imagined that I could simply stick it into any apparatus that had adequate pumping speed to produce the desired level of vacuum, and the injection problems would be over. Not quite. I just moved the problem back one aperture. An unusual breakdown mode. Life with the EV was a tumultuous experience. None of the good old rules worked. Once in a while, something really off the wall showed me what I was up against. In one experiment with the gas diode EV source, I had occasion to use a small formvar-insulated wire as the second anode to collect EVs. The wire size was perhaps 1/64-inch diameter and insulated with heavy formvar. I do not usually use formvar in vacuum, but I was in a hurry to do something and grabbed it. When the EV was fired at the wire with only low voltages applied to it, nothing especially interesting happened. At a very critical threshold of 4.8 kilovolts applied to the wire, all hell broke loose. At every EV firing, there were showers of sparks from all along the formvar-coated portions of the wire. The regions that had been stripped were unaffected. The formvar was being exploded from the wire, and later examination of the wire under the microscope showed highly disrupted regions that had been torn off. Wow! I have spent a lot of time tinkering with field emission processes and have seen such blow-ups often, but always with direct current applied to the electrodes. This one did not figure, so I went back to test the wire under the same conditions at high voltage direct current, but without the EV present. I put both plus and minus 30 kilovolts on the wire, all my feed-through would allow, and nothing happened. I gave up on the mystery at that time, but I have since concocted a couple of theories. One of these theories is that the charge dumped on the line raised the field of the wire surface so rapidly that the surface of the insulation, in spite of the high dielectric constant, lagged behind and appeared positive enough to promote field emission from the wire cathode. Another similar theory is that the intensity of the wave travelling on the wire was high enough to promote field emission and breakdown in the longitudinal direction, somehow invoking the dielectric as a waveguide boundary. Whatever the cause was, this was an intense process at work, and is an example of everyday life with the EV. At the very least, another small tool has been added to the box. Tooling up again 3 to 22. Some black EV laws. What oct those observations op black EVs? Soschled a little lighty shed up this. It looks important. Is it just lack of visual radiation, or does it include all frequencies? A low-loss rosy is always interesting. To get at these questions, and more, AP experiment was yet CR having a gas gradient away from a surface. Ryle at the same time, causing an EY to ilachshed in Telare highest Resha region of the gas. Tooling up Ag 83 to 23, gas Eve dog. Tooling up again, 324. Figure 3, 19, shows a sketch of the layout used. The gas is introduced into a block of porous ceramic that has been covered everywhere with a non-porous glaze, except for a tiny cratch in the bottom of the groove. A resistive glaze is used in the bottom of the groove to help dispel charge. The gas soams out of this groove and is pumped away, UTB chasuum system, thus giving a pressure gradient. The EV source was a mercury-wetted Sorrow wire that lay in the bottom of the grush and used the counter electrode as AP anode, operating at ground potential. A negative voltage pulse of about 2 kilovolts is usually applied to the cathode when the emitter is SHA. Otherwise, a higher voltage must be used. This little gadget just described was operated up to the view of a microscope, and some interesting details could be seen. If the unit was pulsed without any gas in IB channel, and with a collector electrode at a large distance for the voltage applied, there would be no EV formation. This is a condition we have called flaring. Under such conditions, OPLU plasma room is created at the cathode and no EVs are formed. I had so respectful of the EV that I had created a mystical phrase saying if you don't give them a raise to go, they won't start. This personification is not entirely without merit, because it will be shown later that there are advanced electromagnetic messengers sent out from the source to determine if E environment is sorest for formation and propagation. Evolog has a lot of new rules. When the anode is Soreslu positioned and the gas pressure is off, the path of the EV is fairly short and definitely tortured, as evidenced the large amut OI TLG 111 given off from surface interaction. As the gas ratio is raised, the light from surface interaction dims out, and the distance the EV will travel to the anode increases greatly. Under the microscope, its sap, seep that the EV has been raised are the chauffeurs. The lifting is most evident on rough surfaces, where the tops of protruding ceramis bits are at Akilby, the passing EV. DS the gas pressure is raised further. The EV is lifted above the protruding obstacles. This is rather amazing process to watch, but it is absolutely dependable, as if E surface had been greased with a magic substance. I had EEP accustomed to using highly polished surfaces for EV guides. Ut Eshep, the roughest surface had low loss with gas. In addition, EVEP, the customary fluorescence from the surface, was absent with gas. This was indeed a high degree of isolation, and the EV path is very black. I have not accurately measured the gas pressure. It was below the value that would promote a direct current glow dishmar between anode and cathode when several hovolts were applied. DP estimate would be in the 10 to 2 to 10 to 3 tor rapate. A pother interesting new toolas, EEP added, and although it does not entirely explain the EHA of the more somlek gas triode described earlier, it helps. Tooling up again 3 to 25. Back to wideband scope design. It was clearer to me, as time went on, that the need for a fast oscilloscope was just great now, as it was in the very beginning. In fact, I had done myself a great disservice. You ploughing on blindly when assessment of rapidly varying fields would have possibly solved Mapu of my Rollums. This was clearly one of those hinge points in a project where correct decision will go a long way, and it behooves OPE to regard Chefschlu all moves at this time. I needed an oscilloscope with a bandwidth of Reha's 100 GHz and a sensibility of ARU PD 50 volts. I could forego input attenuator switching and highly adjustable timing for sweeps. I was certain that with the implied bandwidth, I would not be able to carry the signals very far op cables, and so the scope would have a small chip structure located close to the experiment. When these and other considerations were factored into the decision of whether or not to start a major IPST-Gumept program, I have to admit it looked like a real fight was in IE offing. Should I go arupt this one or hit it head-on? Bootstrapping. I was beginning to use the tools I had assimilated on this PECT and arrow them, each in half-finished form. A bootstrap operation was in effect, and EV techniques were beginning to reveal answers about new EY questions. This had, essem necessary, a source of the increasing gap between the use of conventional techniques and the emerging EV technology. As AP cameral of this friend, the cathode for the scope was going to be a special adaptation of one of the EV sources because it had higher brightness than anything I had ever seen before. There were other Rollums, but perhaps they could be handled within the tolerant OSHI PDs needed for the scope cathode. EVs were loon like RETF good things. APD I was confident I could make good use of them. The result. As with all oscilloscopes, there was a need to synchronize several signals without jitter, destroying the time resolution of the instrument. What this would mean in EV technology is that OPE-EV must trigger the generation of another, without jitter. I did not know the details of the formation process, and so a little test way in order to determine some of the birth ratios. To do this, I set a test whereby AP-EV TM gate was connected to the cathode of another EV generator. A bias voltage way applied to the second EV generator YO as to test the operating point of the field emission process connected with EV generation. In operation, this bias voltage was set to some value and the primary EV pulse fired. Then the tooling up again 3 to 2B. Second cathode, or EV source, was tested with a witness plate to see if an EV had been fired from it. This primitive device was a pretty ragged reformer, but it was finally developed into the picopulsar, or EV pulse generator, and into the field emission EV sources that are described in the chapter on components and devices. Thick film work. As is usual in backing off to make a special piece of apparatus, I also had to keep backing up into the Konstruktiop technologies. This time I needed a high-temperature equivalent of the submersial thick film screening process for firing ratups of materials onto ceramic substrates for producing conductors, dielectrics, and resistors. In order to avoid Mapu of the known limitations of conventional thick film processing, I elected to develop a chasume firing process. A chasume purpose was built thoroughly of firing a L-inch substrate to ochre 1800 degrees centigrade for maturing the various concoctions applied to it. Within a short time, I had brewed up the materials needed. Conductors were MASF molybdenum with a pinch of aluminosilicate glass for binder. Dielectrics were aluminosilicate glasses, and resistors were aluminosilicate glasses with a pinch of tenia reduced during the chasume firing. I could use this combination of materials, along with the mosaic technique, to fabricate almost anything I needed for the scope peaked. Once in while the surfaces were too rough and I had to polish them or use AP evaporated coating to do the job. Cathode with steings attached. The cathode for the scope tugged out to EAP-EV source of the mercury-wetted Sora type followed you another aperture to isolate the plasma and define the emission angle more asheritelu. This design flies in the face of conventional design. It used ceramic in regions of Elstrop flow that Opomalu held sacred for metals only. There was no Chemjing Rollum, and so I did it. Charge was taken care of, as if you magic. The average emission spectrum was measured you projecting the emission image onto Flalcorecept screen through a deflector-type epigu analyzer. It was horrible. I didn't worry about that. I only wanted the emission to have good spot shape and low energy spread during a short period of time, and I could provide for that with a fast gate. The emission was too bright for the phosphor screen, and so I put in another aperture, in IE form of pinhole, to help clean-er the image. I was out to make an important discovery. Tooling up again 3 to 27. Even though I had threatened to make a pinhole electron camera over a year ago, and had even bought the channel plate electron multiplier for it, fate had kept me from putting the entire apparatus together. I had initially wanted it to look at black EVs and see if there was anything in the way of electrons coming off of them. I expected there would be, but there were other things to do. In effect, I had now made a crude electron pinhole camera and was looking at an electron source that had an EV for its origin. I puzzled over what I saw because it looked like there were stringy things coming from the source and not the smooth emission I had expected. Something was amiss. This was one of those wild moments I live for. There was a new animal in the woods. I was looking at it, and it was looking at me. What to do? Now here was a tool and a half. With this, in cleaned-up form, I was going to be able to bring down a mighty blow upon something. The cathode work was folded up in a neat package and put away, with many thanks for this introduction to a whole new world. I was off to make a better electron camera and see what this stringy new stuff was. The pinhole camera. A pinhole camera was thrown together according to the drawings shown in Figure 3.20 and the photos shown in Figure 3.21 and 3.22. This is an extremely simple device, as scientific instruments go, and it has performed admirably from the beginning. What is not shown on the drawing is the arrangement of the power supplies that allows nearly any voltage to be applied to nearly anything. A bunch of unregulated and isolated power supplies were used. These power supplies had reversible output polarity and could be stacked in almost any imaginable arrangement. With this power supply system, the voltage on the phosphor screen could be maintained at 5 kilovolts relative to the output of the channel electron multiplier, while the multiplier gain could be varied with another supply. The input voltage to the CEM could be varied and either polarity used relative to the case and shield. This gives the effect of a retarding potential energy analyzer. The deflectors, used for energy analysis, can have any reasonable voltage applied to them relative to the case, and the entire case and shield can be set at any potential or polarity up to about 5 kilovolts. This latter function is used to act as an extractor from the source of particles to the camera nose. Tooling up again 3 to 28. Figure 3.20. Tooling up again 3 to 29. Figure 3.21. Figure 3.22. Tooling up again 3 to 30. The camera had a pneumatic manipulator hooked up to it, so that 3-axis motion could be obtained with limits of travel of about 1 z-inch for the y and z axis. A travel of 0.1 inch was provided for the kh axis motion. The magnification was set, U moving the z-axis of the camera with the manipulator. Nogmalu, the magnification was RUP at about 5, with spacing of UA inch from the target to the nose of the pinhole camera. The field of view was determined U using the KH and Y manipulators. The light output of the SEM was monitored UA TV camera, and dye was recorded on a videocassette recorder. At times, the VSR also had oscilloscope waveforms mixed into it via another camera watching the scope. This system was very versatile, and a godsend when used to waft the antics of EVs at play, especially during the time when they Pecha seemed to do anything the same way twice. But then, that is getting ahead of Oka's story. The EY is caught. On September 17, 1982, the mystery of the stringy things coming out of our emission sources was over. The pinhole camera was aimed head-on at a diode source, like the one shown in Figure 3.18, and some of the MAPU images recorded on the VCR Oka, a period of time, are shown in Figures 3.23 through 3.30. The image is a time-averaged photo taken of single firing of the sockets. The streaks seen coming into the camera are enlarged at the end due to a close approach to the pinhole camera and the resultant increase in magnification. Tooling up again, 3 to 31, Figure 3.23, Figure 3.24. Tooling up again 3 to 32. We were seeing electrons emitted by an EV that was in the process of shedding electrons and dying, much as if it was a burning ember giving off light as it died. The center region of Figure 3.23. is the source of the EV coming almost straight into the camera. Figure 3.24 shows a shot that is moving at a downward angle. To verify that the image was indeed produced by electrons, a crude energy analysis was performed by applying a direct current voltage to the deflection plates of the camera, so that charged particles were swept sideways according to their velocity, charge, and mass. An example of this kind of analysis is shown in Figure 3.25. Tooling up again, 3 to 33, Figure 3.25, Figure 3.26. Tooling up again, 3 to 34. In this photo, Figure 3.25, the source has been moved to the right side of the screen to allow more room for the tail of the energy distribution to show. A very complex pattern can result from this kind of analysis, and for a true energy analysis, it is necessary to know that the EV is coming straight at the camera. This can never be known for sure with this simple setup, and so it has limited value. One can be relatively certain that the image in Figure 3.25 is produced by electrons having a wide energy distribution. An improvement can be made on the energy analysis by using the retarding potential method to chop the tail of the electron distribution. In the photo of Figure 3.26, the low-energy electrons have been removed by applying a retarding voltage to the input of the channel electron multiplier. Tooling up again 3 to 35, Figure 3.27, Figure 3.28. Tooling up again 3 to 36, Figures 3.27 and 3.2008, are examples of the absurd antics of some EVs. There is a foggy background image of a previous shot showing on these photos, and it is caused by using a pulse firing rate that is higher than the recovery time of the TV camera. Aside from the aforementioned problem, it can be seen that the EV is capable of undergoing some really frantic motions in an effort to escape coming directly at the camera. Tooling up again 3 to 37, Figure 3.29, Figure 3.30. Tooling up again 3 to 38, VU turning the source sideways. The progress of the emitted EV's escape followed another way to verify that they actually proceed away from the source. Figures 3.29 APD 330 are examples of this HND of observation, and a great MAPU variations in the formation and propagation properties can be seen from shot to shot. The EV originates at the lower side of the picture and proceeds to the top. There is nothing particularly notable about the shot in Figure 3.29, except that the EV appears not to reach the target. This was Roalu the case, in fact. Have included the photo shown in Figure 3.30 as AP a cameral of some of the MAPU unknowns in this business at this time. Is the EV going away from the source actually running through a nebulous ring-like EU structure, or is this just some artifact of the previous shot? The only way I can tell what is going on is to analyse the MAPU shots, not published here, that I get op videotape. Although EVs can finally be dealt with, and their properties ascertained in various ways, many mysteries remain. Evology is a very rich and complicated business, and there were many good days yet in the outpouring of information that was to follow. Tooling up again 3 to 39, IL, TI, AL1, Chapter 4, TNV outpouring. Some of you now have already scanned ahead and looked at some of the later photos, and perhaps you wondered what those ISAR images are all out. Before we get to AP explanation of the photos, we should first attend to some of the calibration exercises for the pinhole camera and the associated measurements. SAMRA calibration. Among the chief SOPSERPs with the measurements involving a source and IGET for EVs are these. What is the total charge in the discharge, and what is the quantity of charge transported to the TMGD? Although there she variations on the scheme about to E discussed, it is normal to transport almost A11 of the free electronic charge in the source region to Faya node, or TMG region. The apparatus for doing this is somewhat unconventional in that a lot of ceramous material having high resistivity is used in the process. This Pormalu makes charge hard to trace, but in the equilibrium method used here, there has been no ROLEM. The dielectric material just produces a circuit that is hard to appalooze, but plasma people are used to that. EV source. A convenient EV source is OP similar to the EV gas diode shown in figure 318, except that gas is not chest, and the cathode wire is made of sorra wetted with mercury and pushed into the ceramic pozzle to within about 1 zm of the tip. Vmiationy on EV sources are discussed in the Charter-op components and devices. The operating voltage can lowered U for EPG a silver anode electrode onto the outside of the nozzle very pair the F. This electrode must be covered with a fairly thick dielectric material to keep the discharge some triopeps that some out of the tip from being collected on the anode. A phytidon coating of glass dielectric material is usually used to produce this insulation. A region of space between the source and the collector is usually used as a filter or separator region to assure that no disorganized components of the plasma discharge at the cathode reach the anode collector. This region can be a dielectric guide with almost unimaginable complexity to filter out everything except the EV. Separator technique is further described in the chapter on components and devices and in the discussion on the mosaic guide shown in figure 2.10, which represents an extreme version of filtering. Charge collection. For collection of the charge transported to the anode, it is only necessary to put an electrode, operating at ground potential, the same as the anode and counter-electrode of the guide, somewhere in the guide region. Accessory electrodes resembling Faraday cages can be used, but the results do not differ greatly with their use. A known load resistor is commonly used at this anode point connecting the anode to ground. Since this is the point feeding the oscilloscope or other current measuring device, it is normal to use a 50 ohm resistor. Care must be taken to use a sufficiently low load resistor that the voltage will not rise too high and reflect the EV. A reasonable maximum is about 500 volts for EVs made with a 2 kilovolts pulse. Lower voltages are better. The rise rate of this voltage is very high, and an oscilloscope of adequate bandwidth is required to measure the voltage. If this cannot be done, then a capacity load for the EV must be provided. An EV will not land on an inductive circuit or on a small wire if it has any choice. It will skip to another electrode if there is one available. For any particular wire size, there is an upper EV size or current limit that can be collected. This law must be obeyed. Pulse power supply. The EV is generated from a pulse voltage source with a known series resistor between the voltage source and the EV generator. By this time in the project, an EGNG high-6 hydrogen thyrotron was being used to discharge a pulse delay line into a transformer for generation of the pulse voltage. A scope is used to monitor the voltage on the EV source, and the current is calculated from the resistor value and the voltage drop. An example of the waveform often found is shown in figures 436 through 438. The outpouring 4:2. There is some difficulty in assessing the current responsible for the EV generation from these waveforms. The actual formation of the EV takes such a short period of time that it is not possible to see it accurately on a conventional oscilloscope, and all that shows is the disturbance and small step. The steps occur at successively lower voltages in the photos shown, possibly because of the plasma discharge that follows the first EV generation. Low-voltage EV sources produce the cleanest waveforms. For a 200-volt formation, the cathode voltage drops to 10 volts or so. It remains there for a vacuum discharge for about 3 nanoseconds and remains for a gas discharge throughout the duration of the applied pulse. The anode waveform is similar to the one obtained at the output of a scintillator. A sharp negative fall followed by a recovery determined by the time constant of the anode circuit. For coulometric work, the capacity in the anode can be made fairly large to make charge measurement more accurate. Anode current values. Since most of the work reported here has been concerned with determining the detailed properties of the EV, I have not used large currents as they tend to confuse the basic processes of the EV. The current range has varied from 1 to 6 amperes. It is easy to get a value of 1 ampere from a source to an anode, with a variation from shot to shot that is sufficiently low so as to not show much fluctuation on an unexpanded scope trace. This corresponds to a variation in the 2% category, with an occasional blooper coming along that is several times this value. The pulse repetition rate for the mercury-wetted copper sources discussed earlier can conveniently go up to several kilohertz. A maximum frequency of around 10% MHz has been used for this source, but the driving pulse power supply requires a much more expensive technique than the standard thyrotron generator used on the simple pulsar. It has been found that the 1 ampere level of anode current is produced by a chain of about 3 to 5 1 micrometer diameter beads having an overall diameter of about 3 micrometers. These are rough measurements and are given to much variation, but these numbers will serve as a reference for future discussion. In order to make the measurements even this definitive, it is necessary to extract carefully the EVs from the plasma trash, and also to select a particular size bead chain by employing a separation method in which one bead chain out of a group is caused to leave the group and proceed to our measurement apparatus. This extraction and selection method is described in more detail in the following paragraphs and the chapter on components and devices. The outpouring 4.3. Plasma deflection and cleanup. While I am the subject of extraction from a plasma source, here are some data relative to such EV processing. Figure 4. 1 is an end-on view of a plasma source without mush cleanup. Figure 4. 1. The source is a nozzle of ceramis with a 0.203-inch inside diameter hole in it. Although it is not clearly visible in this shot, there is an electrode on the left side of the nozzle with voltage applied to it. The voltage is positive with respect to ground, and is therefore the anode voltage that will eventually attract the EV. However, during the period of time when the EV is covered with rasma, or positive irony, the positive electrode repels the EVs residing in this positive slough. I knew that a plasma had this net positive effect due to higher L-strop mobility. Yet, I was surprised to ye that the EVs confined in this sheath were deflected with it. After a period of time and space, the plasma is cleaned off, and the EY is deflected as cloud of electrons, figure 4. 2 shows the end view of a NOS that has been sleared of plasma. The emergent EV can be seen coming out of the center hole and string an anode electrode peru. This is AP opticae photograph taken through a microscope with a TV camera attached to it. The outpouring 4:4, figure 4:2. The resolution and contrast are pretty raw, but it does show the effect that is an important reversor to EV evaporation from a surface. If a positive voltage is applied, pair the exit of this ceramic NOS, or E, 1 EV out of the bunch. That comes 8, will leave the formation regiop and jump a vacuum gap to the output guide circuit. This is the separator action that greatly improves the purity of the EVS used in the acrylomepts mentioned here. The negative voltage pulse obtained across a 50 ohm anode 1 ode, with a 50 ohm line and oscilloscope attached to it, is typically 60 volts high and lasts only as 1 ong as the fall time of the oscilloscope. The scope I use shows a 3 nanoseconds fall time. The waveform is somewhat ragged and hard to read, and stray electromagnetic leakage into the scope through the Roa ion and other EMI sources has to be guarded against. The outpouring 4:5, charge calculations. Under the conditions stated, assuming a delta function of Schge, the calculated Schge is about 2 kH10 electrons. This condition produces a strike mark that is smaller, but similar to the OP shown in figure 3.3, or perhaps more equivalent to the less resolved images shown in figure 5.9 and figure 5.13. Depending crop the conditions of flight between the cathode and the anode. A considerable pummer of electrop sap is lost in this transit. These are the electropy that are visible to the electron pinhole camera. The pummer of lost electrons will be discussed in more detail later. When collecting an EV of the type just discussed, there is a small but clearly visible flash at the anode associated with the plasma produced during the EV energy dump. The plasma radiates across a wide restrict of energy, and this further complicates the measurement of charge. It is not possible to shoot the EV into a standard shadow cup because of the electromagnetic fields discussed earlier, but it is possible to lead the EV into a collector region, you conveying it up a guide. One day measurement techniques will be standardized, but for POW we just ike what we get, and work with it as best we sish. SAMRA magnification. Most of the photos of EVs in flight shown in this chapter are taken with a magnification of about 5 in the Eelstrop SAMRA, between the object and the phosphor is 3 8 of the camera. There is an additional magnification provided the optics of the TV camera and the associated display system. When A11 of these factors are taken into consideration, the final magnification is such that a rear one object of 0.1 inches in lateral extent produces an image that extends from one side of the TV screen to the other. The referencing borders of the TV misread SAP usually is seen in the photos of the screen. Using this magnification of 5, the nose of the camera with the pinhole aperture in it is about 1 inch from the EV source under investigation. This close proximity has not caused APU interference with the experiments so far. When the magnification is varied, moving the nose in and out along the z-axis of the camera, there are no obvious effects up the path of the EY in the experiments discussed here. The outpouring 4B sensitivity calibration. Let us now look at the problem of converting the image data obtained on the phosphor screen of the camera, and consequently the TV screen, into significant measurements of emission density from the EV in flight. The problem will be broken into 2 parts. 1. The calibration of the overall sensitivity of the camera, looking at a conventional, well-defined thermionic or field emission electron source. And 2. The application of this calibration data to EV measurements through mathematical manipulation. For calibration, the camera is set up to look at either a thermionic or field emission source operating at some voltage of choice, usually 2 kV for the example chosen here. The thermionic source used was a heated tungsten wire loop with a small aperture placed immediately in front of it to limit the area of emission seen by the camera. This aperture, in conjunction with the magnification of the system, determines the spot size seen on the screens. The field emitter does not need such an aperture because it is essentially a point source of electron emission. The final spot size seen is largely determined by the pinhole aperture in the camera, or the combination of the pixel size of the channel electron multiplier plate and phosphor screen. There are several parameters that will be needed for the calibration of the camera. The 2 kV accelerating voltage is applied for only 1.5 microseconds in order to minimize considerations of phosphor and TV integration times. This voltage is applied to the cathode as a negative pulse, and the housing of the camera is held at ground potential. The gain of the electron multiplier is set by the voltage applied to it. This value for calibration is set at 2000 by the application of 760 volts. In the normal use of the multiplier for EV observation, the gain is set to 10 by the application of about 450 volts. The direct current voltage on the phosphor screen is held at 5 kV for all purposes. The brightness level of the output image used for calibration is estimated by I to be about 25% of the saturation level of the TV viewing screen. This is a crude method of calibration, but it has been checked with a light meter and found to be adequate for the work being done here. The area of the light spot formed on the channel multiplier is also needed for a calibration of current density into the multiplier, and this area is measured by reference to spots or scratches made mechanically on the phosphor screen of the CM. The final measurement needed is that of current input to the CM, and this is determined by knowing the gain and having a scope voltage drop measurement across a known load resistance in the CEM phosphor lead wire. The camera pinhole used in the calibration work was 0.019 inches in diameter, the outpouring 4 to 7. Mesujmept SAP is reduced to the following values. 1. Sim UFST signal to scope for 1, brightness, across 11.5 k ohms, equal to 2.5. 2. Area of spot on SEM YSREEP, 0.7 mm kh 2.5 mm equal to 0.017 cm2. Calculated values FOG 1, Iskeep brightness. 1. Surrepta SREEP equal to 2.2 kh 104 amps. 2. Shrept into SEM 1.1 kh 1 G7 amps. 3. Surrept density into SEM equal to BKH 10 to 6 amps, CM2. 4. Charge collected equal to 1.65 kh 10 Ts. 5. Number of electrons collected equal to 1F formula for the PUMEG of Elestkops SM2 to the SEM input to reproduce a full spot brightness of at gain G, name 4, fel 02, kh juzo kng, kh 106, equal to 2 degrees Fahrenheit BT bol E, kh 10 seconds SM2. The purpose of this calibration is to use the camera for quantitative measurement of the emission of both electrons and ions from an EV, and to to determine VMIS emission densities from this and other sources, using the measured dimensions of the EV from witness plate shots, or assuming maximum-sized dimensions from the camera images. In a fashion similar to the OP just described, the sensitivity of the camera to ions has EEP measured using ion sources of lithium, the outpouring 4 to 8 EV emission calculations, for an object distance of 1/4 inch and an image distance of 1¼ inch in the camera. A point object or source will image as a disk about 3 times 10⁻² centimeters in diameter. The EV image in motion is seen to exhibit an intensity F of 0.5 on the TV screen at a gain of 10 and have a minimum width of about 3 times 10⁻² centimeters. The corresponding area on the phosphor screen is 7 times 104 cm2. The number of electrons arriving on an area corresponding to an image of a stationary EV is this, equal to 1.4 arc 107 electrons, neon. The corresponding number of electrons given off in all directions, assuming isotropic emission, is this, Ne x 12.5, 1/4, 2 plus 3.1, 0.012, equal to 3.5 ek 1012 electrons. The ratio of track length to EV diameter in the camera view is 1000 micrometers, 10 micrometers, or 100. Hence, the total number of electrons given off during the flight past the camera is 3.5 + 1014 electrons. The corresponding number of coulombs is 5.6 times 10 to 5. If the surface of the EV is taken to be about 3 times 10⁶ cm2, from a measured diameter of 10 micrometers, then the current density at the EV surface would be 6 times 1011 amps, cm2. For a pure electron EV model having a translational velocity of 4/10 or 3 to 107 meters per second, the rate of emission would be approximately 1025 electrons, or 1.7, 106 amps. The calculated lifetime of the EV would be 10 to 3, plus 3 times 1073 UX, 10 to 11 s. This lifetime is in accord with observations on heavily loaded or disturbed EVs. These calculations also show the charge density of the EV to be about 6.6.1023 electrons, cm3, approximately that of a solid. Not all of these numbers will hang together, and it is not my intention to convince anyone of anything with such number games. This exercise is just an attempt to show the incredible difference between the ordinary world of electronics and the EV world. It should be recognized that a pinhole camera is not a very efficient device, yet it will image an EV onto a phosphor screen without any gain applied, and this stunt requires a lot of emission density. On the other hand, the EV is capable of passing by the camera so quietly that a gain of over 1 million will not detect any emission. There has to be some use for this kind of thing. The measurement methods and calibrations used here are not highly accurate, but they do serve as a good guide for workers in the field. We have not been grossly misled by using the methods presented here. The outpouring 4 to 9. EV action. It is difficult to choose. From the many available video photographs of EVs in action, just few to illustrate some of the things EVs do. I do not have an adequate explanation for Mapu of the things they do, so will not show oscillopses. Each the photos I will show do not have adequate explanations, but at least the effects repeat themselves enough to be worthy of some comment. Vlipkegs. To begin the description of EV antics, let's look at figures 4.3 through 4.5. This is an end view of a gas diode source, and the photos shown here are a part of the series shown in the last chapter. In figure 4.3, there is a question of whether we are looking at one EV with gap, or two EVs, with the source of one of them somehow cut off from our view. Figure 4.3. Vous referez to figure 4.4 and figure 4.5. It is possible to how there was actually continuity between the two parts of the same entity. The outpouring 4.10, figure 4.4, figure 4.5, the outpouring 4.11. My interpretation of these photos is that the EV blinked out for a moment because of some unknown cause, and then returned for a brief moment before disappearing from the screen or dying altogether. I would not attempt to claim that in these photos the EV went somewhere else and lived on. It probably died. But one must be constantly aware that disappearing from the screen does not mean the EV has died. There will be many examples later of disappearing acts that are followed by dramatic reappearances. The model I keep in mind is that an EV is travelling in a potential well that comprises its electromagnetic container. It is possible to stimulate this container and lose electrons by either thermal-like processes or tunneling processes. Both of these excitation methods come from static field configurations of surrounding structures which the intense moving field of the EV is likely to excite. In short, the coupling coefficient between the EV and its physically rough surroundings is very high. This is prone to produce high-frequency excitation of the EV potential well, resulting in loss of electrons. You cannot easily drive a full bucket of water over a rough road without losing some water. Energy analysis. I included Figure 4.6 to show some of the most horrible examples of energy analysis by the deflection method. There are multiple exposures on this frame, and the initial paths of the various EVs were not straight enough for decent analysis. One thing worth noting is the detailed structure showing in the tail on the lowest EV trace. This kind of structure is occasionally seen at high energy level, around 2 kilovolts, and seems to be trying to tell me something. When a good spectrum of this 2 kV blip in the energy distribution is seen, there is usually a disturbance that follows in the form of a deflection. I tend to think of the EV potential well depth as being around 2 kilovolts. This is very high for chemical entities, but then we are not dealing with chemistry. The X-ray emission spectrum that is emitted when an EV dies suddenly also seems to be peaked at around 2 kilovolts. This is a subject that will be discussed later. The outpouring 4 to 12. Figure 4.6, Figure 4.7. The outpouring 4 to 13. Kinky eyes. Figure 4.7 through 4.9 show some Rialu-Henke behavior. These shob, like the previous ones, are coming straight out of the source into the Samra. The most noteworthy thing out these photos is the way the EV goes straight and then abruptly turns with ERHF little extra emission at the Sorpery. In A11 of these shots, the EV originates in the centre and seems to have reasonably equal leg length between T's H arps. This is true not only on the shots Yhaup, but on Mapu others available. I have a notion of what causes this effect, but there is certainly Po roof at this time. I have suggested before that some EVs she very tangled at birth, or some so you rolling across surface, and that a flight across a chasm or a low resha regiup allows them straighten out into a circular configuration. This untangles the amulets, often found to regulariu spaced, as the EVs go along through this regiup. I imagine that this process of unwrapping is a disturbing one, and shakes the potential wallone sufficiently to source electron emission, perhaps IP a specific direction, and that this jetting action is responsible for the abrupt terp. In a Pother scenario, I can see how the disturbance could cause an imbalance in container geometry, causing a propulsion effect from radiation asymmetry. I sap also see how such disturbances can be quite periodic, you virtue of the symmetry in the EV sphusture, and how this bears up the question of why the periodic THGP's osser. Of source A11 of this is highly conjectural, but it is nice to have something to hold on to while going through the dark woods. The U for EPG 4 to 14. Figure 4.8. Figure 4.9. The outpouring 4 to 15. Figure 4.10 is a side view of an EV from a gas diode source that has originated at the lower part of the picture. OP resop for showing this picture is to reinfo. I thought that something is tuming abruptfly in a more or less rectangular pattern with some very definite bursts of electron emission at the sorpers of the rectangle. In addition, there is the possibility that another EV is shooting past the rectangle heading down the top of the photo. The lower overall density of this shot allows better apaluis of the Elysiot bursts. In Mapu of the other shots, the TV system is well into its saturation region, and the electron bursts do not show well. Figure 4.10. Consorting. In the next series of photos, figures 4.11 to 4L4, I would like to suggest there is some consorting between two EVs coming out of the gas diode source, as seen in the side view. Again, the flight path originates at the lower side of the photo and proceeds to the top. Several things, sap, seen in the photos, the outpouring 4 to 1b, ILTL. There is a general tendency for the EVs to some less associated as they proceed away from the highest pressure region of the source, although there is a faint suggestion of expansion and contraction in a periodic fashion between them. This action is reminiscent of the fission-fusion behavior seen while EVs travel on a dielectric surface. It cannot be said for sure whether or not the EVs are Trakelipji together or sequentially, but at least something has synchronized their paths to an interesting degree and produced what appears to a 180-degree out-of-phase relationship. Figure 4:11. The outpouring 4 to 17.
Figure 4:12. Figure 4:13. The outpouring 4 to 18. Figure 4:14. Deflection tests. The next series of photos, figures 4:15 through 4:29, will attempt to show several important features that were not clearly available up to this time in the measurements. One feature will be a crude measurement of the velocity of an EV in Chazum flight. There will also be evidence shown for the individual nature of the high charge density entity, the EV. There is also supporting evidence for the ability of an EV to switch rapidly the potential on electrodes.
In the same series, it will be shown that a single burst from a particular EV generator, or sockets, can produce several reasonably well-spaced EVs. Finally, in this series, the blinking or modulation ability of electron emission from an EV will be shown in very graphic form. The setup for one of these experiments is to use a mercury-wetted Sora EV source operating in a doghouse so as to suppress stray plasma emission. The EV thus formed is led out of the formation enclosure across a resistively coated dielectric surface, or guide. The guide is terminated as a pointed ceramis structure aiming at 2 electrodes located in Chazum and spaced about 1 millimeter from the launching guide. The arrangement of the electrodes is shown in Figure 4:15, the outpouring 4 to 19, Figure 4:15. The closest electrode to the EV source is shown in the lower center right of the photo as lighted area caused a string IV. There is another electrode about 1 millimeter beyond the first one and located to the 1 EFT in the photo. This electrode is also shown slightly lighted, possibly UAP EV striking it. To get these photos, the camera is essentially watching the EV move sideways toward 2 small wires extending downward from the plane of the photo. The wire diameter is about 1/8 inch, and the length is adjusted to make a 1+ wave resonator warn against a ground relay at whatever frequency is desired. Picoscope. This experimental setup is a very complicated OPE, well worth the effort because it reforms the function of a picosecond pulse generator and an oscilloscope with a real-time effective horizontal sweep in the picosecond range. With this configuration, waveform measurements can be made in real time to 10 to 13 seconds. This is not an accurate device, but it sure opens some frontiers. The basic technique is to treat the EV as if it was some HND of electronic burning emma that can deflected electric fields and imaged on recording device, the pinhole camera. The Offercry PG 420. One of the most basic considerations is the speed of the ember, or EV, running across the view of the camera. We have used voltages for EV manipulation that give a velocity of around C2. This has EEP calibrated a variety of methods, Pope of which she very accurate, stemming from knowing a particle frequency that is applied to the deflectors and using this voltage as a deflection signal. Unfortunately, the frequencies needed for calibration are too high for easy generation in Muller oratory, standard methods, so I have to resort to left-handed methods to do what I want. These methods consist of using harmonics of a magnetron to excite various tuned structures that are under analysis. Srestrom analyzer to a top frequency of 18 GGGs, the top frequency of MU analyzer. Beyond that frequency, it is necessary to fly blind working with tuned stubs that are supposed to something like loaded 1, plus wave antennas. When A11 of this is done, it is found that an EV will excite such straichiochures and show a wiggle that is due to mutual coupling. Knowing the frequency of the stub and the dimensions of the wiggle, it is possible to estimate the EV velocity. Amazingly enough, the velocity is near to the CHG that was predicted for the operating conditions chosen. It didn't have to sum out this way. For the dimensions shown up the photos, the EV takes about 3 kh 10 to 11 seconds to go between the bottom of the screen and the first electrode. A similar time delay exists between the two electrodes because they have a spacing of about 1 millimeter. The best time resolution that could be obtained from the relatively busy photos shown would act 3 kh 10 to 12 seconds. Risorolsa. In addition to being ALA to see what is happening to the EV, it is also necessary to have method of producing the time-varying voltage on the electrode that is to wiggle the EV. In the Ekreramept Sheechpady A discussion, this is done using the first EV of a train of Sekarul EVs to excite the deflector electrode, while a pother electrode is used to collect the second EV, passing the excited electrode. Of source to get this timing to work out Ike's a lot of compromises in the experiment, such as using big fuzzy EVs in order to get the desired sequence of events to Ike relays. Let us now paim the centermost and closest electrode the deflector and the uppermost and left electrode the collector, both shown in figure 4.15. With Telt's names in mind, we set up the sequence of events that will take rays. The outpouring 4 to 21. Sequence of events. When an EV trape is fired off, the first OP strikes the deflector electrode, producing damped wash trape of oscillations at the patral frequency of the deflector. That the deflector was Stritsk can be verified the trays going to it, and the intensity of the emitted electrons from the electrodes. It actually looks as if it had been hit something. As a test of the validity of the assumptions Herg, it is possible to aralue a direct Schrept bias voltage to either electrode and control which electrode gets hit, or whether either gets hit. The control is quite effective. When the two voltages on the electrodes she properly proportioned to receive the first EV up the deflector electrode and the second up the collector electrode, an amazing thing can be seen. The EY to the collector is actually deflected in some periodic fashion. Even though this was the aim of the effort, it is still amazing to me that it actually happens. In the photos from figure 4, 1b to figure 4, 2 or itis, clear that the EY path up the left side of the photos is trying to follow some fairly damped high-frequency voltage variation. There are vagaries and variations in the watchforms, but these could be due to Mapu things, not the least of which is the extra EV that gets thrown in every now and then and can be seen striking the deflector electrode. For very wide deflections to the left, the EV image is cut off, the deflector plate in the Samara, and that accounting for the broken path in figure 4.17. The outpoling 4 to 22. They are short. One thing should be very clear from the photos: the EV is essentially as long as it is wide, just as the deflected images up the high-resolution witless plates suggest. There is no smearing on the photos, such as one Al Ruid get, where a long shape deflected. It should also be fairly slesh that the timing between the EVs is fairly regular, and the spacing is something like the characteristic time of the system, 10 to 12 seconds. I am not sure what parameter in the source produces the spacing, but from other observations it seems to be controlled the size of the bead chain that is used. The bead chains seem to be spaced about 1 chain diameter apart. There is nothing rigorous about these notions. Shti 11 of this helps to fill in the picture of how some of the helical structures shown in figure 4L4 are put together. Figure 4.16. The outpouring 4 to 23. Figure 4.17. Figure 4.18. The outpouring 4 to 24. The outpouring 4 to 25. Figure 4.21. The outpouring 4 to 26. Emission modulation. There is another indication in the group of photos just presented that will also be shown much more clearly later: the non-uniform brightness of the deflected EV. The EV shows a fairly faint trail when it is turning in a large radius as it enters the view at the bottom of the pictures. As the EV is more sharply deflected, it generates a brighter image, indicating more electron emission has occurred. This lends credence to the notion of a potential well that can be sloshed enough to emit electrons. Of course, another possible explanation for this brightness change is that the EV has undergone a velocity change. I can't tell which notion is true, but I prefer the one involving the modulation of a potential well. to help clarify some of the questions having to do with emission control from an EV, and also to get a better view of their spacing habits, a modification to the above apparatus was made. This modification consisted of using only one electrode to act as an EV collector. The location of this electrode is shown in Figure 4.22 as a bright spot at the top of the photo. Figure 4.22, the outpouring 4 to 27, Figure 4.23, Figure 4.24, the outpouring 4 to 28, Figure 4.25, Figure 4.26, the outpouring 4 to 29. The trail of an EV to this target is fairly faint because there is very little disturbance in the system and, for this shot, probably only one EV in view. Figures 4.23 through 4.29 show different degrees of activity caused by the random variations between shots. My interpretation of these photos is that one EV got through to the collector and excited the electrode, which was then able to undergo a damped oscillation. The field from this initial impact excited the remaining EVs on their way to the electrode. At one point in this experiment, when most of these photos were made, the voltage on the electrode was just marginally able to collect the first EV. After the initial collection, there was a long recharge time relative to the spacing of the oncoming EVs, and they could not land on the electrode that excited them. These EVs were deflected to the right of the electrode and off somewhere else. The combination of the direct current and the submillimeter wave field produced the path of the EVs approaching the electrode. One very interesting feature of these photos is the relatively high modulation index of the EV. The emission is cut off to a value of at least 1/100th of the on-state, as shown in the photos, and if the gain of the multiplier is turned up to explore the limit, it is at least 1/1000th of the on-state. This effect has to be explored with a microscope looking directly at the CM phosphor, instead of using the TV camera, due to the overloading effects in the TV camera. Another point worth considering is that a steady emission of electrons from this little portable battery is both started and stopped in a fairly symmetrical fashion in terms of exciting field amplitude, and that the timescale for doing this is clearly in the sub-cosecond range. Some switch, the outpouring 4 to 30, Figure 4.27, Figure 4.28, the outpouring 4 to 31, Figure 4.29. In this series of photos, not 11% of the effects seen SAP explained. At this point in the project, the best way to get ANSWEB is to somehow suffoopt questions with the IoT of Little Zolsweb. Then it seems that their combined value is greater than any OP question answered as RefESF, as we SAP frame the question. Inductance effects. Up to this point, A11 of the photos of EV's hush, EEP shown to clear of the effects of catching an EV in the target shay of the SAMRA. If the EV is allowed to caught on a low inductance target within view of the SAMRA, there is usually a loss of image quality because of spray radiation from the impact point. I stress that the inductance of the target must E1L, but LOI LS a sherry qualitative term that should be expanded upon before we go on much further. As have mentioned before, APEV will not easily land up a small wire. If the image of the landing is viewed IP the SAMRA, the EV can be seen snipping ochre the wire surface before finally hitting it. I believe this is simply caused U the EV, the outpouring 4 to 32, depressing the voltage on the wire so greatly with its own negative charge that the wire is unattractive to the EV. A larger wire, or a large area surface, the usual signatures of a low inductance or low impedance, is A, to supply the instantaneous charge demanded U the EV and prevent the depressed potential effect. It is always important to consider the impedance and wave velocity of the circuit being considered for an EV landing site. X-rays? I while offer two explanations for the observations that follow. One of these explanations seems preposterous, while the other is absurd. Although the effects to E explained are very graphic, I am not too disturbed, you not knowing their cause exactly. I will like the first explanation the X-ray process, and the second I will call the enhanced electron mobility effect. When an EV is caught on a low inductance circuit, it arrears to release its epigoo rapidly enough to produce a 1 Shay quantity of kh Rao photons having energy in the 2 kV range. OP demonstration of this effect is shown in figures 430 and 431. In both of these photos, the camera was watching an EV sum at the nose of the SAMRA from a source, viewed end-on. The main difference between these photos and the earlier ones is that the EV was allowed to hit the SAMRA nose instead of the anode armature ectopole to the SAMRA. What is showing in the photos is a white flash of emission in the center of the SESREAP, probably due to the EV arrow ash, and some images that are not usually seen. The thin vertical objects to the left and right of the scepter flash are shadow images of the deflection plates in the SAMRA. The insulators holding the plates extend left and right at the center of the photos. In addition, there is a dark spot JITE above center left in both photos near the deflection plates. There is also AP artifact of photographing the TV image that should be ignored. This is the diagonal band running from top left to lower right, and it is sync, our image resulting from photographing at too high a shutter speed. The outpouring 4 to 33, figure 4:30, figure 4:31. The outpouring 4 to 34. It has EEP found that the image of the deflection plates is caused a point source of electrons having AP apergu of around 100 volts. In this first interpretation, it is presumed that these electrons sum from the inside of the SAMRA housing and are produced a small area X-ray source outside of the housing where the EV struck. Additional data to sororate this assumption is provided the dark spot that is always present when this effect OSB. The dark spot could have caused a shadow from a brass insert that holds the SAMRA armature in relays. There have been MAPU measurements IKEP, whereby the nose of the SAMRA is polished before a EV strike occurs, and then is examined after the strike to determine the position of the strike and sorrelate it with the brass insert producing the dark spot. Sorrelatiop is always found. This point-pection image effect is always produced when an EV strikes the low-inductance nose of the SAMRA. It is petcher found when an EV is let down easily off a high-inductance target. When calculations are done to determine the X-ray intensity that must be present to produce one of the electron emission recorded, the PUMAs reach such staggering proportions the mechanisms used for calculation suspect. For a camera, it is estimated that the SREAP intercepts about 0.01 of the electrons produced on the inside surface of the SAMRA, the KH Rao, strike op the outside, if the electrons are produced isotropically. It is further estimated that 0.1% of the X-rays reach the production sites due to the geometry of the EV and strike site. Only 10 of these will produce one electron pair enough to the surface that can escape to the imaging SREAP. From screen brightness considerations, it is estimated that 109 electrons struck the channel plate multiplier. Therefore, 10 seconds, KH10Z, KH104, KH101, 1016 X-rays are required to light up the SREAP as it is observed. If 107 KH rows are required to produce a single recordable electron, 1,023 electrons from the EV are required to reduce the observed lighting of the phosphor. If the electron-emitting disk of the EV has an area of 3 KH10 GM2, the electron flux density is 3 KH1028 electrons, cm2. Each step with these large numbers, the current density of photoelastropes in the SAMRA would only E5 KH1F LSMZ and would not cause space Shaggy degradation effects of the image beyond that scene. The mechanisms for KH Rao and photoelectron production are just too difficult to see at this point. I cannot get too serious about calculating EV properties from the observed KH Rao effects. There are just 2 MAPU missing pieces of data. The KH Rao emission could even arise from a form of synchron radiation from magnetic field collapse, or from bremsstrahlung. The outpouring 4 to 35. Enhanced electron mobility. The second explanation for the image production, figures 430 and 431, stems from the notion that there is something amiss with standard calculations for electron penetration distances in a metal, or at least amiss with using the cindered penetration distances where Pekka and EV is involved. OP interpretation could simply be that the range of electrons in metal is greatly increased, the internal fields produced in the metal, by the interception of an EV. What we are seeing in these examples is electrons emerging from the second side of the target, or even exoelectrons launched from the metallic surface, mechanical shock. In any event, AP extreme upset to normal equilibrium is recorded. I would now like to introduce an experiment, very similar to the OPE just discussed, to help stress the difficulty of having AP-adequate electron supply at the target site for an EV. In the pinhole SAMRA, drawing in figure 3.20, let us put a 0.0002 5-inch thick phione of aluminum across the 0.040-inch hole in the anode. Using the same EV source in the previous discussion on KH-Rao effects, let us launch an EV at FIS target so as to strike the foil in the center while watching the result with the SAMRA. I can tell you the result was not too good because the foil had a hole blown through it, and the SAMRA was highly insulted. If we increase the foil thickness to 0.001 inch, the EV does not blow a hole through the foil, but it does dent the foil nicely with a perceptible bulge on the reverse side. Actually, the anode is a little different from the drawing in that it is an integral part of the nose of the SAMRA to help prevent stray radiation fields. Speckles. When the SAMRA is first turped on and an EV is allowed to strike the foil, an image is produced as shown in figures 432 through 434. The main difference between these photos is the amount of anode voltage applied for extracting the EV. There is a critical threshold for extracting the EV from the source. Ops this voltage level requirement has been met, there is little need for more. However, for a small voltage ipsremept past this critical level, different things can be seen. The voltage difference from figure 4.32 RU figure 4.35 is only about 50 volts out of 2000. More about the action of this EV selector technique is described in the chapter on components and devices. The outpouring 4-36, figure 4.32, figure 4.33. The outpouring 4-37, figure 4.34. When I first saw this specked pattern, I thought was onto some diffraction effect produced the EV, and at the root of all knowledge. It was a great disappointment to find the effect was caused little 10 angstrom specks of aluminum oxide that detached themselves from the aluminum foil as a result of the shock treatment the EV was giving the foil. I actually had to collect samples of these flakes and analyze them in a transmission microscope before I would believe this was the cause. Giving up mu diffraction patterns was pretty hard. What put me on the correct path was the observation that the aluminum foil would clean after bombarding the foil for AP hour or so. After the foil was clean, the pattern was that shown in figure 4.35. I still have trouble believing that aluminum oxide particles can give rise to Illustrop emission in a SEM, but the evidence is overwhelming. The outpouring 4-38, figure 4.35. Thermionic-like pulse emission. The mystery was not over yet, however, because I should not explain the RATUP in figure 4.35. I originally put the aluminum foil ahead of the SAMRA to get a cute form of EF scope in which could image the landing of EVs with high resolution. This just flat did per work. What I got was an image with a lateral dimension of ocatores of RP-INI, and this was totally useless. This effect turped out to a useless for imaging, but it is a re-1 whiz-bang of a PUHB geparator. View reform EPG AP energy analysis on the electrons forming figure 4.35, I determined they had a spread somewhat similar to thegmiopis emission, mising from a negative potential of 2 kilovolts. How could this E? Electrons are not supposed to have RAPG enough to penetrate the 0.001-inch foil target. It finally dawned on me that possibly the foil was actually being pulled down to this negative chalu, the auricle of the EV, and that the momentary heat PG of the aluminum did indeed reduce thermionic emission. How wild! The outpouring 4-39. Calculations were made op all HNDs of things such as the inductance CD, resistance at elevated temperature, specific heat arguments, and a host of considerations on interacting magnetic fields. The conclusion was that it is possible to drive the hot resistance of 1 kH 10⁻³ OHM's -2 kV with the charge available in the EV. Finally, using the calculated capacity value of 10 to 13 farad, it was determined that the RC time constant would EA out 10 to 16 seconds. It is HHADA to get a Greer on the LR time constant, but best estimates raise it in the same RAPG as the RC time constant. In any event, we should pushing the boundaries of Ilstrop relaxation time in a metal. A negative charge is not easily dispelled for the EV to land. One of the rhyme considerations here is a real possibility that the less drop density for the EV is as great as that of the solid metal electrode, that the mobility could be higher in the EV. This would severely tax the metal to maintain suitable fields for the EV lighting. Measurement itongly suggests that when the EV is starved for electrons, you even so simple a geometric trick as providing a foil rather than a massive block of metal, X-rays wilt neu be generated. Instead, oplu a strong electromagnetic pulse will be generated. Notions for making such a picopulsar are included in the charta on components and devices. The outpouring 440, ions and isotopes together. The photographs presented up to this time have largely been subsumed with electron images from the pinhole camera. The rest of this chapter is devoted to presenting ipfogmatiup, obi and op, both elstrop and ion images, using the EV to stimulate chagyok structures and then viewing the result with the camera. The first startsfer to e-pressen VD is an EY rupop, a resistively coated dielectric surface that statt a gas introduced near the surface, while the entire apparatus is operated IP chasham. This gas EV guide was shown in Figure 319. Some of its operating parameters were discussed in Chapter 3, Figures 436 through 449. So pipe die pertinent to the use of this guide. The OCFO Cry PG 4 to 41, Figure 436, Figure 437. The outpouring 4 to 42. In Figures 436 and 437, the camera is trained on the source region at the 1 hour end of the photo. The white lines show the path of the EV, picking up the image of the emitted electrons. The magnification of this photo is reduced from the values used in calibration, pulling the camera further away from the surface to get a photo of the longer path of the EV. The maximum distance from FEF EV source at the bottom of the photo to imget is something like 1 SNM. Oplu about half of this path shows in the photos just mentioned. The voltage waveform for producing the EV is also shown on the left side of the photo. The pulse length is about 1 microsecond and the vertical calibration is 2 kV RA division, giving about 40 BKV for firing the source, depending Europe the value of other parameters used in the source. In these two photos, a high degree of wandering and disturbance is evident. This is usually caused low gas pressure and a rough surface. As mentioned in Chapter 3, the EV is disturbed surface irregularities, but the gas pressure can lift the EV above such disturbances if the resure is high enough. This series of shots was designed to hit a target of silver painted up the surface. The gas pressure had to be kept low enough for the each to find and hit this TMG. At high gauge pressure, the EV just sailed over the electrode and is off for somewhere else out of view of the camera. The outpouring 4 to 43, Figure 438, Figure 439. The outpouring 4 to 44. Figures 438 and 439 are views of the EV RUP in the region of the target anode. This view is beyond, simply manipulating the camera in the y-axis until the anode room comes into view. In these two shots, the path of the EV sap is seen approaching the target at the top. The EV path is the thin line, and the arget is the oblong bright iPod at the top. These photos are obtained at low gas pressure, and without NY cholage applied to the deflection plates within the camera. As will be shown in the next series of photos, the anode volume is a plasma of ions APD electrops formed when the EV strikes the anode. In Figures 440 through 4.47, deflection voltage is first raised and then lowered in voltage, giving the ions and elastropy separate directions of deflection in the camera. In actual operation, the spectral data is IK, about every 1/3 of a second, or as fast as the TV camera can reach over from the previous Yohob to fogum a nice series of photos of which only few are presented here. The outpouring 4 to 45, Figure 440, Figure 441. The outpouring 4 to 46, black EV strikes. In Figure 440, the EV is seen approaching the target area, but then fading from view. As far as I know, the target was hit, and in all likelihood, the EV seen approaching the target did the hitting, but for a brief moment it disappeared. There was a low extraction voltage, about 100 volts, applied to the camera to help clear the image of the fogging produced by low-energy electrons. This may have somehow also removed the ability of the EV to produce an image in the region of the target. This is just one of the experimental things that gets away from me once in a while. One item of interest in all of the photos that follow is the structure showing in the ion cloud, or plume, at the anode. This usually carries details that are very similar to those of an EV path, but they are shown as positively charged structures throughout their lifetime. Although I am certainly used to seeing EVs suddenly pop out of a cloud of plasma, I cannot say that I have pinned down this effect. In Figure 4.41, the explosion of the anode is clearly evident, but the EV trail is not visible. In this view, the deflection voltage has been raised very slightly, as can be seen by the slight displacement of the ion cloud to the left. There is also a very faint image to the right of the main blast that is in the correct place for electrons of moderate energy. Very low-energy electrons would have been swept far off to the right, the outpouring 4 to 47, Figure 4.42. Low Elstrop-Epergu spread. Figure 4.42 reveals much more information in that the EV input streak can be seen Sleerlu, and it is displaced to the right of center as it should be. Notice that the Epergu distribution of the EV streak is as narrow as the unanalyzed EV path that shows on earlier photos. The emission Epergu from an EV is thus similar to a well-characterized emission line and is not totally degenerate. The ion image in this photo is well deflected to the left, but has a hint of structure showing at a smaller deflected chalue. The shape of this stride Lescher Wiley is seen in later photos. It is possibly related to the shape of the anode ergot. The outpouring 4 to 48, Figure 4.43. Figure 4.43 is somewhat similar to Figure 4.42, except that the EV trail is totally missing. Thing worth considering is that the deflectors in the SAMRA are Sarala of a little bit of mass analysis if the ions delivered to them are not accelerated U a SOMOP voltage. This is a possibility in the Sommerlech ionization system used here, the outpouring 4 to 49, Figure 4.44, Figure 4.45, the outpouring 4 to 50. Figure 4.44 shows the approaching EV fairly clearly, and it goes all the way, or I should say they go all the way. Several paths can be seen coming in, and it is not possible to figure out what is happening. Obviously, the deflection voltage has been raised to a higher value than the last shot. There is a lot of structure in the ion image that could be a result of the multiple arrivals. Twin EVs or dual energy levels. Figure 4.45 shows something very interesting in the EV track, the twin trail that seems to be real. In addition, the electron image, now deflected far to the right, has taken on the shape of the anode electrode, as if it were looping around the electrode before going in for a landing. This loop later will be seen in complete form. Here it only partially shows. Again, the EV energy distribution is narrow considering the deflection voltage applied. The twin trail may be a manifestation of two energy levels in the EV. This question could be answered if the loop had continued around the top, where the deflection would not provide a separation. The outpouring 4 to 51, Figure 4.46, Figure 4.47, the outpouring 4 to 52, neutral emission. In Figure 4.46, there is another phenomenon that happens only about 1% of the time. In addition to the ion cloud showing, there is a bright streak at the neutral position. I believe this is an image of an X-ray or UV production site. As I have stressed before, the EV will dump its energy as X-ray only under certain conditions associated with the anode. When marginal landing conditions exist, the X-ray production effect is intermittent. Sometimes the EV finds a good spot, and sometimes it does not. In Figure 4.47, the deflection voltage has been turned off, and the deflections have gone away. Several EV trails can be seen coming in, but only one can be seen going to the target. Gas pressure effects. In all of the above shots, the gas pressure was kept fairly low, possibly in the 10 to 3 torr range near the surface, to facilitate hitting the anode target. In this range, the EV leaves a faint visible light image as viewed by eye, and, as has been shown, an electron image that varies somewhat. When the pressure is raised, the visible light image fades out completely, and the target cannot be hit because the EV is essentially shielded from it by either a polarization effect in the gas, ions, or what have you. This mechanism is not clear. The outpouring 4 to 53, figure 448, figure 449, the outpouring 4 to 54. During a certain transition pressure range, the images of figure 448 and figure 449 are produced. What shows is a loop of charged particles having a positive sign. This loop can be repeated hundreds of times. It seems to have the shape of the anode and to be centered on it. Where is the EV coming from, and where is it going? The reason that electrons from the plasma, which are presumed to accompany the ions, are not visible might possibly be the application of a low-voltage bias to the camera, mentioned earlier. At a slightly higher gas pressure, the loop fades from sight, and the EV has nothing at all to do with the designated area. It goes off to some place of its own choosing. A small tube, end on. The remaining photos in this chapter, figures 450 through 458, represent an attempt to photograph something with the camera that is somewhere in between the pure EV type of experiment and something more standard, such as a plasma system. The configuration used for this series is a fused quartz tubing with an inside diameter of 0.15 mm and a length of 50 mm. The outside of the tube is surrounded with a metal to act as a counter-electrode or anode, but the end of the fused quartz sticks out about 1 mm past the metal covering. A cathode of mercury-wetted copper is used in one end of the tube. This end is virtually sealed by the copper wire. The entire apparatus is operated in vacuum, and the camera is positioned to view the discharge straight down the open end of the bore. The outpouring 4 to 55, figure 450. Figure 451, the outpouring 4 to 56, T. Lee. When the apparatus is first turned on, without any special extractor or deflection voltages, an image such as the OPE in figure 450 is OIP'd. In this photo, the only peculiar thing is that the emission is somewhat stringy instead of being homogeneous. This could be sold ou apupumer of things, not the least of which could be droplets of mercury, lopy off of the cathode during the discharge, leaving an electron track from thermionic emission. This is probably not the case here, although its seriaplu could happen. VU applying a voltage to the deflection plates. It is obvious from figure 451 that the image is made up of electrodes, and they seem to be hanging together in some way reminiscent of Sipchid EV behavior, but the effect is weak and could easily pass U. The absence of ions in the image also shows here. This has caused U the different sensitivity of the channel multiplier for ions and electrons. It is assumed that since Schge neutrality is more than likely the rule, the pummer of ions and electrons emerging from the tube is equal. I also assume the predominant ion seen is mercury, although no mass analysis has been reformed op the discharge, the outpouring 4 to 57. Figure 452, figure 452 shows a shot taken at higher gain so as to see the ions, as well as a central image that cannot be deflected with the voltage applied to the deflectors. The electron image is in full saturation, and very little detail is available. The remainder of the photos in the series were taken with progressively lower voltage on the deflectors to show the images of ions and electrons coming together toward the undeflected center spot. In this series, the details in the ion image are interesting, but I haish not been ale to get any significant information from them. The outpouring 458, figure 453, figure 454, the outpouring 4 to 59, figure 455, figure 456, the outpouring 4 to 60, figure 457, figure 458, the outpouring 4 to 61, the search for ions. Since OPE of the most nagging questions in all of this EV work asks what holds them together, I have consistently kept mu on the ion quantity and type produced around an EV. Whenever light is produced, UAP EV going across a surface, possibly there are also ions produced, but the numbers of electrons available are far in excess of the ions. It is possible that with THC negative charge laid down on the surface, UEV decomposition, the ions are drawn more strongly to this nearby charge than to the SAMRA. What are the reasons? A strong ion image is not usually available. There she times when just simple experimental error or bad experimental technique will obscure some interesting observation. For ecameral, the images in figure 4.48 and figure 4.49 were interesting to me. I may well have optimized the image, subconsciously, and rejected the foggy cloud of electrons that may have existed pair the image, and held the slew to other mysteries about the roses. In Mapu of these experiments, ID statistical nature of the RAO R precludes an easy returp to the same data ops that shot is fired, it is gone forsher. In spite of these missed approaches to answering the ion questions, there are still Mapu trials where conditio Rs should have EEP right to see ions in the EV structure with moderately high sensitivity. Such approach is TB launch the EV into Chajum and look at it with the Samara set to optimize ion collection. Applying the RORA extraction voltage and polarity to the Samara. Both end-on and sideways analysis has EP done on EV traces. This method. It is usual practice to teach EHRP up the SEM gain higher and higher as the extraction voltage is being raised for ion collection. At a fairly well-defined point, the Ilstrop image of the EV track disappears very cleanly because of the limited energy of the electrons, usually are out 2.2 kilovolts, and then the SEM gain can interrupt up all the way. With some risk of breakdown, the SEM SAP operated at a gain of 20,000. Up to these test conditions, every other gain is turped up maximally. When this is done, the detection limit of ions calculates to at least 10 to 5% of the electron density. With a little stretching, it can even be said that ions she not present to within each epopion in a million electrons. That seems unusually low to me, just from the sign point of accidental involvement. There is still some mystery as to why ions do not seem to show themselves if they are preanal. This is somehow tied to the often repeated observation that an EV sap go through a low Rochechouart gas para surface and leave neither an optical nor illustrop trail as evidence of passage. The outpouring 4B2, the notions to follow may be a little too philosophical, but this is not a bad time to record such notions. Suppose, for some reason not yet understood, the EV really is a tightly bound group of negative charges with the density implied by the measurements. Inside this array, we might say there is a tendency for like charges to attract each other, at least to within certain limits. Does this not imply that for some distance around this reversed Coulomb region, there is a region where unlike charges might repel? Farther away from the EV container, there would be the normal effects of unlike charges attracting each other again. I don't know why anything would behave this way, but then again, I do not know why EVs do what they do. Whenever one rule seems to have been broken, it is likely that you will find another broken rule somewhere nearby. Summary of EV properties. The following list summarizes 10 properties of the EV revealed by the pinhole camera. 1. The diameter of the largest charge-emitting structure tested here appears as a visual trace shown on the screen and is 1/22nd of the full screen width of 0.1 inch as referred to the object. This is an apparent width of 10.2 centimeters or 200 micrometers at the object. This dimension is not consistent with the witness plate marks showing bead chains with a diameter of 20 microns or 2 times 10.3 centimeters, but there are many ways to make an image look larger than it actually is, and we may have some of these at work in this apparatus. Space charge repulsion and scattering around the outer regions of the EV could easily account for this loss of resolution. 2. It has been shown that the residual charge carried by a 3 micrometer diameter EV striking an electrode is 2 times 1010 electrons, and that as many as 3.5 × 1014 electrons can be given off by a 10 micrometer diameter EV over a flight path of 1 millimeter. The charge density from these considerations is in the range of 6.6 per 1023 electrons, cm3. It is not known whether an EV gets smaller in flight as a result of shedding electrons or not, but there are indications that some EVs may actually explode in space once a lower critical charge, and perhaps charge density is reached. 3. The velocity attained by an EV under applied fields indicate the charge-to-mass ratio is similar to that of an electron. 4. Deflection of the EV by fields of known polarity shows that it responds as an electron. 5. Tests on the ion content of an EV attest to an upper limit of 1 ion per 100,000 electrons. 6. An EV is capable of being excited into emission of a narrow band of electron energies by various means, including electromagnetic excitation. 7. Sudden destruction of an EV causes copious emission of X radiation. The outpouring 4 to 63. 8. An EY can be transported without emission of illustrops or photons. 9. The charge of AP-EV sap, a dumped suddenly on AP electrode, causing a LHH time rate of change of voltage op that electrode. 10. Coupling between adjacent EYs produces quasi-stable structures. Reviewing the AOV list of EV rarity makes me sherry glad that I finally got shooped to trying the pinhole camera. The SAMRA has indeed produced AP Okfuripk of information op the properties of APF, and a lot of time was saved, you using this qualitative instrumentation Arosh. In a later phase of the work we whittle fill in a few of the blanks left open here. The last EV experiments to be done in Pescadero, California, were made op October 14, 1983. After this, to avoid the oppression caused, you living IP, the California coastal zone, where government permission is needed to do almost anything, the Iabratary and MU home were packed up for a move to Texas. The Outpouring 4B4, Chapter 5, EV Targets. This chapter gathers together an account of various events that do not fit neatly into the foregoing chronological narrative. For most of this data, I did the work at Pescadero, where there are exceptions I have identified where it was done, and by whom. No conductivity, no strike. In May of 1983, there was much concern about the shape of an individual EV bead, so some tests were done in vacuum to see if a high-resolution witness plate would reveal more about the EV structure. One of these tests consisted of firing EVs into a target of thin film material from a source with good aiming ability that could put an EV shot group within a 20% micrometer diameter. The usual target was a solid material, but these results suffered from poor resolution, and I thought a thin film target would be better. Such a target was fabricated by using a standard 200 mesh copper grid electron microscope specimen screen as the base. This held a thin film of carbon with chromium deposited on it to a thickness of about 500 angstroms. This grid was put into the anode witness plate holder of the apparatus, and EVs were fired at it, op at a time. Much to Mew's surprise, I could not hit the center of the target at all. The center is the diamond-shaped region shown in Figure 5.1. Even after nearly 100 shots op screen. A11 that I sockled hit were the sorrow bars of the grid, and these shots were scattered A11 eruped the scepter for which I was aiming. Figure 5.1. On one of these grids, shown in both Figure 5.1 and Figure 5.2, a strike did manage to hit the edge of the film enough to wreak the film in the center. A Scheffel inspection of Figure 5. 2 Richels, about 3 EV strikes on the sorrow grid, as well as a barely visible splash at the lower edge of the broken screen hole that is responsible for the broken film. Mu iptets rotatiop of this is that the chromium film is so high in resistance that the voltage on the film is driven negative, U the approaching EV, thus making the film an unattractive raise for the EV to land. This kind of argument is very much in one line with the discussion in the last chapter on how the electrons are upale to be supplied, even a relatively massive alumipum foil. When the EV cannot land on the center of the grid where it was aimed, it must terp within the last tens of micrometers and hit the copper grid, FAF, targets 5 to 2. Figure 5.2. Conductive backing plate. An immerate factor in the above experiment was that the sorrow grid was mounted in holder that did not provide APU conductive backnung for the grid. The grid was held at the edges only. In the next experiment, a conductive backing way provided in the form of removable plate of titanium, one of the oldest witness plates used, and this plate was closely coupled to the copper grid. What was seep after a single EV shot is shown in figures 5.3 through 5.5. EVTM gets 5 to 3. Figure 5.3.
Figure 5. EV targets 5 to 4. 1 liter IYI. Figure 5.5. Vulung through the blown Yule film material, it is possible to see an EV strike on the back nung plate. This mark is typical of an EV strike on a titanium plate. It has the classic milk splash structure, associated with it, in which a central core of material rises up and then falls to one side or the other, finally freezing in place. It is remarkable to me that the structure of the EV is maintained after penetrating the film of chromium and sarop. Notice also that the carbon is attacked less than the schromium. The type of destruction produced here is not so much that of a bullet-like thermal rosas, but rather one of a miniature bolt of lightning where the film is destroyed at great distance. You, a violently active assassin, who escaped Onargilu unscathed. Thin sarop target. The attempt to increase the resolution of the witness plate had failed, but I attributed the failure more to the presence of the chromium than to the presence of the sarop. Attempted to rescue mu high-resolution aims. You using a film of sarop without the chromium. Normally I would have considered this futile because of the negative field the EV would have induced into such a high-resistance material, but I began to see the light from the backside of the Rolem. In some respects, APEV is interested in high-resistance materials, as evidenced due their attraction to dielectrics, possibly through the polarizability of this class of material. In APU event must have thought a carbon film looked more dielectric than metallic to an EV, and so decided to give it a shot. EV targets 5 to 5. A sarop film out 100 angstroms thick was mounted on a Sora grid in the recessed holder, and several shots were fired at it. The grid was inspected in both an optical microscope and the SEM, but nothing really interesting showed. This is one of those times when intuition has to be trusted, and Mike told me to put a high-resolution transmission electron microscope on this inspection job. I do not have a transmission microscope, so I bought some time on one at Stanford University and looked at the films. It is a tedious job to look for a low-contrast object on a background of about the same density, and so I spent quite a bit of time scanning Arup-D. Cicera, one funny shapes kept coming up in the region where I had bombarded the film, but I kept passing them U. These shapes were simple little rings that were slightly darker than the surrounding material. They happened to be very close to 1 micrometer in diameter. Suddenly, I found a Rokep film that had EEP rolled back due to strain, and I got a sideways view of the effect that had been producing the rings. What I saw is shown in Figure 5b. This looks like AP extrusion of the sarop film. It was going in the right direction for an EV to have passed through, and it is the right size for bead. But how in blazes can one extrude sarop like this? Figure 5b. Once in a while, I just have to accept something new. So I recalled that impact extrusion at Higg sped can X-food materials Pormalu thought to E-brittle. If A11 of this is possible, the EV that got through would certainly E-filtered of heavy ions, although I cannot itchep E sure of that apumor. Unfortunately, I did not collect the EVS used to hit the target. This was just AP oversight, and there was no time to go back. EV targets 5B. I am not sure whether this attempt to improve the resolution of a witness plate was a failure or not. There is no detail op the film of sarop that gives any clue as to the structure of the thing that passed through. Perhaps it was rotating and lured the image. Perhaps this is A11 there is. We will return another day. These photos represent the last of the targets that were used at Pescadero. The following work was done while the 1A was being rebuilt in Austin, Texas. The work done on plasma streamers during this interim period was Reolu low science, because most of my equipment and gadgets were still packed away in shipping boxes. The streamer work RORA is described in the next chapter, but there are some EV targets used in the work that I want to describe here, while the memory is still fresh up what happens to similar targets in Chazium. Strikes from a Tesla coil in air. 11% of the events in the streamer work are done in an 8 Asiaki environment, with or without metallic electrodes in phi gas, and with a pulsed RF power supply. This power supply produces a burst of RF in the MHZ Rapshi. Thus, several complete cycles of energy are available to form both EVs and a sheath of ions that can socker and shield them, as will own a supply a retar RP direct path to the source. Without elaborating further up the methods used, I do want to show the difference in the effects on a target witness plate, Figure 5, 7. EV targets 5 to 7. The strike marks produced in Figures 5-7 through 5-9 were produced in the most primitive way possible. A standard laboratory Tesla coil, Pormalu used for finding leaks in a glass Chazium system, was allowed to streak a film of chromium on glass. Figure 5-8.
This was done at atmospheric pressure in air. What one sees visually is a thin, loose streamer going to the plate, and a small flash at the plate. When this plate is viewed in a SEM, these photos result. Figure 5. 7 shows a rather messy area on the substrate with some chips and scratches on it. It also shows 3 strike MSKs and some of the splattered metal from the strikes. Figure 5. 8 shows a single isolated strike MSK with a small quantity of splatter. I show this because there is po-Rayleigh outstanding roughness on the surface to cause a cathode arc crater or the like. I have constantly looked for such occurrences but have Pecha found them. From Eschlier work I know that an EV goes where it is aimed. Even though the terminal guidance is strongly electromagnetic, Titare EV is not Oshef Sopserpt about roughness or small points. In the photo, a DHK rectangular patch shows, resulting from contamination in the SEM. I just watched this spot too long. Figure 5.9 is a magnified view of Figure 5.8 showing a sherry nice round hole. The ellipticity is due to the viewing angle of the SEM. It is AP old trick to use a 1A Tesla coil to pierce very small holes in thin glass for making misread leaks. This is the mechanism that does that job. With the experimental setup used, there is no definite way to say whether this was an anode or a cathode. It is just a hole in the chromium film, but it is very similar to other holes we have seen. Draw your own conclusions. EI targets 5 to 8, Figure 5.9, strikes in low-pressure xenon. To make just a little more science out of the above experiment, a discharge was carried out at a pressure of about 0.1 millimeters of mercury in xenon. The power supply used was the pulsed 1.7 MHz burst generator mentioned earlier, discussed further in the next chapter. At this low pressure in xenon, the streamers are very thin, almost invisible, and seem to have no energy at all. Their strike mark is practically identical to the one just shown for 1 atmosphere of air. Figure 5.10 shows one of the most peculiar of the strikes obtained. EV targets 5 to 9. Figure 5.10. In this photo, there are 2 strikes that must have occurred simultaneously, otherwise the film would not have been ruptured and lifted from the surface. The strike marks themselves are identified by the splatter that emanates from them. There is 1 strike near each end of the fractured shape. Figure 5.11 is a magnified view of the strike, at the top of the fracture. It is the same old story. The marks look very much alike under almost all conditions of EV generation. EV targets 5 to 10, Figure 5.11. EV targets 5 to 11,
Figure 5.12.
Figure 5.13. EV targets 5 to 12. Difference between gas and vacuum strikes. Now for the Rio 1 Sorais, when a grid of Sora coated with chromium, just like the one for the vacuum shots, is placed pair the path of OPE of Fe low-pressure streamers, and sufficient capacity is coupled to the grid, U attaching a small wire. The streamer either ruptures and sprays EVs up the grid, or the stream terminates totally on the grid, leaving the grid loon like it was hit with a load of birdshot. Figure 5.12 and Figure 5.13 show the low and high magnification SEM photos of the effect. View incorporating gas into the EV transmission process, it has now possible to hit the low conductivity films stretched asteroids the grid with PO trouble at A11. It must be that the ion sheath that is presumed to travel with this HND of streamer somehow prevents the retarding field from building up on the films. Again, I wish I had caught the transmitted EVs on a high-resolution Witten BSS plate up the back side of the film, but I11 saved that OPE for later too. EV TM gets 5 to 13. Scanning tunneling microscope strikes. I was attending a field emission SOPFREPS and discussing a scanning tunneling microscope with Mark McCord of Stanford University. In this conversation he mentioned having had bad time during his initial work with the instrument he was building, azores of arcing or breakdown between his cathode and the specimen or anode. Ney showed me some pictures of his anode and cathode. As soon as I saw them, I begged a soru of a photo from him because I recognized the signature of the EV again. The photo he gave me is shown in Figure 5.14. Figure 5.14. EV targets 5 to 14. In MC Cordy work, the cathode is a tungsten point, and the anode is either raw silicon or gold-coated silicon. The scanning tunneling microscope manipulates the 2 electrodes to within a few angstroms of each other, and then scans out an image of the surface. If the voltage is much above 25 volts, the arcing problem is rope to happen. What is showing in the photo is a series of explosions at the anode that have occurred as the raster pattern is scanned. Each strata is very much like an EV impact, and a large quantity of material is thrown out of the strata. The cathode, a tungsten point, is initially blunted, but then withstands more of the withering explosions without much change. I comment on this because I'm interested in discriminating between the so-called cathode spot and AP-ever node strike. Almost some to believe there is no cathode spot, just AP electrode that momentarily looks like an anode to an EV, and gets hit. Most of new notions for this potential reversal effect, some from data, others have icon on the unipolar Rs, produced U-laser irradiation. Fred Schwerzke, of the U.S. Navy POSB Graduate School at Monterey, has published a lot on this effect. Schwerzke, 1984. EI targets 5 to 15. Figure 515. Figure 516. E targets 5 to 16. Field emission diodes. As a final RAPSH type of target in this series of EV targets, there is the unwilling target shown in Figure 515 and magnified in Figure 5(1b). These are SEM photos of field emission diodes made USA spint at SRI Iptapatiopol. The photos show what is left of a beautiful array of field emission diode emitters after some HND of electrical breakdown occurred. In the testing of these arrays, it is typical to aralue up to 50 volts on the top electrode, or anode, that shows most easily in the photo. If you look carefully, cathodes or emitter tip sap are seen in the small holes. MU interpretation of the blow-up is the same old song. EVs were formed when the Sarept density, ESMA too high, perhaps during breakdown, and then they jumped on the top anode film. The witness marks are not great loon marks, but they do have some of the right characteristics. What is evident here, and in MAPU of the low-voltage EV generators, is that the EVs seem smaller in size. What a universal creation Rosie's this EV generation is. How could it have remained hidden for so long? Voripy-Jethko dielectrics. Another class of attack, launched UEV structures, is formed in dielectric materials that harsher field across them. I am sure there is a field across almost anything that an EV approaches, but in the case I am out to discuss, the field is applied to the material in an attractive direction for the EU before the article of the EV. There are two general subcategories to the class of effects up to discussion here. Category 1 occurs when an EV is caused to rupt down a channel that is Ruroselu made for its guidance. In the case of an EV made from a discharge of around 1 kV with metallic cathode, the channel width, or diameter, used is Pormalu about 20 microns, not too different from some of the EV ring diameters that were shown in earlier photographs. Category 2 of observations is done on 2 plates of Sarafulu lapped solid dielectric materials that have a very small crack between them. EV targets 5 to 17. Figure 5(17). What can be easily seen in the first category of experiment is that when a grush is slife unarger than the critical size for EV passage, there is no measurable effect caused the EV op, the guide structure. Reducing the guide structure only a few % in width for rectangular structure or diameter, for a round structure, the damage is suddenly catastrophic. The implication here is that the guidance is stiff, and take the EV has a well-defined dimension and is quite stiff, as if it were a reamer made of very energetic solid material. The following discussion is of work that was mostly done in 1986. Figure 5(17) shows AP optical photograph of a channel of aluminum oxide film material deposited thermal evaporation, mason, a 20% misrop wire. The alumina is doped with tungsten to render it slife conductive so as to control charging. A molybdenum film was deposited about 20 microns each pedia the channel to act as a counter-electrode or anode. This type of construction produces a well-defined guide for an EV. Doped alumina of at 1 20 microns thickness is op 3 sides of the EV. Although the contrast is somewhat low in black and white photograph, a region of EV attack can be seen on the 1 EFT side of the photograph. This attack has evidently produced heating of the alumina, and subsequent consolidation. The right-hand side of the photograph of the channel has not been damaged, repeated use, as an EV guide. There is only a very small difference in the size of the guide in the two regions. EV targets 5 to 18, figure 5:18. A cover plate of the same HND of alumina was deposited op glass and is used to close off the top of the rectangular channel. In the Particom experiment up here, the chapel depth was not adequate and the cover plate was attacked the EV. The result of this attack is shown in figure 5:18. Its sap is seen that heating has produced shrinkage cracks in the alumina film. EVTM gets 5 to 19. In another instance, shown in figure 5:19, the solder plate was first used op the left side for one experiment, and then again on the right side op a different channel. Obviously, the destruction was considerable on the left side, but the right side of the channel solder was not fitted refs flat on the channel, and this caused the channel depth to slightly greater in one raise than another. Notice that the very slight taper of the cover plate greatly affects the health of the alumina film. In regions where the plate was slightly closer, BV attack has consolidated the material and cracked it. Once a channel has been bored out, UAP to fit the particular needs of the EV, there is no further attack. Repeated EV firings at any known rate within the limits of the RC recharge of the channel can be used without further change in channel properties. Figure 5:19, EV targets 5 to 20. Reori PG small channels. This Reor Rosie, SAP A, carried out from AP absurdly small initial channel size. In one particular experiment, API was launched into a channel of OPLU about 4 micrometers in width that was mechanically lapped into one surface of a rare of 96 VO aluminum oxide ceramic plates. A finely lapped socker plate of 967 Ulchmipaway used to socker the small groove. The two units were RPG together and clamped to produce a sherry small spacing between the two party, RAS less than 5 misro ipshes. A mercury-wetted silver cathode was provided within a small epsilosure pair the tip of this structure, so A to provide an isaurus. A silcher supta elstrode was fired up to Peath. In addition, a grounded collector electrode was placed about 0.01 inches away from the F of the Ceramis assembly placed in a chasum shammer. When a single EV est was fired, pulsing the cathode negative about 2 kilovolts. A lot of SPMKs were yeen to shoot from the tip of the ceramic. 11 successive pulses produced RRO sparis, only EVs that strecks the Argid anode. EV TM gets 5 to 21. Figure 5:20. Figure 5:21. When the two plates of ceramic were taken apart and examined in an SM, the photograph in figure 5:20 resulted, showing the effect of the passage of the EV through the ceramic. Sleep hole was bored in exactly the location where the 4 micrometer groove had EEP previously placed. Notice that phase Ceramis part up the right has a groove sitting at the small depression that had EEP provided as a doghouse for EV formation. Before tar-eye firing, there had been no marks up this polished surface. The EV had dug out a channel in both plates that, in just one passage, took almost all of the material out the way it went. Figure 5:21 shows a magnified view OTI end of the channel on the right side. DS is typical of an EV attack on alumipar ceramic. The smooth-bore fogmed, vapor-deposited alumina is subgrouped, highly disturbed alumipar bits. I would like to know what HND of beast it is that treats our high-temperature and refractory materials so shabbily. EV targets 5 to 23. Figure 5:22. Figure 5:23. EV targets 5 to 24. Multiple hole Voga PG. Even greater mysteries are shown next. Using 2 polished plates that she rushed as previously described, except that Po initial grush was provided, and the fell SIPG rate of the EVs was increased as to allow PO electrical discharge of the ceramic between the firings. Figure 5:22 APD figure 5:23 show a low magnification SEM of the two halves of the ceramis, mirror images of each other. Notice the similarity of the channel sizes and the approximately equal spacing of the channels. This HND of Sharknung has been seen mapu times on Shrephases. The position of the track is caused surface charging. It can be presumed that a similar charging process is responsible for the uniform spacing of the channels here. The EV seems oblivious to the fact that the solid material is in its way. It just treats the submicroscopic srask between the surfaces as if it were a free surface, and projects the material in the grooch out with it. Assuming that the postulate of charge control of the Chapel position is sorest, it can be seen that there is a very high gain process at work here. Which a little charge at the EV generation point controls the removal of a lot of very stable material. Figure 5.24 shows a higher magnification of the end of one of the channel structures formed the EV. Figure 5.24. EV targets 5 to 25. What appears to have happened in the formation process of the channel is that the EV passed through in a very explosive and disruptive fashion, producing a 1OT of fractured alumina. There is also the possibility that a chara of alumina was left behind after the EV passage, and that this vapor recondensed on the surface of the fractured alumina, leaving featureless 1 hour. This thought has erased all hope I had about finding telltale evidence of EV structure, analyzing the walls. Momentum Trapsfeg. In earlier work in channels, using mercury-wetted cathodes, it was occasionally observed that, up to microscopic observation, a small bit of mercury, deposited op the walls of the EV guide channel, would consistently and slowly mosh in the direction of the EV passage toward the anode. It is thus reasonable to assume that some sort of drag exists, and that momentum of the EV movement is passed up to the walls of the guide and the material associated with it. In the case of the properly sized guides, there would seem to be very little of this momentum transfer. On the other hand, when a guide is undersize, or non-existent, at the beginning of the EV firing, the momentum transfer must be tremendous, because A11 of the material in the channel is blown out of the channel in the forward direction. This is not like the case where the entire line of material is just suddenly heated and ejected both ways. The material totally goes out the door with the EV. Does the EV wait for 11% of that material to vaporize and then push it from behind? I think not. I believe the EV passes through the solid material without significant changing the EV form, and then the momentum transfer yanks the material out after FE passage. Soptapeg distortion. Clearly we have encountered a very unusual effect here, and any attempt I make to explain it will, in the main, WPG. In spite of this low probability for being correct, I'm nevertheless going to comment op one of the mechanisms think is at work here. I believe a form of radiation propulsion is induced in the EV. Changing the shape of the Pourmalus symmetrical, fierce, electromagnetic container that Rs the EV. More is said about this in the Charter on Theories. EV targets 5 to 26, Chapter 6, Strabamers. This part of the story begins one Sunday more PPG, in June 1984, in CMLS Bad, California, where I was taking some helicopter staining at the Hughes AI Craft delivery sector. I had just finished having breakfast at a small restaurant in one of the shopping centres and was walking out of the door when I saw a picture in a newspaper lying on the floor. The picture showed a clown looking at a large glass sphere with MAPU streamers of electrical discharge in it. This sphere, as it TRAPs out, was on display at the Science Museum in San Diego. It was only about 7 a.m., but I must have kept some records getting out of Carlsbad and into San Diego. I was far too early for the museum to open, but I lurked around waiting for someone to show up. Finally, I found AP attendant and got to the curator of the museum. I arranged for a demonstration of the device and also got the name of the fellow that had put it together for them. His name was Robert Golka of Brockton, Massachusetts. The characteristic of this device that immediately drew MU attention was the high aspect ratio of the streamers. They were thread-like both in the gas phase and up the wall of the glass sphere that contained them. The streamers would follow your hand if you moved it pair the glass. It made a very beautiful display of something I would hashbet mopu, Michlis, and chalk had to do with EVs. This was another ope of those intuition poits I could not let pass. The rolum I was having with the knowledge side of Mu Mind was this. I was firmly convinced that EVs oshkud at a metallic cathode and at no other place. This device on display RVA's obviously an electrodless discharge operating on high-frequency SHREPT and was thoroughly in violation of my premise. I knew of no way in the world for a gas to get the LSFOP density that I thought was required for EV formation. At this point, I just had to sweep MU knowledge up to the rug and row attention to what I was seeing. Though this time, in 1984, the 1A had been moved to Austin, Texas, and was being set up to do microfabrication technology in exotic materials. A such that is what EV work demanded. It way a HMD decision to get into this technology work, as so's such work is usually either sherry expensive or goes sherry slowly. I was trying to get ROHPD these limits with some brilliant stroke of invention when this streamer roller mareshed. The streamers offered some relief to the daily tedium I faced, and I suppose I jumped into it partly because of the fun and comic relief it offered. One of the first things I did was to go back over the ancient literature. I mean way back into the 1800s, and sure enough, the old-timers had seen it all. The problem I had with most of the publications was that the data was interpreted in terms of existing theories, and even the measurements seemed bent to fit the theories. None of what I found could be easily tied to the EV sort of problem I was working on. I am sure such data did exist, but sometimes data retrieval is harder than data regeneration. I started to regenerate data. It was back to the lab for me. Pulsed RF power supply. Most of the good parts of the lab were either still in boxes, or broken, or lost, or so I thought. My working processes are such that I will not try to do good things in a chaotic environment. I am sure that in my mind I had a definite limit on the complexity of the experiments I could do without a proper lab. A proper lab is not necessarily an expensive one, just a well-ordered one. In any event, I started making the gadgets necessary for the streamer work. The first order of business was to make an RF power supply which could be varied in both frequency and output voltage over a wide range. This turned out to be a simple oscillator using a 4-250 tube powered by a high-voltage power supply normally used for electron beam evaporation. The coils were wound on plastic water pipe, about 2.5 inches in diameter, and a range of operating frequencies from 100 kHz through 7 MHz could be covered. Most of the loads seemed to demand a very high impedance, so the coils were wound to accommodate this. In the end, I could jump a 3/4 inch spark gap in air with most of the coils. This power source for the streamer work turned out to be fairly universal. A pulsar, in the form of a grid modulator, was added as an additional feature to help determine the time dependence of the streamers formed. The magic of high atomic number. A miniature version of the sphere I had seen in San Diego was fabricated from laboratory glass apparatus and fired up with various gases and pressures. The streamers that I got were pretty good, but lacked the fine lace structure of the one in San Diego. The best gas for the effect I was looking for was argon, but it still was not great. At this point, I made an effort to get hold of Robert Gulker and ask him what the trick was. Gulker was driving across the country at that time and was to arrive in Brockton in a few days. After a while, I did talk to Gulker and arrange for a consulting session with him in Brockton. The salient point of that meeting was that krypton was used in the San Diego device, and that made all the difference in the world. Streamers 6-2, figure B, 1, Schemas B, -3. I tried krypton in the little ecorimipil setup had made. It worked fantastically well. In short time, I had gone through 11 of the parameters available to me with the apparatus I had made. Pressure, gas mixtures, frequencies, and currents were tested, and the best operating points for the cephephemers I wanted to work with were nailed down. In a short while, a bottle of xenon I had ordered had some in. It was tried with the most delightful results imaginable. The xenon streamers were finer and brighter, and they did wider variety of tricks than the krypton did. It was noted, however, that the xenon results were quickly reduced to trash, a wide variety of contaminating gases. Water, and halogens had to be eliminated from the experiment. These electronegative gases, RF, gobbled up 2 MAPU electrons, a new glass jar. I quickly reached the limits of the simple apparatus, made Rimarillo for emptistic puposes, and had to fabricate another piece of apparatus to carry out some new tests. D-sketch of this apparatus is shown in figure 6-1. The outside container, a Pyrex glass cylinder, had end plates attached to it with Iroku cement. There was also a small glass cylinder cemented on top to hold a witness plate electrode. One technological advance that was necessary with this otherwise primitive piece of apparatus was a fused silica tube to isolate the scepter electrode, because the rotor loading on the rake tube previously used was too great and it would melt. It also proved desirable to put aluminium wool at the end of the center electrode to help distribute the electric field inside the fused silica tube. A glass stopcock was attached to the side with Iroku cement to allow pump down and gas admisi up. In operating this apparatus, the chamber is first evacuated with a roughing rummer. Then, the gas mixture 2E used is admitted, and finally the stopcock is closed. There is only one electrode shown in the sketch, because the other electrode is provided U-capacity coupling to APU objects pair the outside of the cylinder, or end sutures. This variable coupling effect allows a hand to concentrate fields as it moves occur the surface, producing some nice confol effects. GO photos. I apologize at this point for the fact that there were no photographs taken of the work that went on during the streamer period. I think the one reason for this omission is that kept thin. This is the beginning of something that will finally be worth doing. I am fairly often dominated. This HND of thinking in the beginning of a peaked. If the piect is okio before it gets complicated, there Maui no material to publish. Streamers 6-4. The practical side, it is hard to do justice to these beautiful streamers without solar photography. Whatever the causes, there are no photos. The effects produced, these streamers are so incredibly beautiful that anyone even partly interested in the feed realu needs to have his own apparatus to rallow with. There are so many effects to be seen in this apparatus that it would take a separate book to describe them. I allude briefly to mapu of these efficacy, concentrating opthas that bear on the most obvious EY questions. In order to concentrate the data further, I tabulate some of the observations and then give a brief interpretation as to what I believe caused the effect. List of effects seen. 1. At a relatively high RF dye factor and gas pressure, Osha out 1/5 G atmosphere, very fine streamers seem to form pesh the top and sides of the scepter electrode, toward the center and top of the elastgode, and knit themselves into a rope of brilliant blue-white light that then leaves the electrode to rise lazuli to the top surface of the container, whereupon it terps with a small radius and spreads out ochre, the glass surface, as myriad riches of tigged flowing across the top, and then down the glass cylinder, finally to subdivide themselves into oblivion. View of what is happening here is that the EVs she created use some yet unknown process, possibly involving secondary emission and electronic ramming, or shock processes, to momentarily increase the electron density, or pressure at the fine streamer points, and then unite, like they always do, but in a fashion greatly attenuated, the ion sheath, SOVA, PG them. The spreading on the surface is due to greater attraction for the surface than for other strands in the LMGE, loosely knit filament. The final subdivision occurs when the field is reduced to a low value. 2. At high pressure and dye factor, there are definite convective effects to be seen in the Ströcklimeri moving in the gas phase. 3. At high rower settings and high pressure, the streamer forms into a strong-looking roar on the glass surface that writhes out in the shammer wrapping itself about whatever it sap in serpentine fashion, but being careful not to complete a full terp. 4. Low pressure produces several small independent streamers from the scepter electrode which get smaller in diameter and brightness as the pulse width is reduced. Each of these independent streamers mosh toward the outer cylinder in a direct radial line without uniting. I believe that the diameter of the visible streamer is a reasonable measure of the pummer of EVs in the streamer. Under the stated production conditions, there is not enough time synchronization or spatial coupling between EVs to unite, and so they remain IP independent. 5. Even at low pressure, there is a tendency for the path of a new streamer to follow the path or ionization trail of APOID streamer. This effect can persist for up to L/second between streamer firings. Streamers 6 to 5. 6 A11 streamers on the glass walls can be attracted to and guided a finger placed on the outside of the container. This is just a way to concentrate the electric field.
7.
When a well-formed SF femur is observed closely, It is SEEP2E ruptured when a finger or electrode is brought pair the streamer path, the sheath, and part of the core appear to be deflected away from the electrode, and the interior of the streamer yields several bright filamentary objects that attack the glass at the electrode point. Believe these filamentary lights are either the ionization trail of individual EVs or a very small pummer of them. 8. Banding and intense spots of light can be seen in cephemas that hash been abruptly terminated or disturbed. A gross object. These spots are stationary as long as the impediment is stationary, but move when the object causing the reflected wave is moved. Believe this is just another ephemeral of a wave repomp pop that may be similar to the one rorosed during the creation cycle. First 9. Several RF cycles she required to start the discharge, and the higher the amplitude of RF, the shorter the starting time. 10. If the top plate is viewed from the side, so as to optimize the end view image of streamers running up the plate, high-intensity flashes SAP is seen coming from these end views as they scan the detector. A scintillating image is seen on a piece of white rarer held in the viewing rape. RF, there is a high-intensity and NU-TO angle light emission directly ahead of the streamer that is produced, the EV within it. It is easy for me to believe that the ionization produced, this light, is responsible for guiding the EV that follows. 11. Most small sphemi prefer to rup straight on the glass surface, but will abruptly deflect when they epsuter a small imperfection op the surface. The imperfection that causes most of the deflection has been found to dielectric in nature, and would make a good miniature mirror for the light running ahead of the streamer. This guidance technique can be used to focus individual EV streamer strands into a wide variety of either 2- or 3-dimensional patterns. 12. When a well-developed streamer is attracted with a finger, or other grounded electrode, to a rotitial rays on the container wall, the streamer is terminated there as a disruption into a lot of smaller streamers. The final disruption point is often preceded, a sinuous shape resembling a meander pattern in a richer. The stopping action is seen to force a bulge in the main streamer, rodusip g mapu small streamers laid side each, extending for short distance and then reuniting into ope streamer again until final dissolution. This behavior is just a pother example of the coupling action between EVs when their couple PG is attenuated, the sheath or I streamer. Stream F66, witness plate tests. With this streamer work, I had set out to show that they were somehow associated with EVs. It just looked like they had to be, judging by their high aspect ratio. The witness plate would be an adequate proof that whatever was in the streamers was also what I had been calling an EV. A simple test would be to allow the streamer to hit a witness plate and see what was inside. The first test of this was to put a copper grid with a chromium film on it on the witness electrode in the apparatus. This was done, but the streamer just sailed past the electrode without seeing it. It was necessary to make the electrode more attractive to the streamer and to break down the protective sheath by adding a small wire to the electrode to increase the capacity. The result of this test has already been shown in the last chapter in figures 510 through 513. Without any doubt, the streamer contains something very corpuscular in nature, not splattered material. It is difficult to admit that many of our electron and plasma streams have such charge granularity, and alternative explanations are often sought. One of the handiest explanations is the splattering of material from the cathode, or elsewhere, that somehow makes its way to the target. Never mind the uniformity and apparent low mass of these pieces, they must be the culprit. I have run into that argument often, but the electrodeless discharge used here shoots it down. The electrodes of this system are not eroded, and there are no particles thrown from them. The fact is, EVs are somehow formed in the system, and the witness plates tell the correct story. We can have lumps in our beams. No cathode spots. Another argument that could be raised against the existence of an EV is that we are really seeing cathode spots, or the formation point for a disruptive discharge. It is not very likely that these discharges would originate on some of the thin film targets with smooth surfaces, which have a negative radius of curvature. It is also very hard to explain how a cathode spot could be formed on another electrode past our main thin film target, or how a carbon film could be dented by the formation of a cathode spot. I cannot see how any of the cathode spot arguments hold water. EVs simply exist as an entity of high charge density, and that makes things a lot easier to explain. Streamers 6 to 7. Ubiquitous. As I mentioned in Chapter 5, it is not necessary to go to our particular trouble to reduce the EV strike mark from a discharge. It is necessary to allow the spark from some high voltage source, such as a Tesla coil, to hit a metal surface in order to produce the effect. Photos of these effects are shown in figures 5, 7 through 5-9. I have the impression that history may resort our understanding and use of electronics in a way that is similar to our description of fluid dynamics. There will be the time before the discovery of EVs that is equivalent to the Lamin flow regime, and then there will be the time after their acceptance that is equivalent to the Fourier-Lept regime. Long and short EY sources. Even though there are no photos of the streamer work, there is at least one residual effect that lingers op. The work had taught me to look for electrons that come from some source other than a metallic cathode. This source would be sparse and stingy with electrons. These electrons would have to come from diverse sources, such as gas that was recently ionized or secondary electrons generated from the Peshu dielectric surfaces. If this were the case, there would have to be a returp current, or Resolu function, that would allow the sources to recharge at rates of at least 30 MHz, the highest frequency used up to that time. A11 common sense rebels at the thought of electrons somehow getting together and forming the thin channels needed to concentrate the electrons to the critical density level required to esm AP-EV. Most ordinary knowledge shows a branching out and scattering of electrons from a point during an avalanche process. Of source, there are devices designed to recept this, such as the Chappell-Eelstrop multiplier, but there were no such physical process evident on the surface of a streamer EV source. What was going on here? I had put MU time in on devices such as electron multipliers, so started going over A11 of the mechanisms I could think of to produce a cascading process for Illustrop production, U secondary emission. There is the old Farnsworth RF type of multiplier, in which two plates with AP-RF applied to them can multiply, and there is the well-known multipactor process for causing breakdown on dielectric windows in the presence of microwave energy. I had also been privileged to work with a mirror microscope and watch the charge distribution on dielectric surfaces that is nothing like what one would Pormalu think. The patterns of charge Moshe around in raft-like fashion and produce Mapu Somrelek returps, some of which could be construed to be filamentary in patcher. Whatever the truth of the matter, I began to see the possibility of a long EV-E source that got its electrons from a more gradual charge build-up, electrons hopping on the surface in the presence of the applied fields, and, through secondary emission, slowly reaching the critical level for EV formation. This long process is a low-intensity one, and does not greatly task the materials at the source I, do the short metallic sources that are sarilla of supplying A11 of the emission in a short time, and in a short physical space. Streamec B-8. As I looked further into the question, where does OPE get the Eelistrops for the process of EV formation to begin? I noticed that the range of gas precyclers that best serve the formation of streamer IA EVs was such that the electron MEEP-free path was around the magic 20 misrometer rapch. This is the size rapch for good Chappell guidance, the size rapch for some garden variety forms of EVs, and incidentally the rapch of diameters for cinder channel electron multipliers. A lot of things were coming together that could meep a neat EV source, or at least help me explain why gaseous streamer sources did what they did. With these notions in mind, I was about to bet that gas did not play any fundamental part, and that nearly a resistive dielectric material could be made to satisfy the instantaneous Eelistrops needed to form the EV, and furthermore, that the resistive component sold recharged the depleted phase. The design of a somewhat placid Ard soft yaws for EV generation was coming into being. This proposed source looked somewhat less efficient than the metallic ones, but RAS it would have its rays in the systems to some. This sounds very mystical, I am sure, but as it turps out, things did finally fit together. Streamers 6 to 9. TT1 2J11 it. Chapter Sevi Prevelii. Walches. Are they OG, arpet they? If there is anything Appy Ev can do, it is travel. In fact, I have Petra seen one sit style. Indeed, one of the most damning arguments against their very existence as an entity is that they do not seem to exist at rate. They behave like a soliton. Sap, almost imagine a region of space, charged with energy from the applied potentials, PBG like a fuse with the ignited Rorschach up the EV. I cannot answer A11 of Moo questions about their behaviour with this analogy, but there are enough answeb to cause me yom uneasiness. Nevertheless, to go up with this business it is necessary to take one view at a time, and for PW Moo view is that somehow they are an entity that SAP work with. It is also Moo view that the only reason I hash not seen them at rest is that they must move to generate electrons from their surroundings to feed their unstable state. Perhaps someday I will see a well-fed and undisturbed EV at rest. I Sipsorelu believe a black EV could, get brought to rest, and still exist as an entity. We shall see. Self-synchronization. Ever since I first, Asami convinced that EVs were discrete charge entities, it had EP on Mu mind to find a way to circulate them or to guide them in synchronization with a travelling wake. The priority of that work was Petra high enough to actually begin it, until the streamer work made it slesh that this would be quite reasonable isk to undertake, because of the absence of dielectric charging effects. I have always thought of an EV travelling on surface as a kind of self-synchronous repom-pop, in which the charge op, the surface was depressed, the passage of the EV. This is a form of RC relaxation process, and is not very efficient for high power handling, so I do not count it as a travelling wave effect of Apu merit, because the recharge time is either too long or has too much loss for practical use. The kind of circuit that was indicated for practical use is the well-known LC class of devices, such as the helix or coupled resonant circuit delay line. Circular, UY, LiPeg motion. In the beginning of this Ratesolch travelling wave work, the aim was to circulate EVs around a diameter of about 15 inches, using an RF drive in the 30 MHz wrapped to supply the circulation losses. In order to unearth some of the laws of this domain, I thought it wise to start with a straight section of delay line in order to unearth the injection and propagation 1AWs before getting into the circulation problems. This less ambitious Arrow Y also dictated the fact that the new Resesh laboratory had not been set up. Arrow 1 was constrained to work under conditions that were far from good. Delay line. The first order of business was to fabricate a delay line on a glass tubing that would hash delay concitant with measurements using our oscilloscope. Since the scope had a rise time of about 3 nanoseconds, it was appropriate to make the delay time at least 1 BNs to get away from interfering effects caused the EV source firing. I wanted the smallest diameter tube that I could get without unduly complicating the attachment of fittings to the end, or making a unit that was so fragile it could not be handled. At this point, I was getting most of the actual thing-making on the project done. Relatively new, and Epecrieps real in the laboratory, and this greatly limited the complexity of the technologies available to me. After a short time, a piece of 3 mm outside diameter glass tubing was wrapped with a coil of wire that gave an impedance of 200 ohms when used as a delay line, with Irasitu loading to ground. Since I did not have a pulse generator with a short enough pulse-rei time to test the delay of the line, I threw together a spark source to generate the necessary pulse. The line gave 1 BN's delay for 11 inches of winding on the glass tube. The architecture used in this experiment is described in more detail in Charter 8 in the section Optra-Velip waves. Length limitations. I did not have any experience with long path length for EV guides except at high voltage, and the use of high voltage way not thought to be desirable. The compromise length of about 1 foot for the experiment was deemed to be a reasonable value. Actually, the source characteristics determine the operating voltage more than does the length of gas guide that follows it, but for the next few months we would be locked down to 1 foot, just as we started that way, and had some initially good results. Seeing this lock-in effect is usually a wagpie PG to me that I am losing MU flexibility, but during this period of warm with others I had necessarily given up some flexibility. Travelling waves 7 to 2, EVT Tiernan. On August 13, 1984, the EV travelling wave tube literally flew off the drawing board. In spite of the complexity of all of the interacting elements of EV generation, propagation down a delay line, and catching both the EV and the travelling wave, everything worked the first time around. The experiment literally seemed to turn itself on. This is one of the nicest feelings a designer can have. Some of the parameters used in this experiment were these. 1. The EV source was a mercury-wetted copper wire. 2. Xenon gas pressure in the tube was about 3 torr. 3. Pulse input voltage was 600 nanoseconds width at 1 kilovolt through 1,500 ohms. 4. EV target voltage was 0 volts. 5. Load on the delay line was 200 ohms. 7. E firing rate was 100 pulses per second. The results of this first run were these. 1. Output voltage from the delay line was negative 2 kilovolts. Clear be seen on the target electrode. 2. Output voltage into the target was negative 60 volts. 3 EV strikes could. 4. A faint purple glow could be seen in the tube. 5. When a positive voltage was applied to the target, visual EV streamers could be seen for the last centimetre of the EV run just before a strike. 6. Load on the target was 50 ohms. Waveforms. The waveform out of the delay line was a function of the gas pressure, as was the length of the tail on the pulse. Basically, the pulse was a sharp negative pulse of about 16 nanoseconds in length, followed by a lower amplitude, flat, topped pulse that had a length of virtually 0 under ideal conditions. The maximum length of the trailing pulse was linearly related to the gas pressure. The higher the gas pressure, the longer the pulse. The longest pulse I allowed to develop was about 1 millisecond. It would appear that the length of the pulse was also a measure of the travel time for the EV from the source to the target. From these measurements, it can be deduced that the EV lived for a millisecond at high gas pressure because the strike mark could still be clearly seen. During such tests, the pulse repetition rate was cut down to just a few pulses per second to allow clearing of ions between pulses, travelling waves 7 to 3. When the system was warn guessed for high output voltage on the delay line, the gas pressure was minimum. As the pressure was being reduced from some high initial value to the lowest value that would sustain the EV generation, the voltage output on the delay line steadily rose to its maximum value. At the lowest pressure point, there was only the IPGT high-value negative pulse of about 16 nanoseconds in width, with no lower amplitude dill on it. This observation of getting maximum output at low gas pressure is consistent with the streamer data obtained earlier, which showed there is an effective shielding action on the EVU, the ion sheath around the EV. At the lowest gauge pressure, it could be easily measured that the total time delay from EV firing to aricol at the output of the delay line circuit, about 0 foot away, was equal to 1/2 the velocity of light. This data is fairly strong evidence that the charge travelling inside the glass tube along the delay 1 ein was largely composed of electrons and was roughly in synchronization with the watch on the delay line, thus qualifying for legitimate inclusion in the 1ist of travelling watch devices. Multiple eye-gep ratio. At times it was possible to geparate McKelfel EVs, a process not specifically designed into the system. One of these processes produced 2 distinct EVs from a slight overshoot of the driving pulse watch form. The ringing time of the pulse generator was 600 nanoseconds. An amplitude of only 70 volts produced EVs with the same characteristics as the main EV generation method. This is the truth with gas systems. They often contribute things that have not been asked for. I liked the low-voltage generation processes, but it was not realu up to mu control. I suppose the effect arose from a plasma weight or something similar, and since I was eventually going to get rid of the gas, there was no use in optimizing the effect. Statistics. From the preceding data, it would seem that we had perlu everything we needed to go ahead with the circulation picked. Wrong! What does not show is the way we had to fight and scratch to get back eschaprap of the initial results op subsequent tries. I have often heard of something like the law of the Rhymery Maximus, which stated, if at first you succeed, oo petcher will again. I sure had a rhyme example of that law on Mu hands. We tried turning things off and then back on again. We changed EEY sources. We changed gas pressure and the rise rate of the pressure. We changed turp cycles to help slash out any charge that mau have remained op the wall one from previous NRNs. We cut pulse length down to 15 nanoseconds op the evidriture. We did this not for a day or so, we did this for weeks. At the end of weeks, we made new apparatus with different dimensions and went through the same rituals with different incantations. Travelling Waves 7.4. To give the reader a feeling for the variations encountered, the input and output values would range from the best values shown above to needing 3 or 4 kilovolts to fire off the EV and then getting only 400 volts out of the delay line. Since power in the circuit varied with the square of the voltage, we were being hit by an effect of the first order. The only thing that was consistent was the 60 volts output on the target, but that did not matter since what we wanted was the output from the delay line. Down in size. In an effort to get away from some of the geometrically controlled effects, we went down in size with the entire apparatus, even though it meant more difficult construction techniques would have to be used. A small ceramic tube with an outside diameter of 1/32 inch and a length of 4 inches was made and fitted with the same kind of accessories as the larger unit previously described. We also went to a lot of trouble to make a special source, described as an EV launcher in Chapter 8. This source set the record of 200 volts for low-voltage EV generation and launching in small tubes, but did not get rid of the vagaries in the operation. In this small apparatus, the input pulse was still driven through the 1,500 ohm current limiting resistor, but the delay line impedance and load was lowered to 170 ohms. With all of these changes, the results went from rotten values such as 1,250 volts input, with 240 volts output, to slightly interesting values of 1 kilovolt input for 450 volts output and 2 kilovolts input with 900 volts output. There was just no greatness to be found around here. Stress. The characteristic of the variation was what gave me such a bad time. When the particular run worked, it worked pretty well for a reasonable length of time. But eventually, something would happen. At times the cathode would shift its operating point and that would end the good results. At times the cathode would not change and something else would happen, such as a charge change on the wall, and that would throw the operation off. Of course, we coated the inside of the tubes with resistive material, but that was not the trick. We tried all normal variations we could think of within the antique technology that was available to us. None of these things worked. To say the least, I was highly stressed. I was bent way out of shape by the group effect that forced me to work steadily and not jump around a lot, as I am used to doing when I work alone. I do not even like someone to know what I am doing when I work, because they might ask what happened to the last thing I was working on. Normally, in the period of a day, the last thing has died, and so have several other schemes since the first time I saw the Inquisitor. I'm willing to bear the onus of behaving in this way because I have found the methods I need to solve problems and break barriers. On the other hand, it is difficult to work these methods into a group action without causing trouble within the group. Travelling Waves 7.5. An additional stress producer also occurred at this time in our operation. It came in the form of Bill Church, suddenly becoming a person acting more like a chief executive officer than the good old Bill, scientific log jam buster, whom I had known for 7 years. Perhaps the acquisition of a small tribe triggers off this authoritarian response. This new development set off some waves that really stopped my motion for a long time to come. Wrap up! This phase of the TUT work ended without a satisfactory technical conclusion. After more time goes by, we may look back and muse that premature termination was caused by political intrigue or the like. My claim then was that the technologies used were not up to the task. Perhaps some people can bash their heads into the technological wall every day and get the job done, but not me. What happened is that we slowly started ambling down the road to technological improvement by going into film work using thermal evaporation of metals and dielectrics. Photolithography was to be our shape-defining technique, and we would move towards smaller structures, the natural realm of the EV. Looking back on this phase of work from my present vantage point, I can see a host of effects that would produce the spotty results we got. One thing I had failed to consider at the time was that the EV is a known periodic structure, composed of bead chains with a defined spacing between them, determined by parameters in the source and the following purifying train. This periodic structure was interacting intensely with surrounding periodic structures in our apparatus. We were deeply immersed in coherent interactions that are capable of constructive and destructive interference, and we had no control over the fundamental parameters of the process, such as bead chain spacing. I am glad I quit fighting traveling waves when I did, even though quitting made me look pretty bad at the time. I should have trusted my intuition and quit sooner instead of dragging out the process. Traveling Waves 7-6. Chapter 8, Components and Devices. In any discussion about EVs, a question that always comes up is, what good are they? Meaning, what kind of gadgets do they make? Here are a few things I believe about the use of EVs, although at this point the statements may be somewhat speculative. However, statements being speculative never deterred me before. In this discussion, it is not easy to separate components from more complete devices, so this chapter has a mix of the two. EV sources. EV sources are the second most difficult aspect of the entire EV field. The most difficult task is knowing what the EV itself is. If we knew exactly what an EV was, we could better accommodate its generation and use, but for the present I must be content to generate them, using the few experimental guidelines that have been developed. I hope that someone else will gain, from this chapter on devices, a little more insight into EV formation mechanisms and EV use. As stated in Chapter 6, at this point in time there are, in my mind, two broad classes of EV sources. There is the short source that is characterized by a violent eruption of material and intense plasma production, or at least intense electron emission from a field emitter. And there is the long source that is gentle, although probably somewhat less efficient. This long source was first seen in the streamer work, where EVs seem to come to life as microscopic threads on a surface in a gas discharge with RF power sources. Since the short source was known to me first, I will describe it first. Basic firing sequence. I will attempt a basic description of the sequence involved in forming an EV from a short plasma source, but since I do not know just what that really entails, do not expect too much from this explanation. Also, I will not repeat many of the fine descriptions of cathode spot and arc initiation theories available in the literature. For an enlightening discussion of what goes on during the first few picoseconds of an arc's life, I recommend Messiaat's, 1982-1983. I think his discussion bears heavily on what happens during the early part of the formation cycle of a short EV. As the electric field is raised at the cathode, liquid metal is drawn up into a sharp Taylor cone, and a point is finally reached whereby field emission first occurs and a runaway process commences. This process requires some gas to be present beyond the cathode, or to be vaporized from the cathode by heating the cathode with the emission current passing through the cathode material. The electron emission ionizes this gas, and the charge separation produced enhances the field at the cathode. The process then regenerates, as quickly as thermal and material supply sources allow, until thermionic emission also comes into the process by heating from particle collision and back bombardment of the cathode by ions. This is a very complex process. It is a wonder that anyone has figured out anything about it, even if it has taken over 80 years. Components and Devices 8.2. The birth of an EV, and then a miracle happens. Somehow out of this mess an EV emerges. If there was ever an example of how order is created out of chaos, this is it. I have not been privy to the finest details of this birth because it is a deep, dark secret, veiled by a high density of particles moving like mad hornets around a despoiled nest. What I have seen, by observing from the outside with an electron camera, is an EV emerging from the plasma cloud. Some of the observations were discussed in Chapter 4 and shown in Figure 4.1. At first, it shines through the cloud just enough to see its outline. At this point, it obeys the law of its mother plasma and moves as if it were positive in polarity. When it finally moves beyond the moors of the womb and cleanses itself, it has become an entity obeying the laws of the electron. It is a magnificent birth cycle that can be easily repeated billions upon billions of times. One day I will probe further into this little miracle, but for now, I must be content to use the offspring in some mundane fashion. Components and Devices 8-3. Figure 8.1. Components and Devices 8-4. Metal vapor sources. As a general statement about short sources that can be fired repeatedly, it can be said that a migratory conductor is needed on a conductive substrate that has a field-enhancing shape. As a simple example of this, consider a mercury coating on a sharpened copper wire. Most variations on this basic scheme are just ways to help along slightly deficient properties of material migration, return evaporated material to the source, keep the field producing structure sharp, or help reduce ionization time to promote faster firing of the source. Figure 8. One shows some examples of geometries that help accomplish some of the desired results. All of these sources are designed for EV emission from a specific point, but area sources are also possible. Although it is convenient to operate at room temperature, it is not a strict requirement of this type of source. A source operating at around 600 degrees centigrade was made by starting with a carbon cathode, reacting titanium with the carbon, and then wetting aluminum to the titanium carbide. This source worked very well, but of course there is a huge energy premium to be paid for operating at elevated temperatures. Components and devices 8 to 5. EV surface source, figure 8.2. Comparing APD device 8 to 6. Sugfe sugs. EV use often involves guiding them on, or pish a surface, and this requires coupling them from the source to the surface. In the previous uses described it, is possibleo locate the source, a small distance from a propagating surface and have them work well, but the device described here is IFREP coupled to the surface and guide. The basis for operation of this source stems from the fringing field lines at the edge of the cathode that causes a sharpening effect on the mobile syode metal used. D-drawing of the use is shown in figure 8. 2. A referred embodiment is to use alumipa substrates and aluminum oxide film coverings, doped with tungsten, to make the channels for EV guidance. Evaporated molybdenum has been used as a lead wire material, with mercury added to the molybdenum surface, U-ion admept. Mercury and molybdenum do not have a high solubility. For this reason, it is referable to add an intermediate mavriol, yuck, as nickel, to increase the LDPG. Sora and silver are too soluble in mercury for use in film circuit, as they can rapidly dissolved away. A flat cover plate op the channel can be used with this configuration. It is necessary to coat this cover plate with a charge-dispersing material such as doped alumipa to prevent channel charging. Components and devices 8 to 7. EV launcher, figure 8, 3. Components and devices 8 to 8. EV launcher. In contrast to the surface source just described, it is sometimes desirable to launch an EV into space or through a gap before it enters the guide region. This SAP accomplished with the device shown in figure 8.3. This configuration uses a liquid metal cathode op the outside of a ceramic body. The ceramic is shallow pointed at the end that is intended for launching an eye. The anode of the EV generator is applied inside the ceramic, with special shi being used to carry the anode past the end of the cathode region. In MAPU ways, this source is similar to the OPE previously described in that the mobile metal is drawn to a thin REPG at the end of the cathode, nearest the anode. Firing can be seen all around the cathode region taking rays in a time-sharing fashion. At high pulse repetition rates, there is a steady glow around the cathode end. The extraction voltage applied to the EV guide is an inherent part of this source, and without it, the source will not fire SOREF. The extraction voltage is por malu, the ground potential of the system when the cathode is RUP at some negative voltage. When a wall thickness between Fe cathode and a node of about 0.003 inches is used with the source shown, AP EVSAP, formed and transferred to the guide, when the cathode pulse is as low as 200 volts. Low pressure gas in the guide is necessary to achieve this operating voltage. Ipogapis gas source. As with the 11 attempted to generalize, MAPU effects seem to fall outside the list of general rules. For a Cumral, the yaws shown in the Onauer right Sorper of figure 8, one does not use migratory conductor deposited on a field-enhancing conductor. This source also has shorter life characteristic than the other sources. The titanium hydride is a regenerable metaone that the hydrogen can be put back into, but there is positive Rechart path or no ray-1 flow of material, so after a period of use the active material in the cathode disperses, and the source fails to fire. L. Components and devices 8 to 9. Electrodeless EV source. Figure 8, 4. Components and devices 8 to 10. Orgapis gas sugzes, another acameral, mentioned in an earlier chapter that falls outside the strict definition of short source, would be the nitroglycerin-wetted metal cathode. In this case, the OPLU reason for nitrating the glycerin was to impart some conductivity to the organic material, U including acids, and this was a very artificial means for doing so. Same holds true for sodium iodide-doped glycerip. As long as the quantity of non-conductive material is kept to very thin layers, it is not necessary to dope for conductivity. Polarization of the materione is sufficient to move it in a field, and this can act as a rummer to get the material to a field-enhancing tip. As mentioned also in an earlier chapter, the reason for drying organic materials of the nitroglycerin class was to see if a gaseous uridust of the mobile material could be found. Without going into one OPG life tests, it arreshes that most of the residue of the Orgapis explosion removes itself from the area of the cathode. In this class of experiment, it is necessary to limit the peak energy to rechept cathode damage. Elect godeless source. During the work on travelling wakes, described in Chapter 7, there were a lot of variations tried to test the feasibility of using a high-pressure source regiop for the generation of EVs, while at the same time using a low resif in another region where the travelling wave circuit way operated. Figure 8, 4 shows one of the structureger reasonable performance for this mode of operation. The RF voltage used to generate the EV was applied to the short end of the enclosure, and the EV was taken out through the arafure. An armature as small as L2 of an inch was used, and the EV still one went through. The smallest size armature is desirable from the signed point of the pumping sarasif needed to keep the low pressure ejection operating rory. This source was made of alumipum oxide and metallized with silver where the electrodes were needed. Although this source produced nice EVs, it was not used in the 2T applications, as of the need for constant pumping. For 1-arg rower applications, where there is no objection to pumping, it is a moderately efficient source. EVs can be generated with as low as a few hundred volts applied. Components and devices 8 to 11. EV separators. Figure 8-5. Components and devices 8 to 12. Serrator. In most plasma work, it is not very easy to yee the effects of an EV because they are obscured all of the ions and disorganized electrons. This RO-LEM sap is greatly reduced, using a cover or doghouse occur the plasma source. The EV sap is led out of the enclosure, using a small guide grooch or asher placed somewhere up the way to the anode or ectraster electrode. Figure 8-5 shows 2 beacons of this device. The OP on the left is essentially a cylindrical ceramic piece with a smale hole in one end. This ceramic nozzle contains a cathode, for a cameral, mercury-wetted sora that created the plasma dishimge and heps the EV. A thick film tip of separator is shown on the guide, and this OP has typically EPAP alchmictum oxide base with silver fired op it. Mercury is wetted onto the silver. Components and devices 8 to 13. Figure 8-6. Components and devices 8 to 14. Operating circuit. There are a few general rules I have followed in operating the short sources. I attempted to limit the peak energy at the cathode to a value just high enough to generate the EV I want. The usual way to do this is to put a current limlin resistor near the cathode circuit and raise it as close as possible to the EV sockets. When this resistor, SAPI, made an integral part of the EV source, firing the resistor into the ceramic material comprising the source, the results are better for long life. D resistor value of between 500 and 1500 ohms is good for laboratory work. Figure 8-6 is a typical circuit for using an EV source. With direct, SREPT or pulse rower supplies, it is necessary to complete the SREPT flow path around the 1 ore, and this entails using an anode of some free to collect the EV. What is shown in Figure 8b is a configuration that requires gas in the glass 2E, if a long path length is used at 1 UBU voltage. This is basically the EVTT device without the delay line wrapped around the glass tube. In other applications, the glass 2 can be replaced a guide of another type, and Chariox circuits devised to take advantage of the EV properties. Pulse duration effects. A second guideline for firing short sources, one that is not EEP accurately quantified, applies to liquid metal cathodes where taller cone formation is at work. This guideline states that it is necessary to factor in the length of the applied pulse. For direct, SREPT, and very long pulse applications, the applied voltage is somewhat lower than for very short pulses. Presumably, the metal requires a finite time to migrate to the tip of the cathode, and this delay gives rise to the pulse length sensitivity. Even with this delay, pulses as short as ns have been used with mercury-wetted sorroyorses, with OTST raising the voltage more than a factor of 2 over that of a 600 nanoseconds pulse. Field emission EV sources. The field emission EV source is one that definitely falls into the short EV source class. But this source does not have the limitations on lifetime, because of source material dispersal, that the liquid metal ones do. There are special requirements, however, that will limit the utility of this class of sources to complete EV systems having considerable complexity. This was also the case with individual field emission devices used in conventional electronic applications and described U-shoulders, 19 bone, 1965. One device cannot made and put in a can, and sold because the energy storage of the leads alone would destroy it when operating voltage was applied. Components and devices 8 to 15. The RIP cell requirement for generating an EV is to suddenly have a very high uncompensated electronic SCHE in a small cholkme of space. This implies AP emission processes coupled to a fast switching process. In the previously described phrase of EY generatory, the switching rosacea from the non-linear action of gas ionization, and rare has some electronic gram effects. If it is desirable to eliminate all gas and migratory material from the system of EV generation and use, then pure field emission can be used if a fast switching roses is provided and coupled to the field emitter in shush, a way that emission can switched up and then off again before the emitter is heated to the evaporation point, elastropis conduction. Risserolsa. The field emission EV source just discussed uses field emission operated in AP emission density region, beyond the range Pormalu used for other devices, pulsing the emitter up and off very rapidly. Since the thermal time constant on the emitter is shorter than 1 picosecond, it is convenient to use Eve-Drishop pulse generators. A pair example of such a pulse generator made from fairly large components is shown in figure 8.7. The overall dimension of the picopulsar is about 0.2 inches. Componenty and devices 8 to 16. Pulse generator. Figure 8.7. Components and devices 8 to 17. Figure 8.8. Components and devices 8 to 18. An ecameral of the picopulsar coupled to a standard field emitter is shown in figure 8.8. In use, an EV is formed in the cathode region of the enclosed liquid metal generator. The EV is then extracted, applying a positive voltage to the extractor elastcode. Upon stref ng, the extractor electrode, a powerful short pulse is generated and capacity coupled to the pulse foot electrode. This electrode has a bias electrode attached to it, and can be used for setting bias voltage on the field emitter. The resistor coating on the Rimaru EV side of the ceramic disc is about 0.01 ohms, and the coating on the field emitter side of the disc is about 1 megohm. With the electrodes available in this apparatus, MAPU high-speed effects, SAP, investigated. If the output from the pulse generator is kept low in voltage, and a sensitive detector used for detecting emission from the field emitter, it is possible to measure effectively very short pulse voltage amplitude, a substitution technique using the high-speed rectification ability of the field emitter. Bias voltage is simply substituted for the pulse voltage. INQOF into the state of the field emission cathode can also be made with this apparatus. U-terp PG off the pulse generator and looning at the emission pattern op, a phosphor screen. This is a very versatile piece of apparatus, and a lot of measurements can be made in difficult region of voltage and speed. At higher levels of pulse voltage, far into what is usually thought of as the space charge saturation region for the field emitter, the emitter generates bunches of electrons that resemble EVs, as detected on a Peru witness plate. Very little work has EEP done with this class of Jeparator, but on an Eshlu and primitive piece of apparatus, this type of source produced smaller EVs than has been discussed in the chalka of the work here. These small 1 EVs are potentially very useful for specialized computer-like applications using Sheke itering. Film field emission EV sources. Figure 8.9 shows a geometry amenable to film techniques, and Figure 8.10 shows a block circuit diagram for operating the film type of EV source. This type of circuit is the first short source introduced here that completely gets away from liquid metal use. In this sockres, the switching process is carried out, feedback, on a time scale that is consistent with the thermal processes in the EV generator. It is necessary to switch the emitter on and off in less than 1 picosecond to reach cathode destruction. The feedback shown in Figure 8.10 is a generic free of phase Ipcherter and Sapie transmission line or anything that produces a differentiating overshoot with time delay. The main point to made here is that the speed must high and the size is accordingly small. In a later section in this chapter, pulse yochus will be described that is based upon using a slot in a counter-electrode below guide to produce short pulses of both positive and negative polarity. Components and DVIGs 8-19. Field emission EV source, Figure 8.9. Components and devices 8-20. Field emission EV source circuit diagram, Figure 8.10. Components and devices 8-21. Multi-electrode EY sources. As a logical extension of the film, sockets just shown, Figure 8.11 and Figure 8.12 show multi-electrode EEV sources based upon field emission that is also free of liquid metal emissions. This type of geometry is used when it is desirable to maintain a fixed cathode and anode potential, while at the same time being able to generate an EV from some other control potential. The EY launcher discussed earlier is a specialized form of multi-electrode source, and in any of these applications, a phiode or tetrode geometry can be used. VU analogy to chasium tubes, a triode is simply a control electrode interposed between the cathode and phi anode. As with all control electrodes in any device, there is a degree of interaction between the control input and the output. The tetrode geometry tends to minimize coupling. The sketches shown here show only illustrative of the wide class of devices available, adequately described in the literature for other Rutzroses and Adariel to EV technology. Long sugses. There is still a mystery surrounding the detailed mechanisms at work in a long source for producing EVs, although long sources are much more open and available for analysis than the short yours. What errory to be happening is that a simple electron multiplication process takes raise up a surface under the stimulation of an applied field. The growth and accumulation of charge finally reaches the 1H1, where the containment process, whatever it is, produces the powerful convergence we call the EV. Nothing could be simpler in Ripsol, but there are still MAPU unanswered questions. The gas roll. Upper flat, secondary electron-producing surface, with an applied field along the length dimension, one would naively expect a cascade of electrons to diverge and show a fanning-out effect because of scatter, surface charge, and space charge. This is evidently not the case with a gas such as xenon available to the surface. The gas is useful, if for no other reason than that it allows OPE to see the ionization of the gas, the path of the electrons in minute dione. Fluoresceps of the surface can be seen too, but gas is better. What is seen is that the trails of ions, and presumably electrons, are convergent and not divergent. The process at work here is somewhat obscured. The fact that RF and not direct SUREPT is used in this IA of OREP surface test, and the returp SUREPT ion sheath MAO play a key role in streamer formation. An interesting observation made with gas is that the pressure RAP CE used for optimum fogmatiop of an EV is also the pressure where the MEP free path of an electron is about the diameter of a bead chain, 20 microns. Higher or lower pressures can be used, but this is approximately the center of the useful RAPS. Components and devices 822. Multi-electrode EV source. Figure 8.11. Components and devices 8-23. Multi-electrode EV source. Figure 8.12. Components and devices 8-24. Channels. AP EV can be formed you raising Fe LS top density of a region of space to the critical EV formation level through the use of secondary emission from Peru surfaces and Rehas, accompanying L-stop Rahm effects. A closed channel shape of dielectric material for electron containment, coated with a resistance material to distribute potential and provide field gradient for electrons, is the main element for this type of EV generator. It is necessary to have sufficient ambiguity storage in the channel, usually in the form of distributed capacity to a fixed potential electrode, to supply the peak surrepte demanded. The formation process, otherwise, saturation sets in and no EV generation will occur. It is thought that some switching process is also required to steepen the gradient of electron density in the channel. This could be provided electronical ramming or wave action. Standard Chapel electron multipliers can supply some of the functions needed for EV formation, but not E11. A problem with standard channel multipliers is that they are usually made from soft glass that will not withstand the energy density of the EV creation and propagation process. Tungsten-doped aluminum oxide is a suitably refractory material for EV formation and use. Reshmalu, there are mapu other materials with the required properties. OP limitation of the channel EV soccer stems from the need to have a field along the chapel that sappy rapidly regenerated after the firing of an EV. This charge regeneration is usually provided a resistor chain, in some form or other, connected to a power supply. The quiescent Roa drain due to the resistor is quite high when the resistor value is low enough for high EV formation rate, thus heating of a one-arch system can secure. The basic problem with this rosacea is that the efficiency of electron production is small for secondary emission. About 100 volts per electron. There is AP additional problem with efficiency in that the Roa distribution system is far from ideal, using resistors for distribution. Direct supply of Roa from essentially fixed potentials to lumped electrodes would alleviate this ROLM, but would result in increased technological cost. There are other EV sources that are more efficient than the channel type, but the chapel generator retains a degree of simplicity that recommends it for certain applications. There is no prohibition against using gas in a channel to help increase the efficiency of electron generation and to remove the charge from the walls. Using gas, a higher value of channel resistance sap is used. In the limit, it is possible to use a raw dielectric, and this is the case for EV production in the streamer mode on an OREP surface. If ORTHEG system parameters allow the use of gas, then there may be some advantage in doing so. Components and devices 8 to 25, figure 8.13. Components and devices 8 to 26. Triggers. In all channel sources there is a need to trigger on the process of EV formation, application of a voltage. Although the entire chapel can be pulsed, this is not energetically desirable in most applications. A thermionic electron source can be gated on at a low 1H1 in the electron multiplier chain without using more than a few volts of gate voltage. A gas discharge can be used if triggered jitter and low speed can be tolerated. A gated electrode in the secondary emission chain can be used if the input to the chain is fed with a radioactive thermionic or field emission source. Photon switching can be provided illumination of the input to the secondary emission chapel. There are mapu ways of switching op-channel EV source, but each application requires a specific Frigga processy compatible with the rest of the system. EY guides. An EV guide is as important as the source, otherwise there would be no way to use the EV, as shown in Chapter 5. 5TM gets, the guide channels SAP, highly loaded, and design error can be fatal to the guide. At this point in EV technology, can see two broad classes of guides, and these can be fitted into well-defined engineering terms. The simplest class is the RC guide using doped dielectrics to help control stray charge, and the LC guide that physically resemble delay line structures. There is no need for dielectric material in the immediate vicinity of the EV because the distributed LC components act both as stabilizing element for EV guidance and as stray Schke collectors. This latter type of guide is most desirable, but it is more difficult to construct. RC guides. There is no long treatment of RC guides in this chapter, since enough has been said about them in previous chapters. They are not hard to understand in engineering terms, though they may be very difficult to understand in a fundamental scientific sense. Figure 8. 13 shows AP assortment of guide configurations for running EVs op either the outside or inside of dielectric surfaces. One precautionary citement about RC guides: I would expect much more secure breakdown of these simple guides as the concentration of EVs increase in the guides. It may well be that the effectively short pulse time imposed on the dielectric as the EV passage point is A11 that saves the dielectric. If a guide were full of EVs, and therefore full of charge, it may not be possible for this class of guide to withstand the Sheshka and breakdown Mao Osser. Components and Devices 8 to 27, Quadrupole LC EVE Guide, Figure 8.14. Components and Devices 8 to 28. An effect having to do with guide charging that I do not understand deserves a short mention here. It is obvious when there is a charge on a guide because a new EV will not enter the charged region. On the other hand, it is known that an EV is actually a trape of several charged entities. One might wonder why the second entity in the train does not KLF resist following the first one. Perhaps it is because they she linked with considerable binding energy, thus allowing one ever to follow another if they are not too far separated. The only mechanism I see at work here is that the erase charge of the EV prohibits charging of the channel or surface in the immediate vicinity of T-Tara EV, but allows charging at a distance where the scattered electrons sap some back to the surface. LC guides. Very little has EEP done about this class of guides, but they hold the greatest hope for future development. Although most of the discussion here centers upon small guides that are rarely sized for the small EV structures we now work with, there is no reason to limit the upper size of the LC guides when large, high-powered applications are subserved and different Kunstretzkuhn technology is required. The point to remember about LC guides is that APEV will depress the potential upon any circuit element as it aroses. Inductive elements are most susceptible to this effect. The depressed potential makes the electrode less attractive to the EV, and a steering action is available if there is a more desirable direction to go, as indicated, a higher positive potential elsewhere. Consider the case of APEV entering Pormal to a quadrupole structure, YUK as the one shown in Figure 8.14, that has sufficient inducence in each of the four directions to allow a potential depression of the electrodes as the EV aroses. If a single element of this structure is kept short in length in the direction the EV is going, then there will lonely a restoring force to the scepter if the EV deviates from the center position. Having a long array of these quadrupole guidance elements will thus reaffirm the function of APLC guide. In practice, this shishja dissembles an ordinary delay line in each of the four axes, or however many are used. Depending upon the time constant of the LC circuit, there will be a rebound of the potential after the EV passes, and eventually the oscillations will subside. This description is greatly simplified for a single EV passage. FSH more actually goes up in practical circuits. The main point of this discussion is that the dielectric is not needed in structure that is serial of producing image-like forces for correcting the position of the EV. Both the quadrupole element and the srazer shown in Figure 8.14 are conductors. A stack of these elements can be made in almost a pew shape as long as the Rohrer timing function is performed. In the guide, just discussed, there is a need to consider coupling coefficients between the EV and the guidance structure. There are limits in size for the structure once a particular amount of Sch and Heps EV size is assigned. Too large, a uterus fjord will not respond adequately for control of the EV, and too small a structure will not allow adequate turning time and space for the EV. Both mistakes in size will result in unstable modes for propagation and therefore destruction of both EV and guide. Components and Devices 8.29, Figure 8.15. Components and Devices 8 to 30. An interesting rule of THM for guide design is that the electrodes designed to couple to the EV SAP is considered 1D wave trajectory at the Aroash frequency of the EV. This frequency is determined Ramarilu, the velocity of the EV, r the distance between the EV and the steering elements. Since the diameter of the guide is related to the coupling coefficient, there is AP interrelationship between the diameter of the guide and the spacing of the elements. In FIIS type of guide, the 1 plus waiver elements sap, or rated at dirus sepept, or a fixed potentiae, without changing effects. The nullity to RAU for this LC guide is that the velocity range for propagation is not arbitrarily wide. Scaling considerations. It should islear that as the pummer of EVs in a guide increase, so will the power level. I do not yet know what the limit of power handling ability will, but certainly both the metal and the dielectric get a good warning out at submillimeter wavelengths for the size of guides used for our present EVs. AP-EV, requiring an RC guide size of 20 microns, would require AP-LC guide slife nonaga. The implied spacing between guidance electrodes would also E in the vicinity of 20 microns. Obviously, this is not a Cheru high power handling structure, and although parallel units could be used, it seems more economical of material Shek C and processing to scale or the EV to fit Elshka guides. This scaling is primarily a function of the EV generator, or the Sheshge, combining circuits following the geparators. Film LC guides. There, Shimapu geometric, and electric variations on the guide just discussed, but that fry is rimshalu suited to one-shi structures made U-lamination techniques. Different construction techniques are applicable to small effectory, and particularly to those amepale to film processes. One geometry that fits the basic needs for film construction to confine the EV is shown in figure 8.15. In this expanded, drawing the sideways sophipemept is O beyond U-conductive stubs resembling 17A wavelength lines. The top and bottom confinement is accomplished U-asimilm geometry, but this time it is accessible to continue through the center, and the I-trusture resembles a shorted 1Z wavelength line. The entire structure finally becomes a form of slotted waveguide or delay structure. Since the structure is very active LSG-SALU and would radiate strongly in the form shown, it is necessary to enclose the structure with conductive planes op both top and bottom to suppress radiation. Again, there is no fundamental need for a potential difference between the VMIOS electrodes, and they SAPI connected together at the edge. Components and devices 8 to 31. E-subscopizer. As mentioned in Chapter 7 on travelling watch effects, the EV burst that is generated most yourses is not highly regulated with regard to spacing of the charge entities. There are a variety of processes in the sources that produce the spacing we get, but these processes have been more accidental than intentional. The RC Guai structure just discussed is a form of synchronizer that does two things. The MEP velocity of the chain is locked to the frequency of the guide, and the spacing of the individual charge entities is forced to flow into synchronization with the slot period of the guide. The effect we wish to measure here is caused the periodic electric field produced in the guide, and the ability of this field to bunch the EV train into that field, accelerate PG, the slow EVs, and rearing the fast EVs. If a guide is initially unoccupied, U-AP-EV train, then there is a short time period in which the RF level is too low for strong synchronization. As the RF level builds up, the synchronizing action becomes more effective. The Q or figure of merit OI cavity determines the rate of build-up and decay. 2 LMG a Q will cause breakdown of the cavity, and this must be avoided. There is an implied optimum filling factor for this synchronizer. With low filling, the synchronization is not effective, and with high filling fascia, there is danger of breakdown and interference with the guide function. Aurora synchronizer would be more loosely coupled to the EV than the guide strut arrays should WP in figure 8.14 and 8.15. This loose coupling can be accomplished using a slotted cavity with S struts on one side of the guide. Using this method, the GID-E would operate at a lower frequency than the synchronizer and Hasha-Mush Roda passband. Components and devices 832. RF generators. Although I have discussed circuits that produce RF in the last two sections, the action was associated with internal functions and not used for external radiation. With only slight modification, the RF generated can be coupled out of the EV guide and used for whatever purpose is desired. The lower part of figure 8.16 shows a generic type of RF generator in which a series of slots placed in the counter electrode of the guide provide openings for the charge of the EV to couple out to another electrode that is, in turn, coupled to the radiating system for the RF. In this type of generator, there is a reciprocal relationship between the EV velocity and the output cavity that determines the frequency of the radiation. The EV velocity must be in approximate synchronization with the RF frequency before the cavity can lock the EV and show this reciprocal effect. This system shows many of the same effects found in conventional RF generators, such as voltage and load effects on frequency. All of the usual harmonic effects also show up in this class of generator. Components and devices 8 to 33. Gated electron and RF source. Figure 8 1b. Components and devices 8 to 34. Areriodis waveforms. Aperiodic waveforms for driving various computer or timing functions can be generated with the structure shown in Figure 8 1b. You having openings in the supta electrodes that are shaped like the waveforms to be produced. The load op, the output electrode, must be proportioned according to the bandwidth of the generated waveform. If low frequencies are expected, then the output should be connected to a transmission line with resistive termination at its characteristic impedance. The EV velocity sap is locked into synchronous motion, using RF injection or interaction as previously discussed. This helps regulate the periodic rate of the output pulses obtained op the output electrode. With this structure, it is possible to generate output pulses of either positive or negative polarity, differentiation of the charge as it passes the slot in the counter electrode. A matched or low load on the output rodices essentially negative pulses, while a highly loaded output produces first a negative pulse and then a positive one. This effect is beneficial for generating positive waveforms used in driving field emission devices into the emitting state. Digest SGEPT output devices. Direct coupling between the EV and a collector electrode can be obtained in a variety of ways. In using the simple RC guides, it is possible to collect electron emission out the top of the guide, if the guide is sufficiently deep and the EV is strongly locked to the bottom of the guide or the counter electrode side. The electrons collected on OUST electrodes some from secondary and field emission sources that EP produced use the energy of the EV. Since these electrons have some from a diatestaceous material with long RC time constants for recharge, it is necessary to wait for recharge until one apoffer evi sap ozuru the region. In the LC class of guide, this time delay is very short since recharge is supplied via melis electrodes. Electrons can be collected for direct SGEPT output service, simply supplying a collector electrode since they have been given initiate ipurgu u the EV. This collection can be done using any of the surrounding electrodes shown in Figure 8, 14 or Figure 8, 15, using eavesdrop emission. Since it has been found that AP eavesdrop is made to emit a fairly nitsto band of eavesdrop energies when rarely stimulated, there is a wide class of devices available for application using the EV as a special type of cathode. The primary consideration in using this cathode is determining the MEP epergu and the epergu spread of the emitted electrony. There is also a gating or chopping effect that comes from having a definite spacing between EVs. The RZMG available goes from essentially steady emission, from a frame of circulating EVs, to very pulse-like emission from passing a single EV under AP aperture. Figure 8.16 shows a cross-section of a triode tube-like structure mounted on top of an EV guide and using the EV as the cathode for the triode. The anode is assumed to E the components and devices 8 to 35. EV selectors, Figure 8.17. Components and devices 8 to 36. Phosphor screen or another electrode. IP actual practice, this free of device would be used in one Arja powers to achieve yom complex function, and the triode would be only one type of the MAPU components in the arrow. It would hardly be worthwhile to put only one of these things in a SAP. Since the N-tight chasm tube art precedes this device, it is not necessary to go into the subject any further here, except to point out that many devices have been bypassed in the past due to insufficient cathode brightness. The EV okosomes this objection, thus opening the door to AP-ECHEP wider class of devices than was available with space charge limited thermionic emission. The most noteworthy class bypassed was the beam deflection, free electron device. These SAP POW reconsidered. Display device. Fairly simple use for direct SGEPT emission from an EV is the activation of phosphors for light production. This effect can be seen any time an EV passes, any material that will fluoresce or phosphoresce. If the triode structure mentioned above, or any other spectral geometry for the emission, is interposed between the EV and a phosphor, a type of cathode Rao tube can produced in which selection of the lighted shade is done U-gating instead of U-sweeping a E-MAM. A large pummer of active gates and their driving circuitry obtained using free electron spectral circuits could be formed into large shade, flat rape one displays. The technology for doing this would consist primarily of lithographically formed dielectric plates, with metallized holes in them at appropriate places, aligned with EV guides on other plates. There is high technology requirement for producing this display device, because neither an EV nor free L-strop control requires very high technology. In this display application of EIs, it is possible to lower the technology requirement of other components requiring high technology, judiciously mixing in some EVs. A case in point is that of using field emission, driven, short EV-fogmed pulses. The short pulse, par-7V thegmal rupawow of the emitter, allows operation in the more geometry-tolerant space-chemg limited region and prevents ion bombardment of the sensitive field emission cathode. EV selector. Simple EV sources Geppert groups of EVs having various numbers of beads in a chain and Sheshas pumek of chains. When it is desirable to have only op-raticular type of EV to use in a process, then a selector action can help to limit the PCHMAR of types available and to provide the desired species. The selector action shown here generates a variety of EVs, wraps them to an anode or collector on a dielectric surface around a sharp edge, and detaches selected EVs at this edge, and then extracts them to a guide surface or other useful region. Drawing of a structure to accomplish this operation is shown in Figure 8.17. The selection process is probably accomplished in a fashion analogous to field emission of electrons. Components and devices 8 to 37. EV splitters. Figure 8.18. Components and devices 8 to 38. I can imagine an action that binds the EV to a dielectric surface or any other type of guide, but since all such processes have limits of binding strength, it is possible to remove the EV by applying a more attractive situation elsewhere. The application of an external field does the job in this case. The whole game is to limit the binding energy of the EV and then supply someplace to go that is more interesting. By supplying strippers or selectors in a cascade, it is possible to pick one particular binding energy out of a wide range. This process gets particularly sharp when the EV is first destabilized by a resonance process having to do with the desired end effect. In some ways, this selection is analogous to atomic excitation and selection because there are many modes to choose from. EV splitter. For certain applications involving very close timing or synchronization of events, it is necessary to derive two or more signals from a single input. One method of doing this is to divide the main, or first, event into a multiplicity of subevents. With an EV source that produces a large number of beads or bead chains within a short period of time, it is possible to divide this temporal event by the process described here. Structures for doing this are shown in Figure 8.18. The principal difference between the two drawings is that one uses the mosaic technique, where an EV is locked into an acute angle formed between two surfaces, and the other uses more standard channels or guide grooves. The EV splitter described here is an experimentally verified device, but, like so many EV devices, things happen too quickly for the details of operation to be known. I can only speculate that the overall action is caused by a type of self-switching between bead chains as they pass the alternate path in the guide structure. This could be due to a charging process. What is known is that the arrival of EVs at the two outputs has no more jitter between the two than there is between individual bead chains on a single path. The jitter is almost impossible to measure on the picoscope or electron camera, and this puts it in a time range of substantially less than 10 to 13 seconds. Deflection switch. An EV, essentially a negatively charged entity, can be deflected by another charged object if the charge is sufficient in magnitude and applied for a long enough time. The deflection of an EV through whatever guide structure is used is an essential element in EV technology. Obviously, there is a bilateral effect at work, and the deflector may experience an unwanted reaction from the EV passage. For optimum switching sensitivity, it is necessary to prepare the EV for deflection by making a marginally stable path preceding the deflection process. In general, this increased sensitivity can be achieved by passing the EV from its tightly bound state in a guide to a region having very little lateral guidance. In this low stability, components and devices 8 to 39, EV deflection switch, figure 8:19. Components and devices 8 to 40, region the deflectors can be maximally effective before the EY is OPS again entered into strong guidance region for further propagation. It is obvious that the T-annihilation from the original guide to the low stability region must idun IP a mapper that does not set all transients in the EV path, otherwise spurious switching can result. There is a useful analogue between EV switching and the switching methods chest in fluid logic, ECHEP, to the extent that feedback SAP is used to completely relieve the effect of input loading or coupling. In such EV circuitry, there is a considerable advantage in having the feedback use electromagnetic componenty operating PESH the velocity of light to circumkept delays that would otherwise produce raw transient response. Conventional R, S, and L components work well with EVs travelling about L to the velocity of light. Figure 8:19 is a drawing of a film version of an EV deflection switch. The most residual aspect of this device is the way an EV is epted into the deflection region. In the drawing, there is a stabilizing counter-electrode shown under the entry guide. This is OP method for inducing the EV to proceed as the deflection region without showing instabilities in motion. An alternate method, not shown OP-FA drawing, of inducing AP-EV into deflection regiop with low disturbance is based upon mechanically tapering the inlet guide in the thickness dimension until it is longer effective in guiding the EV. This method is not easy to reproduce in photolithographic technology. Strong, bistable switching action SAP, achieved, producing a geometry that is alert at the ep-fiery region between the guide and the deflector. Of source, more deflection voltage is required in this case. Another variation not shown in the drawing is produced, using resistive termination of the deflectors and letting this deflector region cross the EV path. Dielectric charging is prevented using this deflection method. Components and devices 841, figure 8:20. Components and devices 8 to 42, eye-picoscope. Extending the quality of the stabilizing and deflection methods of the eye switch, it is possible to produce a type of oscilloscope that is Sarai of displaying very high-speed waveforms. This device is shown in figure 8:20 and figure 8:21. Figure 8:21 SAP recognized as the electron samra, and indeed embodies mapu of the elements of the illustrop samra with a few additions to the region where the EVS operate. The camera is used to look down upon the structure shown in figure 8:20 and present AP image of the EV motion op the surface. The motion on the surface is not a true function of the potential impressed upon the deflection electrodes, but rather AP integral of the function. In spite of this, the picoscope is still a good device for viewing fast waveforms. The motion of the EY SAP is viewed directly with a microscope if a rose-raw coating is applied to a suture plate located a short distance from the Schurphase op which the EV is running. This configuration is shown up the right side of figure 8:20. Components and devices 843. Electron camera, figure 8:21. Components and devices 8 to 44. One be using this technique for high-speed work, it is necessary to keep the input leads as short and small as possible. For most work in the range of this instrument, it is most desirable to practically embed the scope in the region generating the signal. These essentially some chip scopes and should be considered practically disposable. For changing the sensitivity and sweep speed of the scope, it is almost necessary to change the N-type device geometrically, or at least to view a longer EV up for longer U-weep times. OPE cannot yet vary the EV velocity ochre a sufficient rapch to get A11 of the timing rapch desired. For timing and synchronization of waveforms, it is necessary to try almost every EV trick available, because conventional transistor circuitry is not easy adapted to EV technology. Components and devices 8 to 45. EV coupling to traveling wave circuits, figure 8:22. Components and devices 8 to 46. Traveling waves. Since AP entire chapter has EEP devoted to the trials and tribulations of the operation of travelling wave devices, it is only necessary to describe some of the apparatus here. Figure 8.22 shows two drawings that may shed some light on the configurations used. The heart of the device shown on the left is a dielectric tube of either glass or ceramic. A coil of wire is wrapped on this tube in such a way that it just overlaps the cathode and the collector. Load is put op the EPD of the delay line formed U the coil and associated ground plane. This load must match the impedance of the line to minimize reflections. The cathode is pulsed with a negative going pulse of from 1 to 2 kilovolts applied through a resistor of from 500 to 1500 ohms. This resistor is used to protect the cathode and to help determine the Schrept being delivered to the cathode. A 50 ohm resistor is also connected to the collector going to the scope. In our particular operation, the entire apparatus was operated in an oil diffusion pumped Cashum system, and K-pop gas was bled into the tube. This allowed us to rapidly change cathodes and other appendages without getting leaks. As far as experimental technique was observed, this device operated very well. It is just that there was basic difficulty with the concept of interacting coherent structures that made repeatability sherry raw. The right side of Figure 822 shows a film equivalent of the Faveling wash apparatus. The slow wave circuit can any pummer of layouts, but this one shows a serpentine line. AP into digitavd Itrixts would do well here also. Optical guides. Although this Ragarar is going to EAP extremely thin offering for a device or component, I still feel inclined to cement on what has been seen IP the way of optical guidance for EVs. There is a day coming when this effect will be understood, and thus some powerful addition to the EV arsenal. The apparatus that first showed the effect is shown in Figure 6.1 and is the apparatus in which most of the streamer work was done. When streamers rise up from the scepter electrode and strike the top, they THRP and RCHP radially op the flat surface of the soccer glass. The roop is not entirely straight as they approach the cylinder wad 1L, but at times there is a fair approximation to a radial line. When this happens, and the line is viewed from the end in the rape of the top, a bright scintillation can be seen. If a piece of white paper is placed shupte the cylinder, mapu scintillations and streaks can be seen. IP order to make the effect more obvious, I caused tremery to rup in long glass tubes, exciting them with short bursts of RF at a frequency of between 1.7 and 5 MHz. About 10 cycles of RF was the minimum that I could conveniently generate, under the conditions. Some repeps and devices 847, Eve.X, ray source. Figure 8.23, components and devices 8 to 48. That produced small, thin streamers. These streamers would rup for a distance of 2 inches or so up the inside of the 3 mm glass tube without turp IPG. Then they would suddenly deflect small angle and then rup state again. Vu looking at the deflection point, it could be seen that the deflection was caused something on the surface. Put small grains of various substances in the tube to see what the effect referred. Silica sand was the whipper. The sand had bright faces, or facets, and I reasoned that it was this optical surface that caused the turp. Also applied the sand to the center electrode, and found that it would cause the launching of a streamer whenever the conditions of angle and field were sorest. There was no way to control the process with phi apparatus used, and the effect was strictly a statistical one. Some day we will get a control on the effect, and it roche to a laser-like roses generating the eam that the EV then rides upon. That would be a nice upagoo, but one I hashe come to expect within the EV field. If such guidance does, as some practical, there is good chance for focusing ipormi ipergu density from multiple sources that are a lot easier to make than conventional lasers. Point X-ray source. The EV point X-ray source can be a simple component of some system. I mention it in passing because it is there, and some pay Maoial to make something out of it someday. Figure 8.23 shows an EV source and a TMG with sufficiently low inductance to cause the EV to rupture, or at least that is the way I think of it, and in doing so, emit X-rays. Circulators. CI teculators are a pother component that there has been no time to work on, although they are as important as APU other component. In some ways, I hope the energy storage capability of circulators will not high EPOF to make them competitors in EPRGU density with chemical explosives. I do not have good visions at A11 when I think of an electrical ohm, but all energy storage devices are potentially dangerous. When guides are worked to a highly refined state, can circulators far behind? If the materials of circulators can take the gaff, and one Shea surreps of EVs can circulated, the generation of magnetic fields will produce the aboleth to span gross physical gaps and produce magnetic bemmings and motors without magnetic materials. Superfine control of these fields is an inherent part of EV technology. As magic as all of this seems to be, I would not expect these circulating surrepti to continue without a drive field. After A11, the stored EPRGU of electrons is pretty low, and HEP superconductors have lower magnetic field limits. FAP is desirable. High-frequency drives, in the sub-millimeter range, is the patrol choice for small drives, while scaling will allow lower frequencies for the larger machines. Components and devices 8 to 49. Some routers. 11% of the components necessary for some rather interesting computers seem to be available within the bounds of EV technology, but the ROA level is far too high with the recept bead size we have, although there are some charge steering technique here using deflection switches that could use large EVs to their best advantage. Just a IMEPT's E-flexion, the voltage change produced U-API-EV on a typical structure will show why the present EVs are too large. Take, for example, a low-micron Shea of materia uni with a dielectric obstapt of 5 having electrodes on a pair of opposite SU faces. The computed capacity of this geometry is around 5 kH 10 to 16 F. Only 3 kH 105 charges are needed this capacity to reduce 100 volts. One EY bead sagres around 10-11 charges and would blow the capacitor to bits if an attempt were made to store all of the charge on the capacitor. It would be necessary to drop to a bead size of 0.01 microns or 100 angstroms diameter to provide this charge. I can't say that I eka seen such a small EV and it mau not eshepi possible. The major implications here are that API-EV is recept too large for the simple computer functions that are presently practiced. It is not just a question of simple row dissipation. It is of being a major threat to the very existence of the machine. Irui is needed for the EV is a method of computation that uses the SAR may EV mapu times oka, if all the order is destroyed. The method of choice would be more one-ike surrept steering logic, some multi-aperture magnetic device work, superconductive logic, or possibly a form of neuristor circuitry. At the moment, I can see some special, surer, high-speed front-end logic being refogemmed certain input information, but for most functions, the presently available I/O energy level semiconductor components have a lot to offer, and are the winners. Where to from Nagay? Any reader who has managed to stick it out through most of this book mau have noticed that the real data started thinning out toward the end. It even gets thinner from here on, but hang up, because we do not hash far to go. The real beauty of EV technology lies in the fact that they seem to offer not just a variation the same old themes of component and system building, but rather a gateway into AP entirely new realm of fabrication and reformaps. The EV is a new substance. It practically creates itself, and is more than ready to form into vast new organisms with only little help from us. I have dreamed, prayed, proclaimed, ranted, and raved about new organizational methods for Mapu Uia's POW, long before the EV showed and now at last one is finally in sight with all of the necessary prerequisites for growing itself almost alone. The electronic entities to E formed will not look, or E like anything Eka written in science fiction, although I am sure someone has foreseen them. Hope we can knit them into something that aids our culture. I would like to see the time when such app entity, with A11 of its roa and intellect, would fulfill our hopes for a trucklu great self-organizing form of artificial intelligence. Components and Devices 8 to 50. Chapter 9, Guidelines for EV Theories. There are many EV observations that can be made to fit loosely under one set of rules that seem to coalesce into a theory of EV containment and propagation. I am going to submit these observations in the form of a rough theoretical outline, as if a final theory will emerge from this beginning. Considering that this work is in such an early stage of development, it would be a surprise to me if the emergent theory were very close to this preliminary effort. Gradient focusing. Since the EV is such a ubiquitous device, it follows that any containment scheme associated with it must also be universal and easily reproduced. In searching for a convergent, self-focusing process to contain the electrons in the tight little bundle we see, I have been led to consider strong focusing techniques originally used in particle accelerators. Here is a technique that is more universal than it might originally appear. This method is at the root of alternating gradient focusing, monopole, quadrupole, and spiropole mass spectrometers, optical containment of particles, and a host of other particle manipulation methods. The convergence process at work in all of these applications is a dynamic process. The process stems from the time average of an alternating force on the contained particle in an inhomogeneous field being driven toward the region of the weaker high-frequency field, which must be the center of the container. Frequencies for achieving this containment effect extend from low audio range to the optical region. This is indeed a universal process, and it seems applicable to containment of electrons with the density of those found in an EV, provided sufficiently high frequencies and amplitudes are used. Before I am through describing this containment process, I am going to ask you to believe that it is possible to contain electron pressures equivalent to billions of atmospheres with radiation. Spherical monopole oscillator. A second requirement of major importance is to find a containment geometry that naturally occurs whenever the initial process of forming an EV begins. This geometry must also be consistent with the needs of the containment technique in providing a convergence, while at the same time not allowing the motion of the electrons contained to radiate all of their energy to space. It is possible that the simplest imaginable configuration of spherical compression is the shape of choice. This geometry results quite naturally from the plasma blow-up that follows, along the lines described earlier in Chapter 8 in the section on short EV generators, and from the description of Mesiarts, 1982-1983. There is also something similar to a spherical electron blow-up formed when a field emission source, initially operating under space charge repulsion, is pulsed with a very short pulse, although this source would also seem to contain toroidal components of motion. Internal modes. The largest concern with the spherical geometry comes when one considers the radiation from the electrons oscillating and converging in their self-generated field. In the ideal case, the radiator would be classed as a monopole, and this would be incapable of radiation, a very desirable feature for low loss, but one that then becomes suspect of not having sufficiently interesting internal fields for supplying the focusing action. I will also have to assume that dipole and quadrupole fields will radiate excessively, and thus remove themselves from the structure, perhaps leaving their electrons for containment by another more conservative segment of the container. In such a matter as this, I will just have to wait until someone else makes a pronouncement. For the moment, I will adopt the spherically oscillating charge, assume it has the ability to self-form the internal states for producing the desired convergence from the initial formation energy, and move on to the process that maintains the oscillations of convergence. Zero-point fluctuation drive. At this point, I can fall back upon the paper of Bergström, 1973, mentioned earlier, and claim that the motion of contained charges is indeed what binds them to the remaining charges forming the entity. At this same juncture, I can step over into the holy region of the vacuum, or polarizable ether, as Bergström called it, and begin to look for the sustaining process that keeps the entity intact for longer than would seem possible from initial energy input considerations. I will invoke zero-point fluctuations as the ubiquitous energy source to sustain the life of the EV. Puthoff, 1987, has shown that the ground state of hydrogen is a zero-point fluctuation-determined state, and that this carries with it the attendant implication that the stability of matter itself is largely mediated by ZPF phenomena in the manner described. a concept that transcends the usual interpretation of the role and significance of zero-point fluctuations of the vacuum electromagnetic field. I claim that the initial motion of electrons set up at the time of an EV formation is kept in equilibrium, or compressed further, by the electromagnetic input from the zero-point fluctuations. Guidelines 9-2. Reformation. In any complex process, such as the one just described, it would not be likely for the process to freeze at the moment of formation and never change again. Indeed, the opposite is implied. The more complex a process, the more likely it is to continue changing state with time until a final low-energy equilibrium is reached. I would expect an EV to be a ragged thing initially due to the unsymmetrical fields that determined its formation. Once the entity wrested itself free of the formation region, I would expect a high degree of conformity with the container, but that it would still have a life of its own. I would also expect that there would be a chance that it would reform into a more ordered structure that has a relatively narrow radiation line width. This reformation may cost the loss of some electrons, as we have witnessed with the electron camera. We have seen how amulets reform, and how in doing so they eject electrons that cannot be accommodated. Reflecting back upon the photographs of the bead chains, and knowing that these results represent not only the influence of the containers for the beads, but also the force that binds the beads together, we see an absurdly complex electromagnetic field configuration having many bound nodes in a harmonic sequence. It is a wonder that any change can be made in the structure without a total disaster. This is simply a wondrous process. Container size limits. If this container process follows normal laws of nature, we would expect that the lower size limit would be strongly affected by surface to volume ratio considerations. In all likelihood, there is a minimum size bead that can be made with a particular rate of energy input to the process. Bergstrom, 1973, declares that the same process of containment is good for things ranging from the size of an elementary particle to ball lightning. Perhaps so, but it will take pair production energy densities to form an electron-positron pair. The EV, having a much smaller surface-to-volume ratio, would not seem to require such a high energy density for formation. There is also this matter of why the bead size seems to be predominantly 1 micrometer in diameter. Above this size, the process just seems to prefer to form other beads instead of growing larger beads. My guess at this point is that the disturbance we introduce into the formation process has something to do with the maximum size attainable. It may be analogous to blowing bubbles. High pressure and high velocities, creating turbulence, do not make nice big bubbles. It takes low-velocity, undisturbed air to make large bubbles. This is the weakest kind of statement that can be made, but I feel inclined to offer something here since the size of a bead is such a characteristic thing. In a more scientific vein, it would also be interesting to look at vacuum breakdown, or sparking as the non-linear mechanism that limits the size of a bead to the 1 micrometer diameter region. Guidelines 9-3. Container summary. Up to this point, the process I propose for formation of an EV is this: an externally driven process of compression, which strives for something roughly spherical, is followed by a rebound that produces a self-excited field operating in such a way as to converge the electrons toward the time-varying, field-deficient center of the spherical monopole oscillator that is developing. This oscillator is coupled to the ZPF fields and is sustained. There is a regrouping of charge and fields, both within and outside of the newly formed entity, until an equilibrium is reached. This equilibrium may be the incognito state of an EV, called a black EV, and could be closely related to an excited state of the vacuum. Surface field measurement.
Consideration can now be given to some of the external manifestations that have perplexed us. In particular, why does the EV not show the megavolts of field that one would calculate from considering the number of charges present in the radius indicated by the witness plate strikes? Most of these measurements are made by observing the velocity of electrons either given off by the EV or electrons approaching the EV from outside. In both cases, we see only kilovolts of energy at best. The solution to this mystery is that the container action of the EV has isolated the fields of the EV core, and all that we have access to is the surface of the container. This surface extends a considerable distance beyond the actual region containing the electrons, and so our radius measurements using the witness plate radius are false. This
is the correct inside size for the container, but it does not represent the region of interest when using either emitted or incident electrons to probe the fields. There is, in effect, a work function associated with the container, and this can be overcome either by thermal-like or tunneling processes. In addition, one must consider the effective field reduction caused by the container overcoming the space charge repulsion force. Maximum energy extraction rate. Since the ZPF energy supply rate is limited, probably by coupling considerations, there is a finite extraction rate of energy from the electrons in the potential well created before the stability criterion for the well is exceeded. If this rate is exceeded, as it may well be upon contact between an EV and a metal, then the EV explodes, giving up its container energy into whatever region of the radiation spectrum is most appropriate. There are indications this may be the soft X-ray region for 1 micrometer beads. An indicator of a useful energy supply rate from the vacuum can be gleaned from the data on how an EV bores its way through aluminum oxide, as described in Chapter 5, EV targets. The constant diameter of the bored holes suggests that the device doing the boring was either very high in energy, guidelines 9-4, content, and hardly affected the operation, or that it was being resupplied with energy as it venal I choose the latter explanation. I would like to point out again what a high stiffness must exist within the boring entity, and that this implies a high radiation epigoo density for the container. One could think in terms of the radiation being used as a plug to prevent the escape of materia 1 in the rearward direction, while the pressure at the front was determined the Chara pressure of aluminum oxide. Sommupi Satyop with guides. When the EV is Pomalu formed and proceeding in a guidance channel, it will be in constant communication with the guide. The coupling is likely to emission from the containment frequencies, which Maui in almost any radiation band from submillimeter through kh rho. Some of these emissions would returped from the guide to the EV, and they would constitute a sensor and servo system to maintain RORA positioning in the guide. It should clear that high-loss material for guides so-called have adverse effects crop the guidance system. Observations on some EVs operating in Chasium without the advantage of a nearby guide show that they are stressed to the point of extinction. Other EV structures do much better, presumably because they radiate less. The IPTEG-PUL structure of the EV would thus dictate its lifetime when using this scenario. The recube of this situation is seen when an EV proceeds through ECHEP, very low gas pressures, especially through high atomic puma gases. In this case, the long lifetime of the EV might be traced to the shielding action of the excited gas. Soft Voopderies. It has been noted that APEV has a whiteate in which it can mosh through gas without causing APU-ararept ionization. These interaction misread's do not extend to extreme sensitivities, but for a given set of conditions, the EV suddenly goes black, perhaps appearing later, but for a time essentially disappearing in terms of illustrop, ion, or light emission. I believe that the high-frequency containment theory can socher this state without too much trouble. It appears to me that the fields reaching out from the EV solid have the RORA gradients and sufficiently low frequency to present a soft effect on Peru objects, such as molecules, and to be able to sweep them aside without exciting them to optical transitions or ionization. Polarization. When we think of the attachment force that binds an EV to a dielectric guide, we Pomalu think in terms of the direct-surrect polarization, and there should be plenty of that AROC PD in EV. With the container model we now hash in mind, we must also consider the high-frequency polarization effects that would surround the EV. I assume that these would guidelines 9-5, effective up to the resonant frequency of the material being used for the guide. In considering polarization, note that this can be considered a bilateral process. In my opinion, the EV is also deformed slightly whenever a direct current polarization field is present. Later, this will come into play when we consider the propagation properties of an EV. Consolidation. There is a slightly disturbing prediction from the model suggested here. One might suspect accretion of charge onto the larger structures until mother beads or ball lightning had formed. There would be a necessity for exciting the entire structure at low amplitude and waiting for the process slowly to occur, dissolving out the smaller kinks and depositing them onto the larger structures. If this type of process does occur, it would play hob with my intentions of forming stable, complex structures with EVs. I can only hope EV laws of organization follow those of chemical binding, but are somewhat elevated in their binding energies. Charge density modulation. Another prediction that comes from the model chosen is that a variable dress charge would be available from the EV. If the effective radius of the container is associated with the state of excitement, then this would appear as a charge density modulation to a fixed observer located on the edge of the guide. This is a bilateral effect and would seem to have regenerative properties. In this light, an electrode would be responsible for exciting the EV, and in turn, the EV would excite the electrode. Many devices can be devised using this principle. Optical beam source. An earlier chapter noted that streamers formed by an EV were frequently seen to be guided by what appeared to be an optical beam. Using the guidelines proposed here, it is clearer to me how this could be accomplished with the highly organized system of radiation sources surrounding the EV. Using even the simplest considerations of radiation from a line of oscillating charges, a beam of radiation in the fore and aft direction would be expected. I would not be surprised to find that certain easily available configurations and vibrational modes between EVs did indeed produce tightly beamed actinic radiation that could ionize a corridor ahead of the EV, producing a favorable path for propagation. This relatively fast photon beam, going ahead of the EV, would seem to help set up a straight guidance path. This straight guidance channel would, in turn, help provide a more tightly bound beam, and so forth. This seems to be a logical explanation for the straight streamers we see produced in gas. Guidelines 9.6. EV propulsion. I believe an EV is being propelled by radiation, stemming from a very slight distortion of the radiation container discussed here. The distortion I envisage would be produced by application of a steady field from a simple voltage on an electrode, by a standing or running wave field, or by polarization in a dielectric material. The distortion produced would have to modulate only a small fraction of the total radiation energy available in the container to produce propulsion. With this method, as long as there is a small gradient available to distort the EV, there will be motion toward the applied field. To get a feel for the throttling power available with this method, consider the aluminum oxide boring trick, where something like the feeble applied direct current, or the residual polarization, controlled the gigantic amount of radiation release needed to do the boring. The field for applying this distortion can be either static or dynamic. I would expect an EV to be fully capable of responding to field gradients on optical beams, and therefore to be capable of riding an optical beam out of the initial EV generation region. Furthermore, I also expect the EV itself to be the best generator of the optical fields for propagation. There have been many instances seen in the laboratory where the EV has gone past the electrodes that were used to apply the direct current fields. These were largely accidents, and no effort had been made to set up traveling waves in space to extend the flight of the EV past the electrodes. Structures for doing this are not hard to imagine. It would not surprise me to see the EV brought to a halt by manipulation of these space fields into standing waves, in much the same manner as ball lightning is reported to behave. At the other end of the velocity scale, it is quite likely that the velocity of an EV will be found to exceed that indicated by the direct current potentials applied. The EV is not an electron. It is a complex engine and capable of performing feats associated with more complex systems. With this notion in mind, it is quite reasonable to assume that the velocity of an EV driven by radiation pressure will reach an equilibrium anywhere between 0 and near the velocity of light. I have often wondered if a black EV was not just a plain vanilla EV that somehow got to going so fast it was difficult to see vector and scalar potentials. In the earlier years of research, before the EV project was found, a lot of work was devoted to electromagnetic field considerations using vector potentials and scalar potentials instead of magnetic and electric fields. Although these two methods can always be mathematically derived from each other, there is a profound difference in engineering end results obtained. Guidelines 9-7. When using thought processes derived from one or the other, there were a great mapu mysteries produced in this shay as we've tried to use potential effects for both Sumk-Pisatiop and Sheshker compression. Vu some irony of fate we now have folded back Europe ourselves, and POW have accidentally discovered the EV as AP ideal Moparol oscillator. This oscillator is the Röhrfist Geparator for Chester and Sulch potential waves without contamination from either E or V fields. These wavy sap are thought of as longitudinal waves in the vacuum. They are largely undetectable, use cindered E and V detecting means, but are readily accessible to Fey monopole world. Their array to an incredibly large pummer of useful reaper yet to arise from using potential effects that are not immediately accessible to the force of E and V fields. This phase determined, force-free world will certainly be another chapter somewhere in the future. Guidelines 9-8. Epilogue. The condensation of mu thoughts and the writing of this book have EP just a phase in the constant cycle of searching the species of the physical sciences. A pew part of the cycle is coming soon, in which the resolve of FE search repeal, disseminated APD, sopcherted into chefjul products B. Following this, I will retship to exploration of the vast electronic wilderness just discovered. This soozle of sesh, discover and exploitations twi, to me, just about great as anything could E. This episode has ended, but the E3 I a whole isto v soptipude. Epilogue. References. Bergstrom Arnie. Electromagnetic Theory of Strong Interaction. Physical Review D. Vol. 8, Nober 12, 15 Dec 1973. pp. 4394 to 4402. Boyle W.S., Kislyuk P.P., and Germer. L.H. Journal of Applied Physics. Vol. 26, p. 720, 1955. Kislyuk, P.P. Bell Laboratories Records. Vol. 34, p. 218, 1956. Lafferty, J.M. Vacuum Arcs Theory and Application. John Wiley & Sons, 1980. Malmberg, J.H. and O'Neill. T.M. Pure Electron Plasma. Liquid and Crystal. Physical Review Letters. Vol. 39, no to 21 November. Messiers, G.A., Physicist. In a Vacuum, Discharge. IEEE Proceedings. Exth International Symposium on Discharge and Electrical Insulation in Vacuum. October 25th to February 28th, 1982. Columbia, South Carolina. pp. 37 to 42. Messiers, G.A. Explosive Processes on the Cathode in a Vacuum Discharge. IEEE Transactions on Electrical Insulation. Vol. L-18, Number 3. June 1983, pp. 218 to 225. Nardi v. Bostic, J. Puchets, J. and Pryor W. Internal Structure of Electron Beam Filaments. Physical Review A. Vol. 22, Number 5, November 1980. pp. 2211 to 2217. Puthoff. He grounds state of hydrogen as a zero-point fluctuation determined state. Physical Review D. Vol. 35. No 10. May 15th, 1987. pp. 3266 to 3269. Schwertsky, F. Laser Interaction and Related Plasma Phenomena. Vol. 6. Edited by Heinrich Horer and George H. Miley. Plenum Publishing Corp. 1984, p. 335. Schwertsky, F. Unipolar Arc Model, Journal of Nuclear Materials, 128 and 129, 1984. SPI P. 609 to 612. Shoulders, K. Microelectronics, using electron. Beam, Activated Machining Techniques, Advances in Computers, edited by Franz Alt, VL2, Academic Press, 1961, pp. 135 to 293. Shoulders K toward Complex Systems, Microelectronics and Large Systems, edited by S.J. Mathis and Ree Wiley, Macmillan and Company. 1965, pp. 97 to 128. References. Index. Aluminum oxide film. As target, 5 to 18 to 5 to 23, 5-26 aluminum oxide particles, causing illustrop emission, 4 to 38, anode Schrag-Gept values, 4 to 3 aeratus, tools and devices, 1 to 9 circulators, 8 to 49 computers, 8 to 50 deflection switch, 8 to 39, 8 to 40, 1 illustration, 8 to 40 designing, 1 to 11, electrodeless sockets, 8 to 1 illustration, 8 to 10, Eve Gepagator, 2 to 5 illustration, 2 to 6, film field emission EV source, 8 to 19 illustrations, 8 to 20 to 8 to 20 cent. 1 film, LC guides, 8 to 31 gas diode fabrication of 3 to 2 or. Illustration, 3Z0 gas EV guide, Zinus 25, 4 illustration, 3.24 gas triode, 3 to 15, 3 to 21, 3Z2 illustration, 3 to 14 guides, 8 to 27 illustrations, 8 to 26. Lopsha, 8 to 9 illustration, 8 to 9. Apparatus, tools and devices, Soptipede, LC guides, 8 to 29, 8-31 illustrations, 8 to 28, 8 to 30, Mark Geparator. 1 to 11 metal Karog Soccases, 8 to 5 Illustgatiop, 8 to 4 Mosaic Guide for EVs, 2 to 12 Illustration, 2 or 3 Multi-Electrode Source, S, 8 to 22 illustrations, 8 to 23 to 8 to 24 Nozzle Struskers for EV sources, 2 to 16 Optical Guides, 8 to 47, 8 to 49. Oscilloscope requirements for 3.26 to 3 to 28 picopulsar, 3 to 26 to 3 to 2, 4, 2 or 4.4, 8 to 16, 8-19 illustration, 8 to 17 to 8 to 18 picoscope, 4 to 20 to 4 to 21, 8 to 43, 8 to 45 illustrations, 8 to 42, 8 to 44, pinhole, electron samara, 3 to 28, 3 or Sally ratio of 4 to 1, 4 to 7 to 4 to 9 illustration, 3 to 29 magnification used, 4B pictures, 3 to 30 point KH Rao source, 8 to 49 illustration, 8 to 48 pulse rower supply, 4 to 4 to 3 RC guides, 8 Z1, 8 to 29. Resist CLR, EV circuit, 8 to 15 illustration, 8, 3. Apparatus, Soptipede, tools and devices RF generators, 8 to 33 illustration, 8 to 33 scanning illustrop microscope recherches of 1 to 9 selectors, 8 to 37, 8 to 39 illustration, 8 to 36 separators, 8 to 13 illustration, 8 to 12 splitters, 2 to 14, 8 398 to 38 illustrations, streamer formation shammer, BM-4 illustration, 6 to 3 surface illustration, 8 to 7 source, 8 to 7 synchronizer, 8 to 32 traveling wave circuit, EV coupling to illustrations, 8 to 46 tubing, fused quartz, 4 to 55 device, to 4 to 58 watchform mere, 4 to 20 argop gas for producing yttriumary, 6 to 2 Austin tech. La oratory moved to 1 to 9, 4 to 64. V ball lightning, possible formation 019 to 6 bead-shaped EVs binding epigoo of 3 to 1 of 3 to 7 characteristics circular structure of 3 to 3, 3 to 5, 3-7 discovery of 2 to 23, height 3 to 3, 3 to 5, surface epigoo gradient of OP misrometer size of 3 to 3, 3 to 5, 9 to 3, Richters 3 to 2, 3 to 4, 3 to 6, -7, spacing of bead chains, 4 to 23, sweep experiment, 3 to 3, bead-shaped eyes, Soptipede, tangled state of 3 to 1, 3 Bergstrom, ARP, 1 or 0, 9 to 2, 9-3, black EVs, 2 to 15, 9-7, cause of fading, 4 to 47 clefinition, 3 to 2 or to 3 to 22, Flara PG3 to 25, gas resher, and 3 to 25 Richters, 4 to 4B resurser Masipus, 3 to 25 blinking of EVs 4 to 10, 4 to 12 pictures, 4 to 10, 4 to 1-1, or a PG through materials. Li dielectric materials, surfaces Bostic Winston, 1B to 1 to 7, 1 to 10, 2 to 2 Boyle, WS2, brightness of deflected EV, PopUP form 4 to 27. Calculations charge calculations. 4b emisiop calculations. EV 4 to 9. Saror chromium film as target 5 to 1 to 5 to 3 conductive backing. Added 5 to 3 to 5. Pictures 5 to 2, 5 3. 5 to 4 to 5 to 5 Sarop without chromium as target. 5 to 5 to 5 to 7 picture. 5 to 6 cathode Rao tubes activated. UEVs 8 to 37 cathode spots as argument against EVs to 7 cathodes for EV generation. 2 to 5 to 9 2 to 15 to 2 or 6 EVs used as special cathode. 8 to 35 8 to 37 FTLR oscilloscope. 3 to 27 to 3 to 28. Index 2. Cathodes, AP'd NODs RCPG between, in scanning tunneling microscope, 5 to 14 to 5. 15 channels, EV Jeparatiop, APD, 8 to 25 cent charge calculations. 4B charge collection. To 2 charge density modulation, 9B SHAG-APG surfaces ERLU studies. 2 to 11 problems caused or greater THANU. 2 to 15, 5 to 25 Schursch. Bill biographical sketch, 1 to 4 to 1 to 5 financial, and other support from T8 picture, 1 to 3 circulators, EPIGU storage devices, 8 to 49 coaxial diodes, 3-7, 3 to 21 ristors of effects, 3 to 19 coaxial line EV Geparator illustration, 3 to 18 collector electrode, 4 to 2 or, 4 to 27, 4 to 30, 8 to 35 collision experiments, 2 to 14 to 2, 5, 2 to 18 components and devices. C. Apparatus, tools and devices compters, using EVs, 8 to 50 consolidation of EVs, 9B SOPSORTEB-G of EVS, 4 to 1.6, to 4 1 foot 7 inches pictures, 4 to 17 to 4 to 18 containment of EVS SOP taper size limits, 9 to 3 gradient focusing, 9 to 1 reformatiop of structure, 9 to 3 Srerosol Moporol oscillator, 9 to 1 to 9 to 2 summary of theory, 9 to 4 point fluctuation drive, 9 to 2. D. Damping forces of EVs, 3 to 11. Deflection switch, 8, 39, 8 to 41 illustration, 8 to 40 deflection tests, 4 to 19 to 4 to 27, deflustog electrode, 4 to 21 delay line, for travelling wave tests, 7 to 2 devices. See Ararotus, tools and devices dielectric materie LSU, R phases boring through, UEVs, 5 to 17 to 5 to 20 ristors, 5 to 8 to 5 to 20, charging OT 2 to 15, for EV Geparator, 2 to 5 EV RUPS, OP, 4 to 41, 4-43, ristors, 4 to 41. Multiple hole, or a PG 5 to 25 to 5 to 2B picture, 5 to 25 re or APG small channels, 5 to 21, 5 to 23 pictures, 5 22, 5 to 24, diffraction effect of EVs, suspected, 436, 4 to 38 ristors, 4 to 30, 7 to 4 to 38 direct Serept glow discharge, 3 to 2 direct Serept output devices, 8 to 35 discharge trails, 2 to 11 display devices, activated, UEVs, 8 to 37 doghouse, 2 or 6, 4, 1 9, 5.2, 3, 8 to 13, dual EPIGU levels, 4 to 51 picture, 4 to 50. Electrodes, Celesta APD deflector, C collector electrode, deflector electrode electromagnetic, vortex, first PAIM for EVs, Vi electron Omega, C pinhole, Elastrop, Samra Elastrop emissions, from EVs, 4 to 14, 4 to 1, 6, 4 to 27, 4 to 30, 4 to 38, used as a cathode, 8 to 35, 8 to 37 Elastropis entities based OPI EVs, 8 to 50. Electrons condensing to a solid, 1 to 10 cooling of, 1 to 10 lost in transit, 4 to 6 necessary for EV sources, 6 to 8 to 6 to 9 electrum validum, name for EVs, VI emission calculations, EV, 4 to 9 emission modulation, 4 to 27, 4 to 30, 4 to 32 pictures, 4 to 27 to 4 to 29, 4 to 31 to 4 to 32 emission sources for EVs. See sources of EVs emission spectrum measurement, 3 to 27 energy analysis, 4 to 12 pictures, 4 to 13% energy extraction rate, maximum, 9 to 4 to 9 to 5 energy source, for generating EVs, 2 to 7, 2 to 9 enhanced electron mobility effect, 4 to 36, 4-38 pictures, 4 to 37 to 4 to 38, ether theory of Bergstrom, 1 to 10, 9 to electron volts actions blinking, 4 to 10, 4 to 12 pictures, 4 to 10, 4 to 11 consorting, 4 to 16 to 4 to 17 pictures, 4 to 17 to 4 to 18 jumping along a surface, 3 to 11 turning behavior, 4 to 14, 4 to 16 pictures, 4 to 15, 4 to 16 EV generators, 2 to 5. See also generation of EVs, sources of EVs EV launcher, 8 to 9 illustrations, 2 to 6, 8 to 9 EVs. See also bead, shaped EVs, black EVs, witness marks and plates, analyzing with the SEM, 2 to 9, 2 to 11 definition, VI 8 to 1 first appearance of, 1 to 12, 2 to 1 lingering of, after pulse termination, 3 to 17 literature search relating to, 2 to 1 naming of, VI properties of, summarized, 4 to 63 to 4 to 64. EVs, continued, video images of, 3 to 32 to 3 to 39 well-defined dimension of 5 to 18. F field emission diodes coupled with picopulsar illustration, 8 to 18 as sources, 8 to 15 to 8 to 16 as targets, 5 to 17 pictures, 5 to 16 field emission processes, 3 to 22 field-free regions, lack of, around EVs, 3 to 11 to 3 to 12 field measurement of EVs, 9 to 4 film LC guides, 8 to 31 fission fusion of EVs, 2 to 18 to 2 to 19 flaring, 3 to 25 formvar insulated wire, effect of EVs on, 3 to 22. G-gas diode fabrication of 3 to 21 illustration, 3 to 20 gas EV guide, 3 to 25, 4-41 illustration, 3 to 24 gas pressure effect on EVs, 3 to 22, 3 to 25, 4 to 43, 4 to 53, 4 to 55, 5-13 pictures, 4 to 44, 4 to 54 in travelling wave tests, 7 to 3 to 7 to 4 gas triode, 3 to 15, 3 to 21, 3 to 22 illustration, 3 to 14 gases effect on EV generation, 8 to 22 failure of EVs to ionize, 9 to 5 inorganic as source of EVs, 8 to 9% organic as source of EVs, 8 to 11. Index 4. Gases, continued, producing streamers argon, 6 to 2 krypton, 6 to 2, 6 to 3 xenon, 6 to 3 gated electron and RF source, illustration 8 to 34 generating EVs. See also EV generators, sources of EVs basic firing sequence, 8 to 2 birth cycle of EVs, 8 to 3 gas, and 8 to 22 LC guides, 8 to 29, 8 to 31 illustrations, 8 to 28, 8 to 30 low energy level generation, 2 to 7 pulse duration effects, 8 to 15 resistor, EV circuit, 8 to 15 illustration, 8 to 14 synchronizer for EVs, 8 to 32 Golka, Robert, 6 to 1, 6 to 2 gradient focusing, 9 to 1 guides for EVs, 8 to 27 communication of EVs with, 9 to 5 film LC guides, 8 to 31 gas EV guide, 3 to 25, 4-41 illustration, 3 to 24 illustrations, 8 to 26 LC guides, 8 to 29, 8 to 31 illustrations, 8 to 28, 8 to 30 mosaic guide for EVs, 2 to 12 illustration, 2 to 13 optical guides, 8 to 47, 8-49 RC guides, 8 to 27, 8 to 29 scaling considerations, 8 to 31 synchronizer, 8 to 32. First inductance of targets, 4 to 32 to 4 to 33, 4 to 35 instrumentation. See apparatus, ions tools, and devices apparent lack of in EVs, 4 to 62 to 4 to 63 failure of EVs to ionize gas, 9 to 5. Ions, continued, ion and electron images, 4 to 41 to 4 to 61. J jitter, time, 2 to 11, 2 to 12 jumping of EVs along a surface, 3 to 11. K Kiliuk, EP, 2 to 1 krypton gas, for producing streamers, 6 to 2, 6 to 3. L laboratory apparatus, 1 to 9 buildings for 1 to 8 location of 1 to 2 move to Austin, Tex, 1 to 9, 4 to 64 pictures of 1 to 2 to 1 to 3 Lafferty JM, 2 to 1. 2 to 4 laser electron, 1 to 10 photon, 1 to 10 LC guides, 8 to 29, 8 to 31 film LC guides, 8 to 31 illustrations, 8 to 28, 8 to 30 load resistor, 4 to 2 loop of charged particles, 4 to 55 pictures, 4 to 54 low electron energy spread, 4 to 48 to 4 to 49, 4-51 pictures, 4 to 49, 4 to 50 low gas pressure effect on EVs, 3 to 22. M. Malmberg, JH, 1 to 10. Mark Geparator, 1 to 11 Mao. Ed. Picture, 1 to 3. MS Old Mark, 5 to 14 measurement of EVs, 3 to 13 to 3 to 21 pictures, 3 to 14 messengers. Resurso R. Z-25 mesiats, GA 2 to 1, 8 to 2. Memeptum Trapsfer, 5 to 2B Moperol oscillator EV, 9 to 8 spherical, 9 to 1 to 9 to 2 more PPG glory structure, 2 to 4 mosaic guide for EVS, 2T2 illustration, 2 to 1Z multi-electrode Sowers S, 8 to 22 illustrations, 8 to 23 to 8 to 24. N. Nardi, V. 1 to 10 neutral emission, 4 to 53 puzzle structures for EV sources, 2 to 16. O'Neill, TM, 1 to 10, optical guides, 8 to 47, 8 to 49, 9B Rorolsiup of EVS APD, 9 to 7 oscilloscope. Requirements for 3 to 26 to 3 to 28. PACER, via electromagnetic radiation, vi Reriodis Strustage of EVs, 7B Resadego, Caliph, 4 to 64, 5 to 1 picopulsar, 3 to 26, low 3 to 27, 4 Zor, 4 to 40, 8 to 16, 8, 19, coupled with field emitter, 8 to 19 illustration, 8 to 19. Picopulsar, Soptipude. Illustration, 8 to 17 to 8 to 18 picoscope, 4 to 20 IU, 4 to 21, 8 to 43, 8 to 45 illustrations, 8 to 42, 8 to 44, pinhole Ellestrop Samra, 3 to 28, 3 to 31 calibration of 4 to 1, 4 to 7 to 4 to 9 illustration, 3 to 29 magnification, used 4B pictures, 3 to 30 plasma deflection and cleanup, 4 to 4 to 4 to 5 point KH RAW source, 8 to 49 illustration, 1 to 48 polarization, ARU PD EVs, 9 to 5 to 9B potential well of EVs 4.1, 2 modulation of 4.27 potentials, vector APD scalar, 9 to 7 to 9 to 8 ROA supply, pulsed RF, fog streamers, to 2 restless messengers of EVs, 3 to 25 properties of EVs, summary, alpha B3 to 4 to 63, Rorolsiup of EVs, 9 to 7 pulse emission, Tegmiopis, 4 to 30, 9 to 4 to 40, pulse ROEG supply, 4 to 2 to 4 to 3 pulsed RF ROA supply, to 2 Puth Califel HAL biographical sketch, 1 to 4 picture, 1 to 3 op 0 point fluctuation, Reaper MEPA, 9 to 2, R radiation propulsion, induced, UEVs, 5 to 26 RC guides, 8 to 27, 8 to 28, RF generators, 8 to 33 illustration, 8 to 34 ring-shaped witness marks, 2 or 9, 2 to 21 pictures, of 2 to 20. Index 6. Scalar potentials. 9 to 7 to 9 to 8, scanning electron microscope. Purchase of 1 to 9, scanning tunneling microscopes, arcing between cathode and anode. 5 to 14 to 5 to 15, Schwertsky Fred. 5 to 15 selectors for EVs. 8 to 37. 8-39 illustration. 8 to 36 separator for EVs. 8 to 13 illustration. 8 to 12 shoulders. Claire. 1 to 9 shoulders Ken. Picture. 1 to 3 shoulders Stephen. 1 to 9 size of EVs. 4 to 23 pictures. 4 to 23 to 4 to 26 sources of EVs. 2 to 15 to 2 to 16. 4 to 1 to 4 to 2. 4-19. See also EV generators. Generating EVS channels. 8 to 25. Electrodeless source. 8 to 11 illustration. 8 to 10 electrons necessary for emitting. 6 to 8 to 6 to 9 field emission diodes. 8 to 15 to 8 to 16 film field sources. 8 to 19 illustrations. 8 to 20 to 8 to 21 gaseous streamer sources. 6 to 9 illustration. 8 to 4 inorganic gases. 8 to 9 long sources. 8 to 22 metal vapor sources. 8 to 5 multi-electrode sources. 8 to 22 non-metallic cathode sources. 6 to 8 nozzle structures for emitting. 2 to 16 optical beam source. 9 to 6 organic gases. 8 to 11 short and long sources. 8 to 1 surface source. 8 to 7 illustration. 8 to 6 synchronous firing of. 2 to 11 to 2 to 12 triggers. 8 to 27 space charge law. 1 to 7. Spherical monopole oscillator. 9 to 1 to 9 to 2 spint, CA. 5 to 17 splash marks. 2 to 4 splitters for EVs. 2 to 14. 8 to 39 illustrations. 8 to 38 staff. Project. 1 to 9 streamers. Charge granularity of. 6 to 7 display of. In Science Museum, San Diego. 6 to 1 effects seen. List of. 6 to 5 to 6 to 6 literature on. 6 to 2 pulsed RF power supply for. 6 to 2 streamer formation chamber. 6 to 4 illustration. 6 to 3 theories on. 3 to 12 witness plates of. 6 to 7 strikes. See target substrates for guiding EVs. 2 to 12 to 2 to 15 surface charging. See charging surfaces surface coating. Effect on EVs. 3 to 9. 3 to 11 surface field measurement. 9 to 4 synchronizer for EVs. 8 to 32. T targets aluminum oxide film. 5 to 18 to 5 to 23. 5 to 26 carbon. Chromium film. 5 to 1 to 5 to 3 conductive backing added. 5 to 3 to 5 to 5 pictures. 5 to 2, 5-3. 5 to 4 to 5 to 5 carbon without chromium. 5 to 5 to 5 to 7 picture. 5 to 6 cathodes and anodes. In scanning tunneling microscopes. 5 to 14 to 5 to 15 dielectric materials. 5 to 17 to 5 to 26. Field emission diodes. 5 to 17 pictures. 5 to 16 gas and vacuum strikes. 5 to 13. Targets. Soptipute low pressel HEPOP. 5 to 9 to 5 to 12 pictures. 5 to 10 to 5 to 12 Tesla coil IP air. 5 to 7 to 5 to 9 Ristuge. 5 to 7, 5 to 8 Tesla coil in air. As target, 5 to 7 to 5 to 9 pictures. 5 to 7, 5 to 8 Thegmiopis pulse emissions. 4 to 39 to 4. Thick film processing. 3 to 27 Thomson, Joseph John. 3 to 13 time, jitter, 2 or 2 to 12. Travelling waves conclusion of efforts. Toward 7 to 6 delay line for 7 to 2 device description, 8 to 47 downsizing the tube, 7 to 5 EV coupling to travelling wave Sigtritz illustrations, 8 to 46 length limitations, 7 to 2 multiple EV generation, 7 to 4 results of test, 7 to 4 to 7 to 5 subscripized guidance for EVs, to 1 tube design, 7 to 3 wash forms, 7 to 3 to 7 to 4 triggers, for EV Jeparatiop, 8 to 27 tubing, fused quartz, 4 to 55 to 4 to 58. Turning, a Hacha of EVs, 4 or 4, 4 or 6 pictures, 4 or 5, 4 or 6 twin, EVs 4 to 51 picture 4 to 50. Y. Chasium Ars 2 to 1 pictures Ol 3 to 10 surface coating and 3 to 9 chasium. Riekdaup op dielectric surface 1 to 11 to 1 to 12 Chester potentials 9 to 7 to 9 to 8 velocity of EVs 4 to 2 L 9 to 7. Chortek filaments 1B to 1 to 7, 1 to 10, 1 to 12, electromagnetic guidance for 1 to 10 size ecrogimepts, 2 to 1, 1 to 2 to 12, 2 to 2 or to 2 to 23 pictures of 2 to 22 theory of Ocker-Terpt, 2 to 23. W waterglass substrate, 2 1 foot 4 inches watchfogs, 4 to 2 to 4 to 3 aperiodic watchforms, 8 to 35 measurement device, 4 to 20 witness marks APD plates, 2 to 1 Richters AF, 2 to 2 TL 2 to 4, 2 to 8 ring shape D, 2 to 19 to 2 to 2 RCM pictures of 2 to 10 streamer tests, 6 to 7 work methods, 1 to 7 to 1 to 8 working E-rays, Imrotaps Ol 2 to 7, 2 to 91 minus 1. X-rays emission, Srestrachem, 4 to 12, emitted, UEVs, 2 to 7 to 2 to 18, 4 minus 33, 4 to 35, 4 minus 53 pictures, 4 to 34 point, KH Rao Yors, 8 to 49 illustration, 8 to 48, Kepop gas low pressure, as target 5 to 9 to 5 to 12 pictures, 5 to 10 to 5 to 12, for producing streamers, 6 to 3, Z, 0 point fluctuation dritch, 9 to 2.